আরে হ্যাঁ কোন লিঙ্ক? না না না, এসকে স্যার।
So good afternoon all. With respect to Indian Standard Time, I'm sure that we have viewers from all over the world. And on behalf of the Department of Mathematics, Presidency University, it's our great pleasure to welcome you all to the International Conference on Algebraic Graph Theory and its applications. In short, we call it ICAGTA 2020. So within this conference, we have this 2 days conference, and within this conference, we'll witness 4 big names in the field of graph theory: Professor Brian Alspeck, Professor Peter Cameron, Professor Deborah Boutin, and Professor Dragan Maruzic. So I'm sure that we'll able to see very new and recent advancement in this field from the very basic to the end. Along with that, we'll also have the paper presentation sessions, and I'm sure that all over the world, people will join us and will present their papers. So we got many papers. After 2 times, the coordinator will describe all the things in details. Shortly, we are going to start our inaugural session, but before that, may I just request all the participants to please mute your microphone during this talk and turn off your camera so that it will not distract the speakers during that talk and all. During this talk, throughout the day almost, we'll give the link for participation or attendance certificate. So all of you, those who are willing for this participation certificates, are requested to fill that form only once for 1 day. That will be sufficient. New link will be sent for tomorrow. And for the rest of the days, we'll do the same link will do. So we are also viewers from YouTube Live. So YouTube Live viewers are also there. And I'm sure that they are going to enjoy the whole thing. And we have already many participants all over the world. So the first thing that we are going to start very shortly, the inaugural ceremony. And for that, our Honorable Dean Sir, our Honorable Dean of Faculty of Natural and Mathematical Sciences, Professor Shankar Bose, is already with us. So without any further delay, I will just switch on the mic to him so that he will give the inaugural speech for this conference. Sir.
Thank you, Dr. Angsuman Das, convener, Professor Abhishek Odhikari, Dr. Tapon Shah, head of the department, my colleagues, respected teachers, speakers, researchers, and dear students. Thank you and a very good afternoon. I'm privileged to be a part of this great academic review. On behalf of the Presidency University, I welcome you all in this August gathering. This day we have assembled here to be a part of the 2-day webinar on International Conference on Algebraic Graph Theory and Applications, which in short, as it was explained before, ICAGTA, which is organized by the Department of Mathematics, Presidency University, Kolkata. This conference is aimed at instilling exciting ideas to the young researchers working on this topic of graph theory. Going through the speaker list, I'm very much certain that many exciting possibilities will emerge and stimulating discussions will follow. We are passing through a very dark time, unsure about when and how our lives will return to normalcy. The academic fraternity has been kept out of public activity for safeguarding our young citizens. And this imposed isolation has created a huge toll on the minds of students, teachers, and educators. The present endeavor of the Mathematics department is in that way a very positive change in diverting our minds from the gloom. This is what one quite expects from a department which remains active since the year 1817, when this great institution was founded. Brings thousands of students who have made their presence felt in the world of mathematical sciences. Thank you again for inviting me at this conference. I officially declare this conference open.
Thank you, sir. Thank you very much for your nice speech and motivating inaugural talk for all of us. Thank you very much. Now it's the time for our Honorable HOD, the Department of Mathematics, Presidency University, Kolkata, to say a few words towards the participants. Dr. Shah, please.
Thank you, Professor Odhirari. So, I think Dr. Angsuman, convener of this conference, will talk about the conference. So, let me take this opportunity to say a few words about the department. So, before that, I again thank Professor Sampar Ghosh, Dean of the Faculty of Natural and Mathematical Sciences, to inaugurate this program. So, I also thank our respected invited speakers, Professor Peter Cameron, Brian Alsbach, Devda Bautin, and Dragan Medusik, for being agreed to deliver lectures in this platform. So again, welcome to this International Conference on Algebraic Graph Theory and Applications, organized by the Department of Mathematics through online mode. So the Department of Mathematics has started its journey since the inception of Hindu College in 1817. The Hindu College, then the name of this university. The Hindu College then transformed into Presidency College in 1855, and then in recognition of its academic excellence, the college was upgraded to university in 2010. So, as being part of this celebrated institution, the Department of Mathematics has a rich history. It has many notable alumni, including Satyendranath Ghosh, Meghnad Saha, Shyamadash Mukhopadhyay, Radhanath Shikdar, Nikhil Ranjan Sen, Sir Ashutosh Mukherjee, and many others. And besides teaching and research as part of academic activities, the department on a regular basis invites distinguished scholars to visit the department and deliver lectures. The department also organizes a teachers enrichment workshop funded by the National Center of Mathematics. And as part of extension activities, the department organizes outreach programs for high school as well as undergraduate students in order to motivate them to learn mathematics. Faculty members of this department do collaborate with reputed national and international institutes for their research work. The department this year has also been awarded grants by the Department of Science and Technology, Government of India under FIST program. So, and few months ago, in this pandemic situation, the department also had organized a series of webinars where the faculty members had delivered lectures in a variety of topics in mathematics. And this time we are organizing this international conference on algebraic graph theory and applications. So I do believe, in fact, I strongly believe that we will be having a fruitful discussion, and we'll be all enjoying the lectures to be delivered by the invited speakers as well as the contributed talks. Thank you once again, and welcome to this international conference on algebraic graph theory and its applications. Thank you very much.
Thank you, our Honorable HOD, the Department of Mathematics, Presidency University. Now, may I request the coordinator of this workshop, Dr. Angsuman Das, to briefly describe about the details about this conference. Thank you.
Good afternoon to all of you. So to start with, the motivation behind organizing this conference was to motivate researchers in India towards algebraic graph theory, mainly automorphism groups of graphs and their applications. So graph theory as a topic is quite popular in India, but in this particular branch of graph theory, which is related to graph automorphisms and their applications, I think that is not going that far in our country. So with this idea in mind, I approached all the four speakers, Professor Alsbach, Professor Cameron, Professor Maruzik, and Professor Boutin, to organize such a gathering. They were kind enough to give their consent and guided me on how to choose the topics of the lecture so that it goes well with the participants. And regarding the conference, it consists of two major aspects. One is the invited lectures by experts, and the other is the contributed talks by participants. In the invited lecture section, we have four eminent speakers. The first talk will be by Professor Alsbach, who will be mainly speaking about graph automorphisms and basics of algebraic graph theory. His talk is splitted into two lectures. Then we have Professor Cameron, who will be talking on different types of graphs defined on groups. Then we have Professor Maruzik, who will talk about the history and about the famous polycirculant conjecture and semi-regular automorphisms over graphs. And finally, we have our final speaker, Professor Boutin, who will discuss the determining sets of graphs. In the contributed talk section, we have received over 50 submissions all over India, but unfortunately, we can select only 15 of them due to time constraint. At this junction, I would like to thank all the authors for their submissions, and I would like to congratulate those whose papers have been accepted. So with that, and finally, I'll be talking about a few things that the participants need to take care of. First of all, while the lectures are on, please keep your microphones and camera off. Except the speaker. Others, please keep your microphone and camera off. And whenever you have some question, it's better not to interrupt the speaker unless he says so. So it's better to ask the questions at the end. You can either ask the questions at the end by switching on your mic, or you can write the questions in the chat box so that we can relay the questions to the speaker at the end of the lecture. So with that, I now invite Dr. Shubhra Bhattacharya to formally introduce our first speaker, Professor Brian Alsbach.
Thank you, Angsuman. Very good afternoon to all of you in India, and good evening to those who are outside India from abroad. The first invited talk of the session would be delivered by Professor Alsbach. He would be talking on the basics of algebraic graph theory. The lecture is, as already told by Angsuman, is divided into two parts, and the second part of the lecture would be delivered tomorrow. So, Professor Alsbach.
Can you hear me?
Yes, sir, we can hear you. Yes, Professor Alsbach, we can hear you.
Good. I'm trying to get my talk up now.
Okay. Just a bit of introduction about Professor Alsbach. He is distinguished for his research in the field of graph theory. He is known for his research contributions on topics like tournaments and digraphs, permutation group, and actions on graphs, decomposition and factorization, and Hamiltonicity of graphs. He actually advocates application of theory on and complex mathematics for solving real-life problems like the business world. He is also famous for Alsbach conjecture on disjoint cycle and complete graph. Professor Alsbach did his BA in Maths in the University of Washington and graduation and PhD from the University of California, Santa Barbara under Professor Paul Kane. Currently, he is a conjoint professor at the University of Newcastle, Australia. On account of Professor Alspach's 65th birthday, Professor Joy Maris, who herself is a distinguished graph theorist, published a nice article titled Professor Alspach and His Works on discrete mathematics. Interested participants are encouraged to look into the book to learn more about Professor Alspach, his life and work. As of now, let us all welcome Professor Alspach and begin the session. Thank you.
Are my slides on your screen?
Not yet, sir.
Not yet.
Could you please
You
present
can
now?
click the option present now. On the web browser, on the bottom right corner, you will find an option called present now.
Okay, then present now. So what? Just as your entire screen, right?
Yes.
Yeah, enter the screen.
So that should be it there.
No, it hasn't started yet.
Is it?
I think he has to click on the screen.
It's not.
Yeah. I mean, once you have share your entire spheres on your screen.
And there will be a box. Inside that you have to click. Yeah.
Yeah, now it is starting.
Good.
Ah.
Yeah, thank you.
Yeah, now you can show your slides. I mean, you can pass on to the slides tab.
Yes. Perfect.
Yeah, can you make it full screen?
Let's see. View should be under view. View.
Yes. Now
Okay.
it's fine.
Yeah,
Right.
it's perfect.
So first of all, I'd really like to thank the organizers for inviting me to take part in this. It's my first time giving a talk live online. It's sort of interesting and quite challenging in its way, just as you noticed, trying to get my slides up on the screen. And I was asked to just talk about some basics of algebraic graph theory, which is what I did. Included some exercises in here, and for most of you, they're probably quite straightforward, but they might be good exercises for students and so on. And I'm going to, first of all, mention a little terminology that I use that may not be the standard terminology that you're used to. So just mention a couple little things here quickly. So I'm going to denote edges as showing there, and that means then a path will be listed that way, and to differentiate that in a cycle, you'll notice that for cycle, I have the same vertex at the end and the beginning of the sequence. Now I'm going to use the word valency instead of degree, because degree we use for permutation groups. So the valency of a vertex is the number of edges incident with it. And I'm going to be talking now about symmetry in general. Now, symmetry, of course, is a very general concept, and almost everybody has an idea of what we mean by symmetry. And it of course, shows up in ways in architecture, music, all kinds of things, and some of these ways are surprising. In graph theory, we usually interpret symmetry in terms of the automorphism group, and so that's what we'll be looking at next. So automorphism groups of graphs, of course, are permutation groups, and rather than have a section on permutation groups, I'm just going to interlace a few results about permutation groups that I need as they arise, and we'll start with a couple of definitions first. So S sub n is going to set the whole permutations of an n set. It's clear that the order of that is n factorial, and it forms a group under function composition. And now I'm going to use function compositions as f of g is defined by letting G act first and then F. And so I'm reading from right to left when I compose functions. S sub n is called the symmetric group of degree n, and a permutation group of degree is a subgroup of S sub n. Now, there's actually nothing sacred about defining this in terms of the set 1, 2 up to n, so I'm just going to use the same notation anytime the set has cardinality n, and so it's just clear from context always what the set is, and so that you know what the group is acting on. Now, there's a very important equivalence relation you define on the set omega, in which the permutation is acting. And that's this notion that two things in the object set omega are related if there's a permutation mapping x to y. Now, it's easy to show that that's an equivalence relation on omega, and the equivalence classes for this relation are called the orbits of the group. So here's just one little exercise. Just prove that that relation is in fact an equivalence relation. Now, an automorphism of a graph, then, is a permutation of the vertex set, and it satisfies it. Has to preserve v is an edge in x, then f of u, f of v is an edge in x. And if you take all the automorphisms of the graph, they clearly form a group under function composition, and that's called the automorphism group, and we'll be denoting it aut x. So, in fact, another exercise is just actually prove that this is actually a group. Okay, now let's look at a very small example. So here's a path blue. Easy to see that that graph has two automorphisms, right? You have the identity permutation, and you have the permutation that fixes u sub 2 and interchanges u sub 1 and u sub 3. And now that notation that I'll be using for permutations, that's so-called cyclic notation, and you read that cycles from left to right. So u sub 2 is a cycle of length 1, so it's fixed, and u sub 1, u sub 3 is a cycle of length 2, so you read that u sub 1 gets mapped to u sub 3, and then you keep going down the cycle, the last element in the cycle. U sub 3 is mapped back to the beginning element. And this is a convenient notation for many situations. So if you have a permutation group with a single orbit, it's called transitive. And that means simply that if you take any two elements in the object set omega, you can find a permutation that maps x to y. And finally then, if you have a graph now and that automorphism group is transitive, we call it a vertex transitive graph. And these are very basic objects. And they are the objects that people frequently think of as having a lot of symmetry. So here's the graph. So we have an 8 cycle with the diametrically opposed vertices joined by edges. So we can just think of those as the diameters. So we're curious as to what the group of this graph might be. Now, it's easy to see that it's a vertex transitive because you can cyclically rotate it either clockwise or counterclockwise one time, and you can map any vertex, any other vertex. But what about the order of the group? How big is the automorphism group? Well, one thing to notice is look at the edges around the outside of that graph, and you'll see that they belong to exactly 1 4 cycle. You can only get 1 4 cycle from a given edge on the outside. And if you take a diameter, the diameters belong to 2 4 cycles. So so the outer edges of the cycle have to be mapped to themselves. And that tells us that the automorphism is acting on the cycle, as a group acting on the cycle. So the automorphism group of that graph must be a subgroup of the group acting on an 8 cycle. And now let's look at this group a little bit. So we will look at the symmetry group of an n gone. Okay, there's an element, I'll call it rho for rotation, of order n that rotates the n gone. And there's a reflection tau. that rotates the n-gon around an axis, either joining two diametrically opposed vertices if the number of vertices is even, or the axis joining a vertex in the midpoint of the opposite edge. So you can see that the permutation tau has order 2, and tau rho tau, which is conjugation of rho by tau, that you get rho inverse. And that's the so-called well-known dihedral group degree n. Now, again, I'm going to use d sub n since it's a subgroup of n. Many people will use the subscript on the dihedral group as the order of the group, but I want to be consistent with this notion of degree. So the automorphism group of that graph is d sub 8, and because we see rho is an automorphism, and it's easy to see that the involution tau, that reflection, is also an automorphism. So that's the full group. Now that method of finding the automorphism group is, of course, an ad hoc method. And we'd be lucky in other cases. So we need a tool that's sort of general, and that's what I'm going to look at next. So given a permutation group G acting on a set omega and an element X belonging to omega, the stabilizer of X, we're denoted that way, sub G telling you the group and what it's stabilizing, that consists of all the elements in the group that fix X, that map X to itself. And that's called the stabilizer. So mental exercise prove that the stabilizer actually is a subgroup. So here's the theorem 1 in all these notes I'm presenting, the so-called orbit stabilizer theorem, and it tells us that if you have a permutation group acting on omega and let delta of X denote the orbit containing X, then it turns out the order of the group G is the cardinality of the orbit times the order of the stabilizer of X. And that's a very useful theorem because oftentimes it's easy to determine the cardinality of the orbit, and the stabilizer is a smaller group, so it's easier to determine in general than G directly. Now another little exercise is prove the orbit stabilizer theorem, and here's a little hint. And I just include that hint because one of my favorite proof styles is to define a set in two, and then count the set in two different ways, and that's exactly what's happening here. Use when you can. Now we're going to apply the orbit stabilizer theorem in a little more interesting situation, but before I do that, I'm going to make a digression here. Okay, now one of the basic themes throughout mathematics is classification. So that is, you're given a collection of objects, and you'd like to have some nice description characterizing all of the object. Now, of course, there's some subjectivity as to what is meant by nice description, and I don't want to get into discussing that topic. I mean, something to be a nice description, and others might say, well, that doesn't really satisfy me. But so we won't go in that direction. But one natural classification result, of course, would be a classification of vertex transfer graphs. And we're going to look at this and shall see that it appears to be a difficult task in the sense of trying to find a nice classification. So what we're going to do is look at several constructions for producing vertex transfer graphs. So if you have a permutation group G acting on a set omega, in a very natural way, that group G acts on other sets. One such action to look at is how the group acts on K subsets. And it's very simple. It's just exactly how you would expect it to be defined. If you have a permutation in your group G and a K subset, then the image of that subset under this permutation is acting like F, and I'm calling it F. I'm overlining it there because it's acting on subsets. It's not acting on individual elements. So you simply define the image of the subset to be equal to all the elements there where they are mapped by F. So it's clear to see that that thing is mapping subsets to subsets. So it's pretty clear that F to F overline, that's a homomorphism of G to a permutation group G over line. I guess I'll call it G. And so a nice little exercise now is to show that that homomorphism actually is an isomorphism whenever the cardinality, whenever K is less than the cardinality to omega. So because of exercise 5, you're going to become sloppy and use G rather than G bar and simply speak of the action of G on the subsets. So that should make it clear what we mean. So the first construction I want to mention is the Presidency. So we can use that notation, NK. So this is the graph that you form by using all the K subsets of an N set. So that means the number of the and we're going to say two vertices are adjacent if and only if the subsets are disjoint. So that means then that this Kineser graph, it has order n choose K, because that's the number of K subsets. And if K is too big, namely if it's strictly greater than n over 2, then of course any two K subs intersect, so the graph has no edges. But if the K is less than or equal to n over 2, then the valency of this graph is n minus K choose K, and that's pretty easy to check. So another next little exercise is just prove that that graph is in fact vertex transitive. Okay, so here it's a talk on graph theory. So at some point the Peterson graph is going to arise, and there it is. So here's the Peterson graph demonstrated as a Kineser graph. So you notice the 10 vertices are labeled by the 10 subsets of cardinality 2. And you'll notice there's an edge exactly when those subsets have no element in common. That is, they're disjoint. And this is a useful way to define the Peterson graph because it does help in determining its automorphism group. Now, from exercise 6, we know that the vector group with degree 5 is contained in the automorphism group with this graph because you let S5 act on the two subsets and you get automorphisms of that graph. And the question is, what actually is the order of the automorphism group of the Peterson graph? Oops, I better get rid of hide there. So we're going to, I want to use the orbit stabilizer theorem to show that S5 is the entire automorphism group. Okay, so let's let G be the automorphism group of the Peterson graph. Now the orbit stabilizer theorem tells us that then the order of G is equal to 10 because the graph is vertex transitive. That's pretty easy to check. Times the stabilizer of one of the vertices. So let's just fix the vertex corresponding to the subset 1, 2. So now I need to get the order of that group, that smaller group. Well, the permutation, that permutation there that fixes one fixes, it's 3, 4, 5 in a 3 cycle. That's fixing the vertex 1, 2, and it's cyclically permuting its 3 neighbors. So that tells us then that the orbit of 3 under the stabilizer has cardinality 3. So then that means, using the orbit stabilizer theorem again, that the order of the stabilizer of the vertex 1, 2 is 3 times the subgroup that fixes both 1 and 2 and 3 and 4. Now the transposition 1, 2 fixes both vertices 1, 2, and 3, 4, and it interchanges the vertices 1, 5, and 2, 5. So that tells us that that stabilizer of those 2 vertices, that the vertex corresponding to the 2 subset 1, 5 lies in an orbit of size 2 or length 2 or cardinality 2, whatever is your choice. So now you fix 1, 2, 3, 4, and 1, 5, and then that forces 2, 5 to be fixed, and its own other neighbor, 3, 4. And when you fix those 4 vertices, the only non-identity automorphism you get is this. And now we work backwards, so you get the stabilizer of the group that's fixing those 2 vertices is 4. That implies the stabilizer of the vertex corresponding to set 1, 2 is 12, and then 12 times 10 is 120. So using the orbit stabilizer theorem, we see that the order of the automorphism group of the Peterson graph is 120. So that's S5. Now, in terms of kinesia graphs in general, you might wonder if some of the conditions can be relaxed or modified. And there are a couple of special situations that have names and have been studied for various properties. So the so-called odd graph, O sub n, is in fact the kinesia graph with the cardinality of the set 2n minus 1 and the subsets n minus 1. So in fact, you'll notice that the Peterson graph is O sub 3. Johnson graph, JNK, has the k subsets of an n set for its vertex set, but here you make 2 vertices adjacent if and only if the corresponding subsets intersect in k minus 1 elements. So they're as close to being each other as possible. So those are 2 well-known families of graphs, although the odd graphs are a small family, but they both have outstanding problems. So in general, then, you can take all k subsets of an n set and make vertices adjacent if the intersections have some fixed property. These graphs will all be vertex transitive because of the action of the symmetric group on the subsets. Okay, now I'm going to look at an example that's a little more geometric construction. So let f of q, this is the finite field with q elements, then recall then of course that q is a prime power. And I'm going to start with a set of q to the n tuples. So you look at n tuples using the elements out of the field of order q. So of course at the end of them. And now you can easily get a vector space, VQ of n, by defining addition of 2 n tuples according to the obvious rule. You add them coordinate by coordinate. And we're going to use the field itself as a scalar field and define multiplication by a scalar according to the obvious, the scalar multiplies every coordinate. Okay, so just an easy exercise, show that that is in fact a vector space of dimension n. Well, now we're going to use that set, that vector space, to define some vertex transitive graphs. So let V, Q, N, RS, so the 2 parameters there. The vertex set then will be all of the subspaces of dimension R, and you'll put an edge between 2 vertices corresponding to 2 R-dimensional subspaces if they intersect in a subspace of dimension S. So clearly S has to be less than or equal to R for you to have any chance of anything interesting. And when S equals 0, it means that the 2 subspaces have only the 0 vector in common. Now, in this case, note that a non-singular linear transformation of that vector space is an automorphism of the graph. Okay, I just want to consider 2 quick examples to show you the kinds of things that can happen. So let's first of all look at V q to the n 1, 0. So this means the order of that graph is going to be the number of one-dimensional subspaces. So how many are there? Well, each one-dimensional subspace has q minus 1 non-zero vectors in it. So that means the number of one-dimensional subspaces is q to the n minus 1, because you're throwing the 0 vector out, divided by q minus 1, and we get that sequence of powers of q, starting with q to the n minus 1 down to q to the 0. And I'm just going to, for simplicity, I'm just going to call that n of 1. Now, any 2 distinct one-dimensional subspaces clearly have only the 0 vector in common. So that means that this graph, in fact, it's the complete graph of order n1. But let's get a little more interesting here. Let's consider now that using the two-dimensional spaces and say that the two-dimensional, two of them are adjacent as vertices if they intersect in a space of dimension 1. So what's the order of this graph? Well, any one that's in a two-dimensional subspace. Now, the number of one-dimensional subspaces we saw was n of 1. So that gives us n of 1, choose two pairs. However, some of these pairs are going to determine the same two-dimensional subspace. So we have to get rid of redundancy. So look at a two-dimensional subspace. It has q squared minus 1 non-zero vectors, and each one-dimensional subspace has a zero vector plus scalar multiples of a non-zero vector. So that means that you partition the non-zero vectors into q plus 1 sets of cardinality q minus 1, each corresponding to one-dimensional space. So that means the order of that graph is that ratio of two binomial coefficients. To determine the valency, we have to determine how many two-dimensional subspaces intersect a given two-dimensional subspace in a one-dimensional space. And I'm going to leave that as interesting. The trick exercise so far is to prove that the valency of that graph is that number shown there, the quantity q plus 1 times q to the n minus 1 divided by q minus 1. And another exercise is to prove that, in fact, the graph is vertex transitive. So there you have to use something about linear transformations. Now I want to use VQ cubed 3 to define. So start with the q squared plus q plus 1 one-dimensional subspaces and remove the zero vector from each of them. So that means they now have just q minus 1 elements in them. And I'm going to represent a given set of q minus 1 non-zero vectors by any triple belonging to the set. We're really defining an equivalence relation here, but I'm not going to be mentioning that particularly. Now, no matter which vector we choose as a representative, the other elements of the set, of course, are just a scalar multiple of that representative. Do the same thing again, and I'm just going to use square brackets now. And what I choose for representatives, it's completely independent of what I did up above. Nevertheless, we have now these two collections of triples. We have q squared plus q plus 1 triples of the form with parentheses and of the form with square brackets. So I'm thinking of a bipartite graph here. So what I do is one part is going to contain all the triples with the parentheses, and the other parts can contain the triples with the square brackets. And I'm going to say that two vertices are adjacent if and only if the inner product of those two vectors is 0. Note that that inner product being 0 is independent of which representative I chose, because multiplying by a scalar doesn't change the fact that the inner product is 0. So that's why we don't worry about which one we choose as the representative. The product equation arises from multiplying the 1/3 matrix on the left of the matrix that transpose. That matrix has rank 1, so that its null space has dimension 2. And this means that there are q plus 1 triples orthogonal to it. So the valency is q plus 1. So we've got q squared plus q plus 1 vertices, and 2 times that, and this valency is q plus 1. And for those of you familiar with geometry, working on the graph, it's the point line incidence graph of objective plane. But I'm not going to be exploring this any further, but it just again illustrates that you can get some nice, interesting vertex transitive graphs by looking at finite geometry. So we've seen several ways in which vertex transitive graphs are. And finally, I'm now going to use groups to define another family of vertex transitive graphs. And this family is the most heavily studied family. vertex transit graphs. So you start with the group, and you can do this for infinite groups, but I'm just going to do finite groups. You take an arbitrary subset of G with two restricting properties. First of all, the identity is not in S, and S is inverse closed. That is, little s is in S if and only if little s inverse is in S. Then we form a graph denoted KG semicolon S, whose vertices are identified with the elements of the group, and an edge from little g to the G times S on the right is on this G. This is called the Cayley graph on G with connection set S. A few comments are in order now. The reason I exclude 1 is that we don't want loops in the graph. And the reason we have it inverse closed is, of course, the element S, that gives you an edge from G. If you're standing on G, you get an edge out to G times S. But you'd like to have the same edge arise if you happen to be standing on GS instead. Well, of course, what you have to GS by to get G is S inverse. And we treat that as the same edge. We don't have an edge for each direction. If you're working with Cayley digraphs, then that's a different story. One other little comment here, if G is a billion, I use additive notation. So here's an example. I'm going to look at a Cayley graph on the billion group, the direct sum of Z3 and Z6. So you'll notice the horizontal coordinates are 0, 1, 2 for Z3, and the vertical coordinates are 0 through 5, the elements of Z6. I'm going to let the connection set be as shown there. Those are the edges now that are generated by 1, 0 and 2, 0. Those are the edges that are generated by 0, 1 and 0, 5. And so that's the Cayley graph on that group with connection set consisting of those 4 elements. The transitive permutation group acting on omega is said to be regular if the order of G happens to be the same as the cardinality of omega. And here's a theorem that, again, is quite useful. It turns out that these 3 conditions for a group to be regular are equivalent. Number 1 is the condition we use for the definition. But the second really useful thing to know is that for any vertex, the stabilizer is just the identity. Or another property that's very useful is that if you take an x and y and omega, there's a unique permutation in G mapping x to y. So exercise 10 is to just prove this theorem. Now, if you have the group G and let capital L sub G denote left multiplication by the element G, so LG of x is equal to G times x, it's easy to see that that, of course, is a permutation because we're in a group. And it turns out that if you have a Cayley graph on G, then it turns out that left multiplication is in fact an automorphism of x. And that's easily seen because if you have an edge from x to ys, because S is in your connection set, then you have an edge from G times X to G times Y, and because this is there. So that means that left multiplication maps edges to edges. So that's an automorphism. It's then easy to see that if you take the group, left multiplication, that's a group. This group is regular, and it's called the left regular representation of G. And an exercise 11 is to prove that, in fact, that is a regular group. So if you have a Cayley graph on the group G, from the preceding, what we've seen then is that that subgroup of all the left multiplications is the subgroup of the automorphism group. And a classical theorem of Sabadusi from 1958 says that a graph is a Cayley graph if and only if its automorphism contains a regular subgroup. Exercise 12 is to prove theorem 3, Sabadusi's theorem, and just a hint here is the useful thing is that there's a unique element mapping a given vertex to another vertex if you you have a regular subgroup. Now, theorem 3, This is essentially the only tool we have to determine if a graph is a Cayley graph. So it's an important result. So now what we've seen is that there are a variety of methods for reducing British transit graphs, and it would appear that none of these methods are going to produce all of them. And so let's just explore this for just a moment. So earlier we saw that the Peterson graph is vertex transitive and that its automorphism group is S5 acting on the two subsets of a 5 set. So if we can show that the latter group has no regular subgroup, then by Sabadish's theorem we know that it's not a Cayley graph. So how do we do that? Well, suppose there's a regular subgroup H of the automorphism group Peterson graph. So let's call H hat the pre-image of that group in S5. So you've got this regular subgroup H, which is of degree 10 because it's acting on the two subsets. You've got its pre-image H hat, which is acting on 5 elements because it's a subgroup of S5. So let's just think about it for a minute. So no permutation of F H hat can have a transposition in its disjoint cycle decomposition, as this would give us a non-identity permutation in H with a vertex. And we've seen that regular subgroup, the only vertex or the only element that fixes a vertex is the identity. So that means that no permutation in that pre-image can have a transposition in a cycle decomposition. Similarly, no non-identity permutation of H hat can have 2 or more fixed points, as again you get a non-identity element of H with fixed vertices. Well, if you can't have transposition and you can't have more than one fixed, that means the non-identity elements of H hat are either 5 cycles or a 4 cycle and a fixed point, but 5 cycles yield elements of H that are products of 2 5 cycles, and the other one yields an element of H, which is a product of 2 4 cycles and a transposition. So there's nothing giving an involution, and H can't exist because H has order 10, so it has to have an element of order 2. So the Peterson graph is not a Cayley graph. Now I want to explore a little bit about characterizations of various families of vertex transitive graphs. I have to check how I'm doing on the time here. So a Cayley graph on a cyclic group is called a circular graph. So I'm going to spend a little time on them. And we need another old theorem from group theory, but first a little notation. So let F of P be the finite field of prime order, and let Fp star denote the non-zero elements. And let me remind you that that's a cyclic group under multiplication. So now I want to define a function T sub AB, where A is an element in the multiplicative, so it's non-zero in other words, and B is an element, thinking of it, in the entire field. So what TAB of X does to X, it maps A times X plus B. Now it's easy to verify that that function is a permutation of the field. And exercise 13 is to determine the inverse of that. So now a permutation group G acting on omega is 2 transitive if you take any 2 ordered pairs where the elements in the ordered pair are distinct. So X is not equal to Y and Z is not equal to W. And there's an F now that maps X to Z and Y to W. So in other words, any ordered pair of distinct elements can be mapped to any other ordered pair of distinct elements. And we can say that the group then is 2 transitive. Now, if X is a graph of order n, and the automorphism group is 2 transitive, then that it's easy to see that that forces X to either be the complete graph or the complement. Because if you have one edge in the graph anywhere, if the group is too transitive, you can map that to any other pair, and that forces every edge to be in the graph. So in this situation, then that means that the automorphism group is the entire symmetric group. So that two transitive groups arise pretty much only in trivial situation when the graph is either complete or the complement of complete graph. Now here's just an aside for a moment. So the permutation groups generated by a single 3 cycle there, and if you look at the group generated by the product of 2 3 cycles, as far as groups, they're isomorphic because they're both cyclic groups of order 3. However, they certainly are different permutation groups. I mean, one has degree 3 and one has degree 6. Now, I don't want to go into details here, but we're going to say that 2 permutation groups are isomorphic as permutation groups if you can find a bijection between the 2 sets that they're acting on, so that they're essentially the same permutation group under that bijection. And I'm going to use the notation G, that whatever the symbol's called, an H. And of course, with this example here, the 2 things are not isomorphic as permutation groups because there's certainly no bijection between 3 sets. So theorem 4 then, here's an old theorem of Burnside. And it tells us that if you have a transitive group of prime degree P, then the group is either 2 transitive or it looks like a collection of those TAB permutations. Now, if you see a result like this and you're interested in graph theory, as soon as it says it's either 2 transitive, well, you know then you're dealing just with the trivial cases of the complete graph or its complement. And so in all other cases, and that tells you that the group has to look like this. So looking at that statement there just a little bit, notice that A, the first subscript, that's roaming through a multiplicative subgroup of the field, and B is roaming through the entire field. Now, this group has a unique subgroup of order P, and we're going to use that fact later. And you can, T10 is the element that generates that group. Now, theorem 4 then is a powerful tool for gathering information about vertex transit graphs of prime order, as we shall see. And you're going to see that some classification here is really completely done. So first of all, if X is a vertex transit graph of prime order P, then it's a circular graph. And this is easy to prove, so we're just going to look at the little quick proof here. So by the orbit stabilizer theorem, since it's vertex transit, P must divide the order of the automorphism group. So that means that the automorphism group must contain an element rho of order P. But what's the order of a permutation? Well, the order of a permutation is the least common multiple of the cycle lengths in its disjoint cycle decomposition. But you only have p to work with. That tells you that rho, in fact, must be a p cycle. And of course, a p cycle generates a regular subgroup. So the result follows from Sabadusi's theorem. So right away now that tells us that we can say a lot about vertex transit graphs at prime order because they're all circular graphs. There's nothing else. And we can do much more than that. So let's look at that for a minute. So in 1967, James Turner published this paper, which was a very nice result. it tells us that if you have two circulant graphs of prime order, one with connection set S and the other one with connection set S prime, then they're isomorphic if and only if there's this very nice relation between S prime and S. Namely, you can find a non-zero element in the field such that S prime is just equal to A times S. Of course, A times S simply means A times everything in S. And so that's a very nice, straightforward condition for isomorphism for vertex transitive graphs of order P. Now, that wasn't what Turner was interested in. And we'll come to that shortly. So just proving, let's look at a proof for this result now. Turner's proof used eigenvalues of the adjacency matrices, but there's a much easier proof, I think, and this is proof of that. So label the vertices using the elements of ZP, but I'll put a prime on the labels of the vertex set for the circular graph with connection set S prime, just for convenience. And now let's suppose that S prime is equal to A times S for some non-zero element in the field. Okay. Well, let's define a function now, a pretty obvious function. So the vertex I in the first circular graph, I'm going to map it to the vertex A times I prime in the second circular. So now let's check that it's mapping edges to edges. So if you have a first graph, that means you have two vertices of the form I, comma I plus S, because S is in the connection set. That they get mapped to AI prime and AI plus AS prime. And there's an edge joining those two vertices because if you subtract, in the second case, if you subtract the AI prime from the other term, you get AS prime, and that belongs to S prime because S prime is equal to AS. So that function is easily seen. What about the other direction? Well, first of all, if the graphs are either complete or complement of the complete graph, then the theorem is trivially true because you've got full connection set on the complete graph or empty in the other case, so they certainly are multiplicatively related. So now let's suppose we have two isomorphic graphs. Now, that means that there's an isomorphism F that maps 0 to 0 prime, because the graphs are vertex transitive. Now, from Burnside's theorem, remember we said that there's a unique subgroup of order P. So the permutation 0, 1, 2 down to P minus 1, and 0 prime, 1 prime, 2 prime, down to P minus 1 prime, they generate the unique subgroups of order P in the respective automorphism groups. So that's the only way you're getting that subgroup of order P. Now, since F is an isomorphism, that means F of 0, F of 1, F of 2, and so on, belongs to the automorphism group of the second circulant graph. And therefore, that's a P cycle. It has to be some power of 0 prime, 1 prime, 2 prime. And that has to be a power that's non-zero because they're both P cycles. And so once the eighth power of that, of course, is 0, A prime, 2A prime, blah, blah. And that means since F of 0 is 0 prime, then F of I is AI prime. So that means they're multiplicatively related. And so now what Turner was interested in is back in the 50s, 1950s, 1960s, 1970s, Frank Harari used to keep a list of 10 unsolved enumeration questions in graph theory, and each time we'd solve the add to the list. And one of his problems was to enumerate the vertex transit graphs of order n. Well, Turner was interested in enumerating in this question, and his result now allows us to do a straightforward enumeration of the vertex transition graphs of order P. Now, the enumeration uses Polya's enumeration theorem, which I'm not going to cover, but here's the result. So the number of non-isomorphic vertex transit graphs of prime order P is, okay, it's 2 divided by P minus 1. And then that summation is over all the divisors of P minus 1 over 2. Remember, P minus 1 is even because P is an odd prime. And phi is the Euler-Toshin function. And the exponent there is just minus 1 divided by 2d. And so exercise 14 then is just use that theorem to determine the number of non-isomorphic vertex transit graphs of order 37. And you'll see nicely how it works, because 36 has a lot of divisors. You get to have a few terms there. So this was a very nice result that Turner obtained in this paper, and it sort of was one of the really enumeration results for vertex transitive graphs. Now, determining the actual automorphism group is of considerable interest as well, and so Burnside's theorem also allows us to do this for prime order. Okay, so if the graph is either the complete graph or the complement of the complete graph, then the automorphism group, of course, is the full symmetric group. So we're really interested in the other cases. So in the other cases, we know from Burnside's theorem that the automorphism group looks like a set of those TAB permutations, where A is running through a multiplicative subgroup, and B is running through all of the field. And so looking at that, that tells us we can determine exactly what the stabilizer of the vertex 0 is. The stabilizer of 0 clearly is all the permutations of the form TA0, because you can't have a constant there, because A0 is 0. So if you had a constant, you would not be mapping 0 to itself. So the stabilizer of 0 is all the permutations T sub A comma 0 as A runs through H. Well, if you now look at a given S in the connection set, the edge 0S, where is it mapped by TA0? Well, 0 gets mapped to 0, and S gets mapped to AS, which means AS is also in the connection set. And so if you have an element connection set, then you have A times that element as A runs through that group H. That tells us that S is a union of cosets of H. So given the connection set for a prime order circulant graph, let E of S denote the largest even order subgroup H of the multiplicative subgroup, such that S is a union of cosets of H. Now this is well defined because S is always a union of some next one, so E of S is determined. So then in 1973, I showed that this is how you get the automorphism group, that it's either the symmetric group or you get that it's TAB as A runs through E of S, where E of S is that largest multiplicative, even order multiplicative subgroup. Now, at the same time, Turner's paper appeared. In fact, Turner's paper was in the Journal of Combinatorial Theory. There was no Series B at that time. It was just a single journal. And in the same journal, either in that same issue or an issue just separated by one, Adam, Hungarian, conjectured that two circulant graphs are isomorphic if and only if you can find a unit in Zn. This is the ring of integers mod n because I want to allow multiplication. And that would be saying that Turner's kind of theorem works for all n. But in fact, it's easy to find a counterexample to this conjecture. So let's just look at one description of a counterexample. So let x and x prime be circular graphs of order 25, and the connection sets are going to look very much alike, but just a little bit different. So it's going to be plus and minus, and you see 1, 5, 6, 11, 16, 21. And the other one is going to be 1, 6, 10, blah, blah, 11, 16, 21. And so we've got plus and minus 5 in there, and in the other one we had plus and minus 10. So notice that 1, 6, 11, 16, and 21 are all congruent to 1 mod 5. So if you can find a unit that multiply s to give you s prime, then a would have to be congruent to plus or minus 1 mod 5 in order for a to preserve the main part of that connection set. But on the other hand, a would has to be congruent to plus or minus 2 mod 5 in order for a to take plus and minus 5 to plus and minus 10. And so there's no multiplier. And now, of course, 25 is a square, as a prime square. So you can see that involves. And another exercise now is, in fact, show that these two circular graphs are, in fact, isomorphic. So this makes it easy to construct counterexamples for any order divisible by a square other than n equal 4, 8, or 9, using the essential idea from that example with n equals 25. So in fact, this led to conjecture that Adam's conjecture held for square-free n. And after some impressive work, Muzichuk proved the following result over 2 papers. So circular graphs of order n, now 8, 9, and 18 are kind of exceptional ones. And then k, 2k, 4k, where k is not divisible by an odd square, that they're isomorphic if and only if there's a unit, a, and set n, that a times s is equal to s prime. It uses, his proof used Schur rings. It's complicated, long proof, but very nice work. Now, in fact, I'm a little surprised here because this is where I was planning to quit this first talk, because it's about halfway through the slides I prepared, and hopefully I haven't gone over this too quickly, because I thought it would take a little longer. So I'm going to stop there, and I guess let me. So that's it for me for today, and I guess what we do questions now, if there are any questions.
Yeah, so if the participants are having any questions, they can switch on their mic and ask it to the speaker.
Or you may write it on the chat box as well.
Whoops.
Meanwhile, I have one question. You talked about that Savidusi's theorem that graph is a Kelly graph if and only if it is having a regular subgroup. I mean, within the automorphic group. So instead of having a regular subgroup, if we have a subset which is acting regularly, so then obviously it will not be a Kelly graph. I mean, but can we say something about that?
If you have a subset of the automorphism group?
Which, yes, exactly, which is acting regularly on the graph.
Well, but then if it's acting regularly, it is a subgroup.
No, I mean, what I want to mean is that, I mean, that thing that is in that subset, for every pair of vertex, you can find exactly one automorphism which takes the first vertex to the next one. That's what I mean.
Well, I have to think about it for a minute, but I suspect we could prove that, in fact, it forces it to be a regular subgroup.
Okay. I mean, I was wondering that, I mean, will it always be a subgroup? So, for example, if we take some, I mean, coset of that, subgroup, even for a Kelly graph, instead of taking that regular subgroup itself, if we take a coset of that subgroup, that will also be acting, I mean, means for every element in that particular left coset, you'll be finding a unique automorphism. I mean, so, but that subset, I mean, that left coset is not a subgroup. It's just a subset.
Yeah, I'm not quite sure because the yeah. So what you want to say is you've got the vertex set, and now you can find for a given vertex, you can find a unique. No, not necessarily unique.
Yeah, it's uniqueness. I mean, given any two vertex.
So you want
any two vertex, we can find that.
You want to find a set of. Let's suppose the graph has order n.
Yes.
And now you want to find n permutations with the property that there's a unique, for each pair of vertices, there's a unique one that maps that one of the vertex to one of the others.
Exactly.
Well, off the top of my head, I can't.
Okay.
Yeah. Sure, think about it after I leave here.
Okay. So if anyone else has any other questions?
I have a small question. So, for the circulant graphs with order prime, you gave some characterization when two circulant graphs are isomorphic, right? So, what if the order is not prime? Then can we have some kind of these kind of characterizations?
Prime?
Could you please repeat your question once again?
So, for circulant graphs with prime order, you said that two circulant graphs are isomorphic if this one of the S is A times some other S prime. You gave some condition like this. So, if the circulant graphs are not with order prime, it is some other order, then can we give some kind of classifications when these two circulant graphs are isomorphic or not?
For arbitrary order?
Yes, for arbitrary order.
Well, there's Muzychuk's result, which applies to those orders I mentioned. And I mean, essentially, what Muzychuk's theorem is saying is that if n is if n is not divisible by a square, or n is not divisible by an odd square, then they're isomorphic if and only if you can find a multiplier that relates the two connection sets. But if you start getting to prime powers, you can't say much of it, because then once you start taking what are called Reith products of graphs, you can start having all kinds of isomorphisms between them.
Okay.
So I mean, Muzychuk's result is sort of the nicest result that's around for isomorphism of circulants.
Okay. Thank you.
So is there any further question? Then you please unmute yourself and ask the question. So if there is no such question, then I think we can stop it here. Angsuman, can you find any further question?
Can I just
find any other question in the chat box as well? Maybe as because we'll be having one
can I
more
just add one comment here?
Yes.
Because tomorrow I'll be talking about, there's a generalization of this circular result to what are called CI groups and CI graphs and so on. And that's closely related to that. So that might be a better answer for the question she asked a few minutes ago, because I'll be talking about CI groups and CI graphs tomorrow.
Okay.
Thank you.
So maybe we'll be having, we are going to have one more lecture of Professor Algebraic tomorrow. So in case if you have any other questions, you can ask tomorrow also. So as we are not having any more questions now, I think we can thank the speaker for this lecture. Thank you, Professor Algebraic. I think it's quite late for you now.
See you tomorrow.
Yeah.
Yeah, for all the remaining participants, now I am sharing you the attendance sheet for you, those who require certificate for that. So it's already there in your chat box. It's at 1:28 p.m. So with the timestamp of 1:28 p.m., so the form for attendance sheet is already there with you. So those who are interested to fill it up, are requested to fill it up. We'll again share the same link during the next session and all. So all the participants are requested to fill it up. So tomorrow there will be another link for another attendance sheet. So thank you. Now it's over to Angsuman.
Yes. So as we are now already half an hour early, so I think we can start the contributed talk session. In that case, the speakers may get some additional time to present. So earlier it was that the speakers will be having, the contributed talk speakers will be having 15 minutes. So I think there are 7 more speakers in this particular session. So maybe they can be allowed, say 37, so 20 minutes per head now. So can is Professor Shomik Ghosh here?
Yes, I am here. But the point is that suppose somebody is following the schedule.
Yes.
He or she wishes to hear some lecture. So the preponing the meeting, is it possible or right or not? I don't know. But as an organizer, you can decide it. I have no problem to start with.
So I think it's better not to start now, but what we can check is that the connectivity and all for all individual speakers, they can just share their slides so that we can start in due time and at the proper time without any delay. So I think it's better to start at time, because as Professor Ghosh already mentioned that many of the speakers or audience may target some specific talk. Yeah. So
yeah, I understand that. I understand that. But may I ask the speakers of
Angsuman, you can ask that the 7 speakers that whether they are here, and as Professor Odhikari is saying that they can check this connectivity and all these things.
Yeah, so are the speakers there? You can unmute yourself and just say that you are here.
Barkha, first speaker is Barkha.
Barkha,
Are you here? Next speaker is Ganesh S. Kadu.
Are you here? Okay, next speaker. Oh yeah. So you can just check whether your slides are working or not. You can just share your screen and just check.
So I think Barkha is already there. Barkha first.
Yes, sir.
Yeah. Could you please share your slides and all?
Yes.
Yes.
So
It
great.
is
It's,
visible.
Perfect.
Yeah. Who is the next speaker? Professor Ghosh?
Next is Ganesh S. Kadu.
Yeah, I think he is also here.
Yeah.
So, Ganesh Kadu, can you please share your screen?
Yeah. I'm not able to share my screen actually.
Yes.
I'm not able to present.
Okay, so you are having problem in presenting the screen.
Yes.
Yeah, so you can find on the right bottom corner, there is an option called
No.
present now.
First check. First, try to check from which device he is in. Are you presenting from mobile or your laptop or desktop?
That desktop. I'm presenting from my desktop.
Okay. Then on the screen, if you just put the mouse on the screen, then you will find that some pop-up will come up and go to the present now button.
Right bottom corner.
Yeah, I can see this present now button. But when I try to do this.
No, on the present now, when you put on the present now button, then you will find a box will appear and click on the box. Unless you click on the box, it won't do. So please click on the box.
Right. Yeah, but I don't see that box. What I'm seeing right now is can't share your screen. You must have permission in order to share your screen.
Okay, so you are doing from which browser? You are doing from which browser?
Mozilla.
Can you please tell? Mozilla. So could you please install by the time? No, sometimes it's difficult for Mozilla to share your screen. So please install Google Chrome. Please do it from Google Chrome. I think that will be fine. Okay, please, please use Google Chrome. That will be easier. Okay,
May we have the next speaker? Who is that? Okay, let me check.
SN Mira is the next speaker.
Good answer. Yeah, I'm here.
Okay, so can you share your screen?
Yes, sir. Can you see my presentation?
Not yet. Not yet.
Well, first you
need to first present now.
Actually, I am presenting now.
But not yet.
No. I mean, okay, which browser you are using?
Chrome.
Chrome. Okay. So on the browser, on the Google Meet window, if you see, you will be finding a present now option on the right bottom corner.
Yeah, I clicked that button
click it,
and
what do you-
share my.
Yeah, so
I shared
there-
my screen.
Yeah,
No, there you need to click it. I mean, you need to share your entire screen.
Maybe you have to pin on the presentation. You see that you have two, in the list you can see that there are two names
Okay,
against
okay,
you.
okay, okay.
One is presentation
Okay.
and other is yourself. You please.
No.
No, I think your screen is not yet selected. That's why. So one thing, could you please, madam, do one thing? You just go to sign it out and then sign in again. Then I think the problem will be resolved.
Oh, okay, 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 sir. Okay, sir.
So we can ask for the next VC Amrita. VC Amrita.
But Ganesh Kadu is trying to say something.
Okay.
Yeah.
Yes.
Yeah. Can I try with my Google Chrome?
Yes, try,
Yeah,
try.
please.
Yeah, now your screen we can see. Now you just open your slide.
Yeah. Wait.
Make it full screen.
Yeah.
Yes,
Is it?
it's fine. It's fine.
Okay. Thanks.
It's fine. Yeah, it's
Yeah,
perfect.
thanks. Yeah.
Okay.
Great.
Okay. Next, you can now stop sharing your screen.
Sure.
Yeah, next speaker is VC Amrita.
Sir,
Can you share your screen? VC Amrita.
sir. Sir, I'm Meera.
Yeah.
Okay.
Can I check? Can I check now?
Yeah, please.
Yeah, check. Please
Yes,
check.
you can check.
Yes, your
No.
presenting is coming.
Oh,
Yeah.
no. It's Amrita is presenting now.
And okay, sir. Okay.
Okay.
Amrita is presenting. Yeah, it's fine. Amrita, it's fine. Now, Miss Meera.
Sir?
Yeah, please try. Yes,
Okay.
please try to share your screen.
Okay, sir.
Now it's coming. Yeah.
Yeah, now you just
Okay.
you just need to make your slide full screen.
Is it okay?
Yeah.
Yeah.
Is it full
So
screen
you need
mode
to
or
make
it's in a
screen.
presentation, not in a presentation mode? I think it's not in a presentation mode. Can you go to the next slide, please?
Yeah. Okay, but it is readable.
Yeah.
Okay, sir. Okay, sir.
Okay, you can stop sharing for the time being.
Okay, sir.
Now you can call Amrita.
Amrita has checked.
Amrita check. Yeah.
Okay. Then Sandeep Dalal.
Okay, Sandeep Dalal, are you there? Sandeep Dalal.
Yes, sir. Yes. I'm Sandeep Dalal.
Okay, can you just try sharing your screen?
Sure, sir. Maybe. It visible, sir?
Yeah, it is.
Fine.
It's fine.
Okay, please stop sharing.
Okay.
Next, Rajat Kanti Nath. Rajat Kanti Nath.
Are you there?
Mr. Rajat Kanti Nath, are you there? So the next is Shubh N. Singh.
Shubh Narayan Singh. Shubh Narayan Singh, are you there?
Subnarayan Singh is not in the list. He is not here.
Okay, Sandip Dalal is there. He has checked, right?
Yeah. Rajat Kanti Nath. Only Rajat Kanti Nath and Subnarayan Singh. Rajat Kanti Nath I am checking. No, Rajat Kanti Nath also is not in the present list.
Okay, maybe they will join in time. That may also happen.
Okay.
So I think we can take a 20 or 15 minutes break.
No, maybe for the next session, if somebody is there, like Hiranno Kishore Dey is there, we can check their screen also.
Okay, Hiranno,
Are you there?
Hiranno?
Hiranno Kishore.
Yes, sir.
Okay,
So can you share your sharing the screen?
Yeah. So should I share my screen now?
Yes.
Yeah.
जितेंद्र सर यही क्या
So is it okay?
Yeah,
Can you
just make it a presentation mode.
Yeah, it's fine.
Yeah. Okay, fine. And now, is Pankaj Kalita is there?
Yes, sir, I am here.
Okay, please, could you please share your screen?
Yes, sir, sure.
Hiranno,
Sir,
please stop.
Hiranno, please, turn off your
Yes.
sharing the screen.
Stop.
Pankaj Kalita, now you can try.
Hello, sir.
Yeah.
It's coming. Yeah, it's coming. Could you please go to the next slide, please? Just.
Is it working, sir?
Yeah,
It
fine.
is good.
Thank you. Is Mr. Gopinath Shah is there? Mr. Gopinath Shah? Okay, maybe he is not here. Is Shanchita Pal is here? Shanchita Pal? Okay, I think they are not here now.
Yes, Runchita Pal is present here, I am seeing.
Okay,
Sir.
Shanchita Pal? Yeah.
Yes, sir.
Yeah, could you please present
Try
your screen?
sharing your screen.
Yes.
Sir. Hello, sir. I'm present. Gopinath Sahu. Maybe after this.
Yeah, after this, please. Yeah, sure.
Sir, is it visible?
Yes, your screen is visible, but you need to make it full screen.
Okay.
Yeah, please go to the next slide, please.
So you just go to that option. View there. View.
Okay.
The full screen mode is there. Full screen mode.
Yes.
Yeah.
Yes.
Now it's fine. Now it's
okay.
Okay.
Thank you. And Gopinath?
Yes, sir.
Yeah, could you please?
Yeah.
Please stop sharing.
Okay. Yes.
Okay.
Go.
have stopped sharing again.
Yes, actually, I was sharing the entire screen. Is it all right to share the entire screen?
Yeah.
It's okay. Just open your presentation and then share the screen. That would be easier.
Okay. Is it visible, sir?
Make it full screen. Yeah.
It's fine. Okay. Thank you all. So
maybe we can take a 10 minutes break.
Yes, we can take a 10 minutes break and
I think Rajat Nath is there. Rajat Nath?
Yes, hello.
Yeah, can you please try sharing your screen?
Can you please share your screen so that we can test whether your presentation is coming properly or not?
Your entire screen should be there.
Yes.
Is it shared?
Not yet.
So I need to click on the present now.
Yes, and then a box will appear. You have to click on the box and then OK.
And there are 3 boxes are there.
Enter screen. Yeah, enter screen.
Then something else comes. Share your entire screen.
Then yes, you need to click on the box itself. Unless you click on the box, OK won't appear.
Okay.
Yes, now it's appearing. Yeah.
Now it's appearing, huh?
Yeah.
And after that, how to get my slides?
You have your slides on the screen, right? You have already opened your slide. Yes, just click on the slide.
Mm-hmm. Okay.
And make it a... Yeah, it's visible, but you need to make it in a presentation mode. Just... Yes, perfect. Yeah, it's exactly. Okay, fine. Thank you.
Okay, thank you, sir.
Yeah. And only one thing we left.
The person left that Shubhen Singh. Shubnaran Singh is only left, but he is not in the list now.
Okay, then maybe he may join us in time, maybe.
Okay. Yeah. Should I stop sharing?
Yeah, please stop sharing. Yeah.
Thank you.
So maybe we will take a small break and we may join us again at 3 or little earlier than 3 so that we can start in time.
As Angsuman did not give any lunch break, so...
Yes. So not 3, actually 2. Yeah. So now virtual lunch break.
Yeah, virtual lunch break for 10 minutes only. I think it is only for 10 minutes.
Maybe 7 minutes. It's already 13:50. Yeah. So, okay.
So keep with us in 5 to 6 minutes and we will start the next session. That is a contributory talk session. And Barkha, please ready with your slides and all these things open so that we can start in the time.
Okay, can I request Dr. Ramij Raman to formally introduce our chair for this session?
Yeah, I am here. So, shall I start right now or wait 2 minutes?
Okay, maybe 2 minutes you can take.
Professor Shtomi Ghosh to chair today's first contributed talk session. Over to Professor Ghosh.
Thank you, Professor Ramit. Very good afternoon, everybody. So we start our first day contributed talk session. There are 7 speakers here, and each speaker will take 10 to 12 minutes and 3 to 4 minutes for discussion. And the whole thing should be done within 15 minutes. I think everybody will cooperate with this so that we can finish in good time according to our schedule. So, and in this occasion, I very much thankful for Professor Angsuman Das and Professor also Abhishek Adhikari here. And I really congratulate Professor Angsuman Das for organizing this great webinar from Presidency University, Kolkata, and especially on this topic, algebraic graph theory. As I can remember, I have also started studying graph theory with the algebraic graph theory. So it is my pleasure to come here and be a part of this international conference on algebraic graph theory and applications. And I really congratulated Professor Angsuman Das for this. So may I now invite Barkha to present your paper entitled On the Inclusion Ideal Graph of Semigroups.
Thank you, sir. Good afternoon, everyone. First of all, I would like to thank the convener of the conference for giving us an opportunity to present at the International Conference on Algebraic Graph Theory and Application. Myself, Farka, and the topic of my presentation is on the inclusion ideal graph of semigroups. The paper is about numerous remarkable results concerning the construction of graphs arising from rings, groups, or semigroups. In this, we consider the inclusion ideal graphs on semigroups. We consider vertex set to be ideals, left ideals. That's the outline of my presentation. First, some basics of semigroup theory, then followed by the results obtained on inclusion ideal graph, And then some important references. Introduction. Semigroup. Semigroup is a non-empty set together with an associative binary operation. Next, in some examples of semigroups, as we know that permutation group is an important class of group in group theory. Similarly, the same role played in semigroup theory by full transformation semigroup. It is the set of all mappings on a non-empty set X. It forms a semigroup under the composition of mappings. Its importance in semigroup theory can be realized as every semigroup can be every semigroup is isomorphic to some transformation semigroup. Next, the important class of semigroup is Rees matrix semigroup. Every completely simple semigroup can be constructed in this way. Here, I and lambda are indexed family, and G is a group associated with 0 element. Here, P is a matrix whose is a quantity of gamma cross quantity of I matrix. Its attributes are coming from a group G associated with 0, and this matrix is regular in the sense that no row and column of P consist entirely of zeros. This forms a semigroup under this binary operation. Here, if lambda group entry of P is 0, then it will become 0, and if this is non-zero, then it is non-zero. Here, 0 is the 0 element of this semigroup. If we take gamma and I to be equal, then it is called Brand semigroup. If this I is finite, that it is equals to n, then we denote it by B and G. For the trivial group G, it is equals to Bn. Next, we as Akbari introduced the inclusion ideal graph on ring. He studied the graph theoretic parameters like connectedness, diameter, width, perfectness of inclusion ideal graph. Subspace inclusion graph of a vector space is studied by A. Das. Motivated by the work of these two, we consider the inclusion ideal graph, since ideals give a lot of information about the algebraic structure. So in this, we consider inclusion graph, which is undirected simple graph, which vertex set is the set of all non-trivial left ideals, and two distinct left ideals are adjacent if and only if one is containing other. Like some examples of inclusion graph. The inclusion graph of monogenic semigroup. It is a commutative semigroup, so left ideal and right ideal coincide. Here 6 is indexed and 3 is period, so it forms a complete graph on 5 vertices. The inclusion graph for Tx for x equals to 1, 2 is a path graph of length 2. Here I1 and I2 are constant maps with image set 1 and 2 respectively. As you can see that I12 is union of I1 and I2. In semigroup theory, union of two left ideals is again a left ideal. Next example of Brand semigroup for B3 for n equals to 3. It is a bipartite graph on 6 vertices. Since Brand semigroup is a simple semigroup, it does not have both sided ideal. These are all only left ideals, and in fact these I1, I2 and I3 are minimum left ideals. Now some results obtained on inclusion graph. Now this graph, first we need to discuss about the connectedness of this graph. The INS is disconnected if and only if it contains at least two minimal left ideals, means it contains at least two non-trivial left ideals, and every non-trivial left ideal of S is minimal as well as maximal. Next is the consequence of this theorem. If this graph is disconnected, then it will become a null graph, that is, it has no edge. Next, if by the first theorem, we can see that if this graph is disconnected, then it is the union of exactly two minimal left ideals. Now, if this graph is connected, then its diameter will be at most 3. And in the rest of this presentation, we take non-trivial left ideal I of I1, I2, and so on Ik be union of these k minimal left ideal. Here I1, I of I2, and so on Ik are minimal left ideals of S. For S to be union of n minimal left ideas, the diameter of this graph is equals to 3 if and only if it has at least 3 minimal left ideas. For 2 minimal left ideas, this graph becomes disconnected. So next we discuss about the perfectness of this graph. If this semigroup has a finite number of left ideals, then its clique number and chromatic number are equal for every these subgraphs of S. If this I of I1, I2, In means union of n minimal left ideal is a maximal left ideal, then its clique number will be equals to number of minimal left ideals. Here n is the number of minimal left ideals. Next we obtain the girth of this graph. Its girth means the smallest cycle belongs to the set 3, 6, infinity. And this graph is planar if it has number of minimal left ideal. If graph is planar, the number of minimal left ideal is less than or equals to 4. And if semigroup is a union of n minimal left ideal, then this is planar graph if and only if n is less than equals to 4. Means it has number of minimal left ideal is at most 4. Next, we consider this graph on completely simple semigroup. Semigroup which is simple means which does not have any proper ideals, both sided ideals, and contains a primitive idempotent. By primitive idempotent, we mean an idempotent which is minimal within the set of all idempotents under this partial relation. This if E and F be are idempotent elements, then E dot F equals to F dot E equals to E. Now this graph on here we considering as to be completely simple semigroup with n minimal left ideal, then its graph order of this graph is 2 to the power n minus 2. If this graph, if S be n minimal left ideal, be union of n minimal left ideal, and since here S is completely simple semigroup and it is simple, so if S has n minimal left ideal, then it is equals to union of n minimal left ideals, and every non-trivial left ideal will be of union of these minimal left ideals. So every non-trivial left ideal of union of, for example, K be K union of n minimal left ideals, then its degree will be 2 to the power K minus 2 plus 2 to the power n minus K minus 2. And its independence number will be n choose P, where P is, if n is odd, then n equals to 2P, or n for even n equals to 2P and odd for n equals to 2P plus 1, then its independence number will be n choose P. If it, in fact, it has a perfect matching, means its matching number will be 2 to the power n minus 1 minus 1. Next, we obtain the automorphism group for inclusion ideal graph for a completely simple semigroup. If it has at least 3 minimal left ideals, then automorphism group will be isomorphic to Sn cross Z2. If we take if semigroup has 2 minimal left ideals, then it will be null graph. So its automorphism, trivially its automorphism group is isomorphic to S2. As the some references. Thank you.
Thank you very much, Partha, to finish exactly in the time. Now I ask the audience, if you have any question, please.
Can I ask?
Yes.
Yes.
One result you mentioned that the inclusion graph is perfect, but this inclusion graph is essentially the comparability graph of the coset of sub-semi groups, and it is already known that from Galai's result that comparability graphs are perfect graphs.
Yes, sir.
Yeah. So from that result it follows, and some of the coset theoretic techniques you can use to get a few more results in that direction, because you can play with it.
Okay, sir.
Yeah.
Are there any question, please?
Yeah. Can I ask a question?
Yes.
Yeah. Barka, it is Manideepa here. In last some results, we have used the condition that it is a completely simple
Semigroup, right?
Yeah. What is a completely simple semigroup? Can you explain? And why this condition is necessary for this method?
In semigroup theory, completely simple semigroup is an important class of semigroups. Completely simple means if it is simple. Simple means it does not have any proper both-sided ideals. And it has a primitive idempotent. Primitive idempotent, we mean it is minimal within the set of all non-zero idempotents. Because 0 is an idempotent, it is minimal in if S is union, if S is associated with 0 element. So here we consider idempotent to be minimal within the set of all non-zero idempotents. Means if E is less than equals to F, means E dot F equals to F dot E, this is equals to E.
Why this condition is necessary?
Which condition?
This completely semi-simple, yes, for your result.
We study the inclusion item on completely simple semigroup.
Okay, if we consider just a semi-simple, any semigroup arbitrary, so whether we are able to find the independence number. So,
actually, I have found independence number on this on completely simple semigroup. Yeah, either S is union of n minimal left ideals. In general, I have not find out.
Any more question? So we can thank you, Barkha, for nice presentation. And so I can call the next speaker, Ganesh S. Kadu, to present the paper entitled On the Problem of Finiteness of the Clique Number of Compressed Zero Divisor Graphs of Artinian Rings. Ganesh S. Kadu, please.
Yeah, thank you, Professor Ghosh. So are my slides visible?
Yeah, it is visible. You can go on.
Yeah. To begin with, let me thank the organizers for giving the opportunity to speak here. The title of my talk is on the problem of finiteness of Clique number of compressed zero divisor graphs. So to begin with, let me give you some motivation. So we start with a commutative ring with unity. Area of zero divisor graphs really began with experimental paper of Beck, who associated to a ring a simple graph with vertex set consisting of all elements of the ring, and you join the two vertices if their product is zero. A dot B is A and B are vertices, and then you join A with B if A dot B is zero. Okay. Then later on, this definition was modified by Anderson and Wilson to include only non-zero divisors of R. Note that if R is integral domain, then you will not have any non-zero divisors. So this graph will be empty. But if the ring has zero divisors, then this will be a non-empty graph, and its vertex set will consist of all non-zero divisors, and you join two vertices phi and h if their product is zero. So this graph we will be denoting this graph by gamma of R. And then starting with Beck and followed by Anderson, there is such class of graphs. So this gives you an interesting class of graphs, and this offers a rich interplay between ring theoretic properties of R and the graph theoretic properties of the associated graph gamma of R. For instance, we can check that was proved by Beck, and later on this was modified by Anderson. Peak number of this graph equals the number of associated terms of
May I request you to speak louder because your voice is becomes low sometimes.
Sure. It was proved by Beck, and then later on it was modified by Anderson. that this zero divisor graph, the clique number of this graph is equal to the number of associated points of R. So this kind of gives you a first connection between the ring theoretic properties of the ring R and the graph theoretic properties like clique number, for example, or chromatic number. In fact, starting with the paper of Dick and later on followed by papers of Anderson and Lagrange, they studied the clique number and the chromatic number of this graph. So it turns out that for a large class of rings, which includes reduced rings, these are basically the rings with no non-zero important elements and the principal ideal rings. It turns out that the chromatic number is equal to the clique number. And this in fact was the motivation for Bake's initial paper. What we do in this talk is we look at the compressed zero divisor graph, which is in some sense a simplified version of the zero divisor graph. So this was introduced by Boole in this paper, the graph. So this graph is obtained from gamma of R, and what you do is you identify two vertices. So let's say A and B are two vertices, and then you identify them, you put them in one equivalence class if analyzer A equals to analyzer of B. Where analyzer A means all those elements which kill A. Okay. So if analyzer A equals to analyzer B, then you identify these two elements, you put them in one equivalence class. So the vertex set of this graph is basically the set of equivalence classes. And again, as before, you join two equivalence classes, two elements. If the product is 0, one can check that this definition is independent of choice of representatives of equivalence classes. So you get a graph, and what you are doing essentially here is you are identifying two vertices having the same neighborhoods in gamma of R. You have the usual zero divisor graph, and suppose you have two vertices having the same neighborhood, then you essentially identify them, treat them as same in the compressed graph. So what you obtain essentially is a simplified version or compressed version of the zero divisor graph. Now, what we have here is a map, a graph map, in fact, from the vertex set of gamma of R, which is equal to zero divisor graph, and the compressed graph. You take A and map it to equivalence class determined by A. And this has the property that if A and B are adjacent in gamma of R, then psi of A will be adjacent to psi of B, or they may be equal also. And then it is interesting problem to study properties of gamma R from the properties of the compressed graph. Interesting questions here. For instance, automorphism group of gamma of R can be determined from the automorphism group of the compressed zero divisor graph. This was the content of Boole's paper on cycles and symmetries, 2007. So therefore, it is often helpful to look at this more simplified compressed graph rather than the usual gamma of R. Okay. Now, I need this notation, length of R. Length of R will denote the largest length of any of its chain of ideals. Okay. And we will, from now on, we will assume that R is Archimedean, that it has a finite length. So all chains of lengths, the chains of ideals in this ring will be finite chains. The question of when the clique number of this compressed graph is finite was posed by Coit and Dahl and others. Survey paper titled On Zero Divisor Graphs in Progress in Commutative Algebra. This was in 2012. And they proved the following theorem. If length of R is less equal to 3, then the compressed graph is finite, and so the clique number is finite. If the length is 4, then the clique number is finite again, although the graph can be infinite, the compressed graph can be infinite. And then in the length 6 case, they gave an example of a ring where the click number is finite. And this ring is Artinian because its length is fixed. So Artinian rings are rings with finite length. And then the question of what happens in length 5 was stated as an open question by the authors in 2012. So the question is, length R is 5, then its click number of the complex graph finite. And we proved that if R is a ring with length 5, then the click number is in fact finite. So this also shows in particular that the example given by Koindall and others of length 6 Artinian ring where the click number is infinite is indeed a minimal one. Found this ring with the infinite click, and in the length 6 case, but in length 5 it was not known. We proved that it is in fact finite. So this example is of minimal one. And the proof of this result is rather long, so I just want to mention two ingredients that go into proving this theorem. So one uses the orthogonal geometry of bilinear spaces, and some commutative algebra is also used. And I'm going to indicate proof in one important case, namely that R is a local ring of length 5 with n square of principal ideal. So let me give you a sketch of proof. So first of all, the problem is we first reduce the problem to the case of a local ring. We assume that the ring is local, and in the non-local case, we use this Artinian metaphor composition where you write arbitrary Artinian ring as direct product of Artinian local rings. From there, you can go to more general result. So one focuses on the local ring first, and in this case, we look at Hilbert function in the length 5 case. In fact, you can. So let me first recall what is Hilbert function. It's a numerical function where you take integer I, and then you map it to the dimension of m power I modulo m power I plus 1. This m is the unique maximal ideal in the local ring R. M power I is also an ideal. Then n power I modulo n power I plus 1 is a quotient ring. This in fact is a vector space over R mod n. R mod n is a field. It's called residue. So this dimension, so I going to this dimension, it gives you a numerical function. This is called Hilbert function. And the length 5 case, these are the 4 possibilities for the Hilbert function. And so for instance, the first case is really the case of principal ideal local ring, which is very easy to deal with. The most interesting case is the case 2, where HR0 is basically 1, HR1 is 3, which means it has maximal ideal has 3 minimal generators, and HR2 is 1, which means m square is principal. So this is the case which is most interesting and most difficult to deal with, and one understands the proof in this case, the other cases can be dealt with simpler. So what one does in this case is one defines a bilinear form on the vector space n mod x square. So as we noted earlier, n mod m square is a vector space. In fact, n power I modulo n power I plus 1 is a vector space. So this is a vector space, and we define a bilinear form, appropriate bilinear form on this vector space. And interestingly, it turns out that this bilinear form has this property that phi of a bar is 0, and ab is 0. So you can relate the structure of zero divisors in the ring R with the bilinear with the orthogonality of bilinear form. So here you say that a bar and b bar are orthogonal vectors. And then you can also identify socle. Socle is basically the set of elements which are filled by the maximal ideal. You can also relate the socle, and you can in fact compute the socle from the degeneration space of the bilinear form. Alright. So let me explain the proof in the second case where m squared is principal. So basic idea is to take a vertex in the complex graph and map it to vector A bar. So this class equivalence class square A is going to
Try to finish in 2 minutes, please.
sure. So map it to A bar, and then it turns out that if the vertices are adjacent in gamma ER, then the corresponding vectors are orthogonal in mod x square. Okay, and the question is, if suppose you have a clique of large size in gamma ER, then that is going to be a clique. Then that is going to be a set of orthogonal vectors in M mod x square. And then our basic idea is to say that if you have a large clique in gamma ER, the complex graph, then that gives you a large set of orthogonal vectors. And then one says that you cannot have large number of orthogonal sets in a vector space of a fixed dimension. And so here we use orthogonal geometry of non-degenerate symmetry bilinear form on the vector space in mod x squared. And in the case when phi is degenerate on M mod m squared, we go modulo the degeneration space or the null space, and then setting again, we prove that this vector space cannot have orthogonal set of large continuity, and this will eventually force the ring up to have a clique. So that finishes the proof in the local case. And in the non-local case, like pointed out in the beginning, write R as direct sum of Artinian local rings, and then one knows that the clique number of this ring R compressed graph, this is finite if and only if the individual clique numbers of Ri's are finite. And since length of R is 5, the length of individual Ri's will also be 5 or less than 5, like the non-local case. And then we've already shown that in the length less than or equal to 5, the clique numbers are finite. Therefore, the clique number of the compressed graph associated to R is also finite. So this will finish the non-local case. I want to thank my colleague Vinayak Joshi for the discussions, and also thank EST sir for the financial assistance and the project under this scheme here. These are the references. The original paper by Beck, Coloring of Computative Things, and this is the third paper here, published in Progress in Commutative Algebra. This is where this question was posed. Thank you.
Thank you very much, Mr. Ganesh. I am asking the audience very quick if you have any question, because the time actually is taken by the speaker. But however, you can just put one or two quick questions.
Can I ask one question?
Sure.
Ganesh, thank you for this wonderful talk. I just wanted to ask something. In this main result, is there any characteristic restriction do you need on the ring, or any characteristic?
No characteristic. So initially,
all characteristic it will be.
Yeah, initially I needed characteristic not equal to 2, but then later on I was...
Okay. Yeah, because I was wondering this orthogonal geometry perhaps, so it's not creating any problem, right?
No, it initially created, but then I was able to fix that problem.
Okay, yeah. So that's really nice. Yeah, thanks.
So we pass to the next speaker, and Mr. Ganesh, please stop presenting. So I invite the next speaker, S.N. Mira, to present the paper entitled On the Genus of Nil Clean Graph of Commutative Ring. Please, Ms. S.N. Mira.
Yes, sir.
SN Mira, please start presentation.
Yes, sir.
Okay, it is coming. Thank you.
Okay.
Start.
I am SN Mira, research scholar. I'm doing research under the guidance of Dr. K. Sayakumar, MS University, Tirunelveli. Today, I'm going to present my paper on the genus of Nelson graph of a commutative ring.
Can you please speak a bit louder?
Oh, okay, sir. And this is my abstract. The nil-plane graph of a ring R, denoted by Gn of R, is a graph whose vertices are elements of R, and two distinct vertices are adjacent. X and Y are adjacent if and only if X plus Y is a nil-plane element. In this article, we classified all finite commutative rings whose nil-plane graph has genus at most 2, except for the ring R isomorphic to Fp cross Fq, that is product of two fields. And the contents are introduction, definition of the nil-plane graph, planarity of Gn of R, and the Gn of R of genus at most 2. First of all, I need to tell what is genus. A graph G is said to have genus G if it should be drawn without crossings in a sphere with G handles and not on G minus 1 handles. Let R be a finite commutative ring with non-zero identity, and we denote Fp and Z of R for the field with P elements and the set of all zero divisors of R respectively. In 1988, ICAGTA studied coloring of a graph of a finite commutative ring R, where vertices are elements of R and xy is an edge if and only if xy is equal to 0. Product of x and y is equal to 0. Later, many authors introduced different kind of graphs associated with rings. In 2017, D.K. Basnet et al. Introduced nil-plane graph Gn of R associated with girth, diameter, etc. have been studied, and nil-plane element is an element of a ring R if for which it's an addition of idempotent element and a nilpotent element. That is R is equal to n plus c. A nil-plane element, an element n is said to be a nil-plane element if it is if a power n is equal to 0 for some n, and also an element A is said to be an idempotent element of ring R if a power 2 is equal to a, and the set of all nil-plane element, set of all idempotent elements and nilpotent elements are denoted by idem of R and nil of R respectively. This is the definition. These are all my main theorems. Planarity of Gn of R. Let R kappa M be a finite local ring. Then Gn of R is planar if and only if R is isomorphic to one of the following rings: Z4, Z2 of x by ideal generated by x square, or R is a field. For Artinian non-local ring and R not isomorphic to Fp cross Fq, then Gn of R is not planar. For the local case, if Gn of R is non-planar, then genus of Gn of R is greater than or equal to 2. And for the non-local case, if Gn of R is non-planar, then Gn of R is greater than or equal to 2. Let R comma M be a finite local ring, then genus of Gn of R is equal to 2 if and only if R is isomorphic to one of the following rings: Z8, Z2 of x by x ideal generated by x cube, Z4 of x by ideal generated by 2x comma x square minus 2, Z2 of x by x comma y divided by ideal generated by x comma y the whole square, etc. up to Z3 of x by ideal generated by x square. Let R be a finite non-local Artinian ring, then G of Gn of R is equal to 2 if and only if R is isomorphic to one of the following rings: Z2 cross Z4, Z2 cross Z2 of X by either generated by X square, or Z2 cross Z2 plus Z2. These are all my theorems. These are my references. Thank you.
So thank you very much, Gorka, for your
Thank you, sir.
nice presentation. May I ask the audience that if there are questions, please ask.
Hello, I have a small question. As you have mentioned, G and R is planar and non-planar. What do you mean by planar or non-planar?
Okay. A graph is said to a graph if we can draw a graph without crossings, means it is a planar graph. With if any two edges are crossing, then it is said to be non-planar graph.
Okay. Okay. Thank you.
Any more question, please? So if there is no other question, we thank again
Thank you, sir.
the speaker, S.N. Meera, and I am asking the next speaker, V.C. Amrita, to present her paper entitled Planarity and Outer Planarity Indexes of Class of Graphs from Rings. Please, Srimati Amrita.
Good afternoon to all present here. Thanks for giving this opportunity. I am P.C. Amrita. I am doing research under the guidance of Dr. K. Salvatore. And the topic which we are going to discuss today is about planarity and outer planarity indexes of class of.
Can you speak louder, please?
Okay, sure. The topic which we are going to discuss today is about planarity and outer planarity indexes of class of graphs from rings. The abstract of this paper is to deal about the problem of planarity and outer planarity of the iterated line graphs of these following four graphs. The first graph is the Huntington ideal graph. The second one is the nil graph of ideals. The third one is the Cayley graph of ideals, and the final one is the Cayley sum graph of commutative rings. For all these graphs, what we are going to do is we are going to see the planarity index as well as the outer planarity index. Also, we have found the outer planar case for Huntington ideal graph. So these are the contents of my work. The first one is about the motivation of the work. The second one is about the introduction of the work, and the third one is about the planarity and outer planarity indexes of class of graphs. So let's see about the motivation of the graph. Graph drawing has become a lively area in computer science because of its almost all the applications, and in science and technology it has reached its limit. Many researchers have concentrated their attention on drawing planar graphs because of the following reasons. Let's see the reasons one by one. The first reason is drawing of planar graphs have no edge crossings and it looks nice. The second one is drawing of planar graphs have many practical applications in almost all the fields in routing as well as in VLSI floor planning. The final one is about the architectural floor planning, and when you consider in bioinformatics, in RNA structures, these graphs play a vital role. So while developing these algorithms, many beautiful properties of planar graphs have been discovered in which applications in solving problems on planar graphs rather than graph drawing problems. So the field of graph drawing has been very much interested in the last decade. Let's see about algebraic graph theory. Algebraic graph theory, as we all know, it is one of the most flourishing branches of modern algebra, and it has a wide applications in combinatorial problems. So associating a graph to an algebraic structure, it is a research subject in which many researchers have considerable attention regarding this field. The benefit of studying these graphs is that one may find so many results about the algebraic structures via graph theoretic structures and vice versa. In this paper, what we are going to see is about the iterated line graphs. The iterated line graphs has reached a good role in the coming years. The kth iterated line graph of a graph G is denoted by Lk of G, and these graphs are defined inductively as follows. The Lk of G is L to the power k of G is called the kth iterated line graph. L naught of G will be equal to G, and the line graph of L1 of G will be equal to L of G. This is called the line graph of G. And L to the power k of G is equal to L of L to the power k minus 1 of G. This is called the kth iterated line graph. The planarity index of the kth iterated line graph is defined as follows. It is defined as the smallest k such that Lk of G is non-planar. We denote the planarity index of the graph by psi of G. If Lk of G is planar for all k greater than or equal to 0, then we define the planarity or index of the graph to be infinity. Kepler proposed the study of planarity and outer planarity indexes of graphs. Here he gave a full characterization of graphs with respect to their planarity index. These are the results given by Kepler. If the graph is planar, if and only if its planarity index should be equal to 0. Its planarity index will be equal to infinity if and only if G is either a path or a cycle of k 1, 3, and these are the similar results which are given by Kepler. And these are the subgraphs which Kepler has given for planarity index. Next one is the outer planarity index. The outer planarity index of a graph is denoted by psi of G, which is zeta of G, which is the smallest integer k, such that the kth iterated line graph of G is non-outer planar. If L to the power k of G is outer planar for all k, then we define zeta of G, that is the outer planarity index, to be infinity. The first result is due to Huqi, Lin et al., which deals the full characterization of graphs with respect to the outer planarity index. This was the result given by them for outer planarity index. Outer planarity index will be 0 if and only if the graph is not outer planar, and these are the similar results for outer planarity indexes infinity 1 and 2 and 3. These are the forbidden graphs for outer planarity. The first graph which we are going to see is about the annihilating ideal graph. The concept of annihilating ideal graph was given by Berkeley and Reiki. How he defined annihilating ideal graph is he defined by the notation Ag of R as an undirected graph with vertex set as A star of R and two distinct vertices. If you want to give adjacency between I and J, Ij, when you product Ij, it should be equal to 0. Selvakuma et al. Characterized all Artinian non-local rings for which the annihilating ideal graph is planar. So using this planarity result, what we have found is we have found the planarity indexing of the annihilating ideal graph. These are the following results which we have obtained from the planar ring, and we have found the planarity index to be infinity if R is isomorphic to one of the following rings, and the planarity index will be equal to 1 if R is isomorphic to one of the following rings, which is shown here. And the planarity index will be 2 if R is isomorphic to one of the following rings, R1 cross R2, these are the nilpotency, M1, M2 are the only non-trivial ideals in the corresponding rings. And the planarity index will be 0 if these cases are not there. Next is about the outer planar of Ag of R. So outer planar means if you want to say a graph to be outer planar, it can be drawn in a plane without crossings in such a way that all the vertices belongs to the unbounded face of the drawing. If it belongs to the unbounded face of the drawing, you can say that the graph is outer planar. So let's see the outer planar result. The annihilating graph will be outer planar, that is Ag of R will be outer planar. non-trivial ideal J of R such that Ij is contained in nil of R. This was the definition given by Shaveshi. Later, Commissioner et al. Characterized all Artinian rings whose nil graph is planar. So using the planar rings, we characterize the planarity index of those rings. The third graph is about the Cayley graph of ideals of a commutative ring. The Cayley graph of ideal of a commutative ring is a simple graph. It has no loops, as well as it is an undirected graph with vertex at I of R, that is the set of all non-trivial ideals of the ring, and two ideals I and J are adjacent if either J should be equal to IL or I is equal to JL for some non-trivial ideal L of R. This was the definition given by Afkami. Later, we have defined the planarity index of the following rings. And this is the outer planarity index of the following rings. Zeta of I of R, that is the Cayley graph of R. And the final graph is about the Cayley sum graph of ideals. Afkami et al. Introduced the Cayley sum graph of ideals. He defined as follows. He considered R as a commutative ring, I of R the set of all ideals of the ring R, and is a subset of I star of R. The Cayley sum graph of ideals of a ring R is denoted by Cayley of I of R, S. It is a simple undirected graph with vertex set as the set of I of R, and for any two distinct vertices, I and J are adjacent if and only if when you add I plus K, it should be equal to J, or J plus K should be equal to I for some K in S. This was the definition given by Afkami. Later, the authors completely determine all commutative Artinian rings for which the Cayley graph is planar. Using the planar rings, we have calculated the planarity index to be these things. And this is zeta of Cayley graph, that is the outer planarity index of the following ring. These are the references which I have referred. Thanks for giving this opportunity.
Thank you very much for presenting such a nice paper. Now, may I ask the audience if you have any question, please ask.
Hello, I have a question. Are the outer planar and non-planar same things? Hello?
There is a question. Please respond. Srimati Amrita, please respond.
Should I repeat the question? Are the outer planar and non-planar same things?
No, they are not same thing. Srimati Amrita, please respond. Probably there is some audio connection problem of the speaker. I don't understand. She is not responding. I do not know whether she is hearing or not.
Okay.
So, in case the speaker is not available for answering, Amrita, are you available for answering the question? There might be some problem.
I think Professor Selva Kumar is there, so he can also answer.
Okay, then I please invite Professor Selva Kumar. Please, can you answer some question if there is any from audience?
Please repeat the question.
The question, please, madam.
Are the outer planar and non-planar the same things?
No, totally different. Every outer planar graph is planar, but a planar graph need not be outer planar.
Okay.
The outer planar graph is a graph that you can draw in a plane where every vertex is on the outer boundary, outer surface of the graph. So it is a special case of planar graph. It is completely, as Professor Selva Kumar said, opposite of non-planarity. It is rather more planar. Yes. What should I say?
Okay.
Thank you.
Any other question, please?
Yeah, I have a question.
Please.
um, is there any motivation behind the ideas of planarity index or outer planarity index?
Yes.
It's some kind of a iterative operation and then observing a phenomena. What may maybe the motivation or is there any other interpretation, any structural or from other viewpoints?
Professor Selvakumar, are you saying something on this?
In the beginning of presentation, some of the applications need the I will send some application to you. Please post your mail ID.
Yeah, okay, sure.
Okay, thank you.
Okay, so are there any questions from the audience? So thank you, Professor Selvakumar. Now we can pass to the next speaker, Mr. Shandip Dalal. I ask you to present your paper, a study of commuting graph on groups.
Yes, sir. I will take.
Please.
Is it visible, sir?
Yeah, it is okay. Please proceed.
Good afternoon to all of you, and I would like to thank to the convener of the of this conference who gave me an opportunity to present my works. The topic of my presentation is a study of commuting graph on groups. The investigation of graphs related to various algebraic construction very important because graphs of this type have valuable application and are related to combined automata theory. A motivation of this work is the Sagao et al. Used the combinatorial parameters of certain commuting graphs to establish long-standing conjectures in the theory of division algebras. So outlines of my presentations are the first one, introduction. I will introduce some basic definitions. After that, I will present some result which we have obtained in these lections and few references. First one is the commuting graph. It is the simple and undirected graph with the vertex at G and two distinct vertices are adjacent if they commute in the group G. And the results, first one is, in this result we have obtained the edge connectivity and the minimum degree and show that they are equal. Here T denotes the maximum size of the conjugacy classes of the elements in G. In the next result, we obtained the matching number which is equal to the ratio of these two numbers when the size of G is odd. On the other hand, if size of G is even and T is less than equal to the size of the center of the group, where T is the number of the elements of order 2 in the subset of non-central elements.
Excuse me, can you please define the commuting graph before the discussion so that everybody can understand?
This is the definition of the commuting graph. Commuting graph of a group G is the simple undirected graph whose vertex set is G, and if we take any two different vertices, they both are adjacent if X and Y arc x and y commute.
Okay, thank you.
This
Sorry.
is the definition of commuting graph. The next result. In the next result, we have obtained the edge covering number. Basically, this is the corollary of this theorem, because the sum of the edge covering number and matching number is the size of the vertex set of a graph, and this is the edge covering number. In the next result, a group is said to be an AC group if the centralizer of every non-central element is abelian. With the help of this result, we can check this group, finite group G is an AC group. If the commuting graph of G is isomorphic to the commuting graph of other AC group, then G is an AC group. Next is, we give an equivalent condition of a non-abelian group G and AC group if and only if interior of the commuting graph of G is equal to the center of the commuting graph of a group G. Next we consider the group G is the semi-diagonal group. Basically, it is generated by two elements. They satisfy these two properties. First, we obtain the neighborhood of each element. Neighborhood of an element is equal to the group if and only if X belongs to X is either identity element or the a power 2n. Similarly, these result is for even n. The neighborhood of an element is the cyclic subgroup generated by A if and only if X belongs to A, which is different from E and 2n. Similarly, we obtain the neighborhood of this element. Next result is for odd n. This is if X belongs to this set, then neighborhood of X is SD8n. Basically, this set is the center of the group. And similarly, we can obtain the neighborhood of X if X belongs to this set. Next is the structure of the commuting graph. By using these results, we obtain the structure of the commuting graph of semi-diagonal group. It is isomorphic to this graph when n is even, or it is isomorphic to this graph if n is odd. This symbol is the join of the two graphs, and this is the union of two graphs. Next, we prove that the automorphism of the commuting graph of semi-diagonal group, this is equal to this group when n is even. Here, this is the simple direct product of groups, and this symbol denotes the Rath product of a group. And it is isomorphic, it is equal to this group when n is odd. Here, S fixed denotes the symmetric group. Next, we obtain the some graph invariance of the commuting graph of semi-diagonal group. This is the strong metric dimension, and it is equal to 8n minus 2. Next is this is click number, which is equal to 4n. And by using the above results, we should center of the commuting graph of semi-diagonal group is equal to the interior of the semi-diagonal commuting graph of semi-diagonal group. Next, it is eccentric graph. Next, it is a closed graph, and it is not Eulerian because it contains n vertices of odd degree. Next, it is the edge connectivity of this graph is 3 when n is even, otherwise 7. Similar result for the vertex connectivity. Now we obtain the independence number of the commuting graph of semi-diagonal group. It is equal to n1 when n is even, to n plus 1 if n is even, otherwise n plus 1. And this is the matching number, which is equal to 4n. Next result, basically the corollary of this result, and this is the vertex covering number, which is equal to 7 if n is 1, and or 6n minus 1 if n is even, otherwise 7n minus 1. Next is the edge covering number, which is equal to 4n. Further results about the perfectness and the Hamiltonian. The commuting graph of SDA10 is perfect, and the commuting graph of SDA10 is Hamiltonian if and only if n is either 1 or 3. Now we move to the next result, which is the characteristic polynomial of the Laplacian matrix of the commuting graph of semi-diagonal group, which is equal to this one. By using this result, we obtain the Laplacian spectrum of the commuting graph of semi-diagonal group, which is equal to this. Basically, this is the Laplacian eigenvalues 0, 2, 4, 4, n and 8n. And these are the corresponding multiplicities of the Laplacian eigenvalues. By using this result, we obtain the number of spanning trees of the commuting graph of semi-diagonal group. These results for even n, and this number is the number of spanning trees of the delta S DA10. Similar result we obtain for odd n, and this is the characteristic polynomial of the commuting graph of semi-diagonal group. Next one is the Laplacian spectrum, and similarly these are the Laplacian eigenvalues and these are the multiplicities. Next is the number of spanning trees of the commuting graph of semi-diagonal, which is equal to this one. And these are my references. Thank you.
Thank you very much, Mr. Sandeep.
Thank you, sir.
May I ask the audience if you have any question, please you may ask.
I have one question.
Yes, sir.
I mean, what is the interior of a graph? What is the
interior of the graph? Yes, sir. Interior of the graph is the subgraph induced by the interior vertex.
And what is the interior vertex of a graph?
Yes, sir. A vertex V is said to be interior vertex for a vertex U, which is different from V. There exists a vertex W and a path UW such that V lies in that path at the distance from both U and W. This is the interior vertex for a vertex U. And if vertex U is said to be interior for a graph, for a given graph, if there exists a vertex V such that U is interior vertex for a vertex V.
Okay, thank you.
Any more questions? So we thank again Mr. Sandeep for nice lecture. And then I ask the next speaker, Mr. Rajat Kantinath, to present his paper entitled Spectrum and Energy of Non-Commuting Graphs of Finite Groups. Please, Mr. Rajat Kantinath.
Thank you, Professor Ghosh. Can you see my slides?
Yes,
Hello?
it is okay.
Okay.
Yes.
Okay. Thank you, Professor Ghosh. And I would like to thank the organizer, Professor Das, and all for giving me this opportunity to talk in this conference. So I'm going to talk about spectrum and energy of non-commutative graphs of finite groups. And all the results included in this talk are joint work with my student, Wala Hasbus. My previous speaker already said something about commuting graphs. But this is just opposite of complement of commuting graphs. So it is non-commuting graph, but there is a twist. I will tell what is the twist. And here we discuss spectral aspects of non-commuting graphs. Before going to the spectral aspects of non-commuting graphs of finite groups, let me talk about spectrum of a graph. So the spectrum of a graph is the set of all eigenvalues of the adjacency matrix with multiplicities. For example, if lambda 1, lambda 2, lambda n, these are the eigenvalues of the adjacency matrix with multiplicities k1, k2, kn, then we write in this fashion. Instead of writing two row, we write in this way. The power means the multiplicity of the eigenvalue. For example, here the lambda 1 to the power k means lambda 1 occurs k1 times, and similarly the others. So this is the spectrum of a graph, and Laplacian spectrum is the set of all eigenvalues of the Laplacian matrix with multiplicities, and Laplacian matrix is the degree matrix minus adjacency matrix. A graph G is called integral if a spectrum contains only integers. And here we have a general question in graph theory: which graphs are integral? People are studying which graphs are integral, and in general it is difficult to answer, and therefore people are restricting this question to some other small families of graphs. For example, it is asked that can we construct infinite families of integral complete algebraic graphs? So in this talk we will discuss this thing, and we attempt to answer this question by considering non-commuting graphs of finite groups. That is one aspect. And another aspect of this paper is we have something called energy and Laplacian energy. Energy is the sum of the absolute values of all the spectrums, and Laplacian energy is also some kind of sum, and it is given in equation number 1. So here E of G is and E of G are the set of edges and set of vertices of the graph. This energy was introduced by Goodman in the year 1978, and Laplacian energy was introduced by Goodman and Joe in the year 2006. And in 2009, Goodman and others proposed one conjecture that energy of a graph is less than equal to Laplacian energy. Soon after this conjecture, some people come and say that no, this conjecture is not correct. You can disprove this conjecture by providing some counter examples, and the counter examples are given in this paper 1 and paper 2. And we also attempt that can we have some counter example for this conjecture by considering non-commuting graphs of finite groups. So we take that problem, and finally we show that yes, we can give some graph, we give some group for which non-commuting graph is a counter example of this conjecture. So now I tell what is non-commuting graph. So for my case, I will take capital G to denote a non-abelian group, and ZG is the center of the group. For non-commuting graph, I will take the vertex set as G minus center. That means the non-central elements of G, because if we consider the central elements, then that will be always an isolated vertex. So to remove that part, we exclude the center from the vertex, and we take the vertex set as the non-central elements, and we say that two vertices are adjacent if and only if they don't contribute. So in the complement of this graph will be the commuting graph, and in our case we consider the commuting graph as same thing. The two vertices will adjacent if they commute, and the vertex set will be G minus J, non-central elements. This complement of this commuting graph was, that means the non-commuting graph, that is the commuting graph was introduced by Brouwer and Fowler in 1955, and the non-commuting graph was initiated by the work of Erdos and Turan in the year 1976. So studying the spectral aspects of commuting graphs and non-commuting graphs has been started from 2007, where we compute spectrum and energy of various commuting graphs. Abdul Sakir also compute the spectrum of dihedral groups, so considering the commuting case and non-commuting graph of dihedral groups. And Horvani et al. Considered the non-commuting graphs and obtained some spectrum and energies for some groups. We also, in 2018, we also considered the non-commuting graph and obtained Laplacian spectrum for various images of groups. And we also compute energies of those groups. So here in this talk, I will tell about those groups were left out for computing their spectra and energy. We consider here. For example, we consider the Hanaki group, and we compute their spectrum and energy. So this is the Hanaki group. And here you can see the spectrum, these are integers. So it is an integral graph. The non-commuting graph of Hanaki group is integral. Then this is another Hanaki group. Again here, the non-commuting graph is this graph. These are the spectrum. These are all integers, so it is integral. We consider a group for which the central quotient, that is G quotiented by Z, is isomorphic to the dihedral group T2M, and we compute their spectrum and energy. But looking at this, we cannot say that it is integral or not directly. Then, as a corollary of this result, we consider the group M2RS, which is presented by these relations. We computed spectrum and energy for this. We computed consider the both cases, R is odd and R is even. Then putting R is equal to M and S is equal to 1, we get the spectrum of non-commuting graph of dihedral groups if M is odd and if M is even. Then again, in the same corollary in theorem 2.3, we put N is equal to 2, we get the spectrum and energy of dicyclic groups. We also compute the spectrum and energy of non-commuting graph of U6N. And these are some groups where spectrum is already computed by Horvani. Say, for example, if G quotiented by Z is isomorphic to GP equals GP, then the spectrum is already computed, we just compute the energy. And these groups A, Pn, and SD semi-dihedral group of order again, these are also a spectrum of non-commuting graphs were computed by Horvani. Here we just compute the energy. And interestingly, on group this non-abelian group of order PQ, which is also known as Frobenius group, if Q divides P minus 1, these are primes, and it is presented by this relation. And here we compute the spectrum and energy of non-commuting graphs for this group. Interestingly, while computing spectrum, Horvani did a small mistake, and we have corrected the mistake here. And somehow he wrote here minus, but we wrote here plus, and it is correct. So now we have computed all the spectrum and energies. So some consequence you can see, I have already mentioned that if I consider the Hanaki groups, then these are non-commuting graphs of Hanaki groups are integral. The non-commuting graphs of the group for which central quotient is Z quotiented by GP quotient cross GP, that is again integral. Then we observe some observation related to numbers like ni minus 1 into 5 ni minus 1, this type of numbers when it is a perfect square. So we got some conditions like this. The 3 observations are given for those where the numbers ni minus 1, 5 into 5 ni minus 1, these numbers are perfect squares. And using this observation and our earlier theorems, we can say that let ni be positive integers such that ni is equal to 1 and n2 is equal to 1, n2 is equal to 2, n3 is equal to 10, so all these conditions satisfies, then the non-commuting graphs of these particular groups are integral. the non-commuting graph of V8Ni, if Ni is, here I should write Ni, if Ni is odd, then it is integral, and Ni satisfies this condition. And while writing the proof, while computing the spectrum, we have seen that the graphs, non-commuting graphs, are actually are complete R-parted graph for some R. And the general notation for R-parted graph is written as K(n1), N2 up to Nr. So this vertex set can be partitions into R subsets, and two vertices are adjacent if and only if they belong to different subsets. So it is interesting to construct, at the beginning I mentioned that it is interesting to construct infinite families of integral complete R-parted graphs. And we have constructed here. So these are integral, and for this particular graph, it looks like this. We have seen that non-commuting graph of G will look like this particular R-parted graph if G is isomorphic to 8Pn, and similarly all others we have observed. And here this 2n into 2 means, so we use this notation. A suffix A1 into N1, comma A2 into N2 means here K1, K1, K1 A times, A1 times, and N2 into A2 times. So these are the groups. And finally, we can say that if Ni satisfies these conditions, then this particular, there are 8 classes. This particular 8 classes of complete R-parted graphs are integral. And after that, we compare energy and Laplacian energy. In most of the cases, in case of Hanaki group, we see that their energy and Laplacian energy are equal. And in most of the cases, we see that energy is less than is equal to Laplacian energy. So here also, see, if G by Z is isomorphic to dPm, then energy of the non-commuting graph of G is less than equal to Laplacian energy of non-commuting graph of G. Then we consider groups where P is a prime, and if these are actually corollaries, we can see that if order of G is of P cube where P is a prime, then this E LE conjecture satisfies. And if you have a 4 centralizer group, that means your cent G represents the set of centralizers, and this means it is a 4 centralizer group. This means it is a 5 centralizer group. So if it is a 4 centralizer, 5 centralizer group, then also E LE conjecture satisfies. Then we found some relation with commuting probability. Commuting probability of a group is given by this ratio. It is a ratio of set of all number of ordered pairs, number of commuting ordered pairs divided by total number of ordered pairs. And if commuting probability is any of these values, 5 by 14, 2 by 5, 11 by 27, half, 5 by 8, then ELE conjecture satisfies. Also, if P is the smallest prime dividing order of the group, then this satisfies. Commuting probability is this quantity, P square plus P minus 1 divided by P cube, then ELE conjecture satisfies. So we consider some other groups also. These are also all satisfies. But finally, if we take the non-commuting group of order PQ, that is FPQ, and we see Q divides P minus 1 and Q square is strictly less than Q plus P plus 1, then ELE conjecture satisfies. But in the proof of this theorem, we observe that if Q square is greater than Q plus P plus 1, then energy of non-commuting graph of the group FPQ is strictly greater than Laplacian energy of non-commuting graph of FPQ. So ELE conjecture does not hold for non-commuting graph of FPQ if Q square is greater than Q plus P plus 1. And for examples, it can be seen that if you take P is equal to 43, Q is equal to 7, then this satisfies this condition. So in this case, ELE conjecture does not satisfy. Similarly, we have some other examples like P is equal to 53, P is equal to 13, P is equal to 67, Q is equal to 11, P is equal to 89, P is equal to 11, etc. So, and also if you observe the non-commuting graphs of this particular group, it looks like K1 into P minus 1, comma P into Q minus 1, where P and Q are primes. So the Q divides P minus 1 and Q square is greater than Q plus P plus 1. So we also give one class of R, complete R quadratic graph, for which is integral as well as which does not satisfy E-Eli conjecture. I would like to thank Professor William Jaggi, Professor Trinity, Professor Tanner, and others for their suggestions to mathematics scenes. And the first author of this paper would like to thank Council for Cultural Relations for ICCR Fellowship. These are the references. Some of the references I have already mentioned in the slides. So these are some more references. Thank you.
Thank you very much, Professor Nath, for presenting this beautiful lecture. May I ask the audience if you have any question? Any questions from the audience? So if there is no question, then we can move for the next speaker. And I may ask Shubhnarayan Singh to present his paper entitled Vertex Degree in Power Graph of a Finite Abelian Group. So Shubhnarayan Singh, please.
Hello.
But your presentation is not, we can see.
Yes, sir, there is some problem, I think, sir. Please give some 5 minutes, sir. And there is some problem, I think. I'm trying to.
Now you can see there are 2 instances of your presence. One is for your presentation, another for you. So you please pin on the presentation.
So stop presenting 1 minute, sir. Please. Again, I have to now. Okay. Window. The PDF is not coming, sir. What is the problem? I don't know.
I think you are not selecting your entire screen. You are selecting the tabs. That's why. Maybe. Could you please try?
Your screen is coming. You can just open your presentation from your machine.
Where is the point, sir? Where is the link? I am going to the right side in corner. You are presenting the term. So there's 2 options coming out. One is your entire screen, other is a window. Which one we should?
Yeah, when you select the window, you open previously the PDF file, and then you can just select that PDF file for the window.
That is problem, sir. It's not coming.
You can just open your PDF file and do not minimize it, and then you go for the Google Meet. You select that particular window. Or Angsuman, please suggest something.
Yeah, I mean, you can share your entire screen also.
Entire screen, good. Okay. Entire screen, then?
Okay, once you select entire screen, then if you start presenting, then you can go to that your slide tab, and there you can present. I
It's
think.
not coming. It's not coming. It's coming only allow or not allow. Not now. There is two option. But if I'm going for allow, my PDF is not showing.
I mean, are you selecting entire screen?
Yes.
Yeah, now we can see your, screen, but we cannot see your slide now.
Can you open your
So
slide?
we are seeing your screen. Now you open your PDF file from where you just to present.
You just minimize. Yeah, exactly. Click that talk slide.
I kept my PDF open in the home page.
Yeah, click that. Click that.
Yeah, I opened that.
Yeah, now we can.
Now we can see.
Just make it full screen.
Make it full screen. Go to the view. Make it full screen.
Can you see my PDF?
Yes. We can see.
We can see your PDF. You go to view.
Okay.
And then you go to the full screen mode. Okay.
Yeah.
Okay, now we can start talking.
Can you see my PDF?
Yeah,
Yes.
we can see. You please proceed.
Okay. Thank you, sir. Thank you to everyone. So my topic is today presentation is vertex degree in the power graph of a finite abelian group. So first I'll define the power graph and directed power graph. So first I define directed power graph. It's defined by Kolkata and Quinn in 2000. The directed power graph of a semi-group is just a simple directed graph whose vertices are elements of S, and there is an edge from vertex U to the other vertex V whenever V is generated by the vertex U. So this is one example for the directed power graph. I just choose the cyclic graph on 6 element I just 0 bar 1 bar 2 5 bar. Here 0 is the identity element, and because in Z6 0 is generated by every other element, so from every element there will be an arrow from other element to 0, and also 1 and 5 are also generator of this one. So 1 and 5 both generating every element of this structure in Z6. So there will be from 5 to other elements of Z6. Now come to the 2 var, then see, because 2 can generate only 4 and 0, so there is a edge from 2 to 0 and also 2 to 4. C come to a 3 var, this vertex 3 var, so because 3 can generate only 0, so there is a edge from 3 to 0. Come to 4, then 4 can generate 0 and 2, so there is a edge from 4 to 2 and 4 to 0. Because 5 is generator of this group, so there is a edge from 5 to any other nodes of this group graph. So this is the directed power graph of cyclic group Z6. See the another example. Just I choose the symmetric group S3 that contains 6 elements. Just I listed these 6 elements, and see here this singleton one is identity element, and this 1, 2, 1, 3, and 2, 3 are all 3 elements of order 2, while this 1, 2, 3, and 1, 3, 2 are element of order 3. See, because these are all 3 elements of order 2 generate only identity elements, so there is an edge from 1, 2 to identity, also 1, 3 to 1, and 2, 3 to identity. Because 1, 2 has ordered 3, so this generates 3 elements, singleton 1 and 1, 3, 2. So there is a edge from 1 to 3 to identity, also there is edge from 1 to 3 to 1, 3, 2. Similarly for 1, 3, 2. So this is the directed power graph of S3. This is another example. So I come to the definition of power graph. So this definition is given by the Chakravarti, Ghosh, and Sen in 2009. So this power graph of a semigroup is an undirected simple graph whose vertices are elements of S, and any two distinct vertices are adjacent if one of them is generated by the other. So just I provide example again over Z6. So this is a example power graph of Z6. So this is 5 elements, and see that this is a connection there is one is adjacent to all the different other vertices, and also 5 is generated, so 5 is adjacent to all the other elements. 0 bar is generated by all other elements, so 0 will be adjacent to all other elements. And because 2 and 2 generate only 4 and 0, similar to 2 to 4 and 4 to 0, there is a S. Because 3 generate only 0, so there is a S from 3 to 0. So this is a example for power graph of date 6, and similar another example I just constructed power graph of S3. So this is another example. So I'll listed some motivation of this concept. So this is a one first is I cannot say first. So this is observed by Chakravarti, Ghosh and Sen in 2009 that power graph of a finite group is a connected graph. And Chakravarti, Ghosh and Sen in the same paper in 2009 they observed that the power graph of a finite group is complete if and only if this graph group G is a cyclic group of prime power order. Now, in 2011, Cameron and Ghosh proved that two finite abelian groups with isomorphic power graph are isomorphic group. Also, Cameron and Ghosh in same paper 2011 proved that two finite groups with isomorphic directed power graph have the same number of elements of each order. And Cameron in 2010 proved that two finite groups with isomorphic group power graph have the same number of elements of each order, and thus affirmatively settled a conjecture posed by Cameron and Ghosh in the 2011 paper. Curtin and Porguli in 2014 proved that among all groups of a given order n, the power graph of cyclic group Zn has the maximum number of edges, and thus affirmatively settle a conjecture posed by Mirzagar et al. In 2012. Published in 2012. Now this is another observation by Chakravarti et al. In 2009 that number of edges in power graph of a finite group of order n is given by this formula. I need some notation, so I just mention that notation. This mod G is nothing but the order of element G in the group. Mod G is nothing but the order of G. This notation for the cyclic group generated by G, and this notation for either phi function. This is also observing to 15 that vertex degree of a vertex G in the power graph of the cyclic group Zn is given by this formula. In this work, we investigate the vertex degree in the power graph of a finite abelian group. This is a small work that you can say this extension of this 2015 result. So we need some notation. So throughout this talk, the symbol G denotes a finite non-trivial group. Moreover, for any element inside G, we'll denote, this is the notation for the, I denote the degree of G in this notation. In degree of G in the directed graph is this notation, our degree of G with this notation, and the size of the set of bidirectional edges incident on G by this notation. So just by observing the definition of directed power graph, there is this is one remark that in the directed power graph, the vertex corresponding to the identity element of G is the unique vertex, such that in degree of identity is that a vertex is mod G minus order of G minus 1, and outer degree is nothing but 0. This is a unique vertex inside of directed power graph. This is another remark that if we have any non-identity element, then outer degree is nothing but outer degree of element G is nothing but mod G minus 1. Mod G means the order of G minus 1, and bidirectional degree is nothing but either phi function of mod G minus 1. So we observe that we have a non-identity element. To calculate the degree of element G, we have to add the inner degree plus outer degree and then subtract the bidirectional degree of G. So thus degree of G is nothing but in degree plus out degree and then subtract the bidirectional degree. So thus we observe this one, in degree plus order of G minus Euler phi function of order of G. So it is therefore sufficient to because you want to calculate the degree of any element inside element G. So it is sufficient to calculate the in degree because of this observation. We have to sufficient to calculate the in degree of element of J. So this is one result. So I choose this M1, M2, M, these are integers with this condition. 1 is less or equal than M1, less or equal than M2, and so on. And we have a group, a Billion P group, where order of XR is nothing but P per MR for R from 1 to N. If we have a non-identity element of these such that order of X alpha for I alpha is equal to P for T alpha, then in degree of X is given by this formula. The big formula in structure. And based on this theorem, we easily observe that if you have a cyclic group of prime third order, from the previous result, we have observed that if you have a cyclic group of prime third order, then this power graph of cyclic group of prime third order is nothing but a complete graph. Now, if G is the internal direct product of two normal subgroups H and K, such that GCD of order of H and order of K is equal to 1, if Z is any element inside G where X belongs to H and Y belongs to K, then outer degree of Z in G group is given by, we have to calculate the outer degree of X in power graph of H, then outer degree of Y in power graph K. We have to write in this way and this make the subtract by 1. So in this way we get the outer degree of Z in G. Similarly, we get the by Z in J in this formula, where G is the internal direct product of two normal subgroups H and K, with the condition GCD of H and K is equal to 1. Now, as induction on the number of normal sub extension of this above theorem, because previously we just two normal subgroups, now we taking a normal subgroups and just using the induction. So let G be an internal direct product of normal subgroups H1 to Hn, where GCD of Hi Hj, order of Hi Hj equal to 1, where I different from J. If X is any element of C, where Xi belong to Hi, then outer degree of X in G is given by this expression. Bidirectional of degree of X in G is given by this expression, and in degree of X in power graph of G is given by this expression. And finally, we have a abelian group of order n, where n can be expressed in this way: P1 power M1 and P2 power M2 of G, where Xi belong to GPI. GPI just mentioned below. GPI is nothing but collection of all X belong to G, such that X power Pi power Mi equal to E. This is the normal subgroup of G for all I from 1 to K. So where Xi belong to GPI, then outer degree of X in power graph of G can be given by this expression. Bidirectional degree of X in the power graph of C can be given in this expression, and in degree of X in power graph of G is given by this expression. So these are my references. I just read the PJ Cameron paper, Cameron and Ghosh paper, Chakravarti Ghosh and Sen paper, and Guardian Proverb paper, and Thank you for giving the opportunity to present this work at this forum.
Thank you very much for giving such a nice lecture on paragraph. May I ask the audience if there is any question?
Yes, I have a question, if I may. So you have this general result about the direct product of groups of pairwise coprime order.
Yes,
so that suggests to me that your result might generalize to nilpotent groups, because a group is nilpotent if and only if it's the direct product of its CILA P subgroups for different primes.
Yes,
so this should reduce nilpotent groups just to groups of prime power order.
Okay.
So maybe you can extend these results.
Okay, thank you.
Mr. Shubnaran Singh, can you hear the question? Then please respond.
No, sorry, I confused. I did not listen clearly. Can you repeat the question again?
Yes, sure. I'll repeat the question. So I was just wondering whether your results can generalize from abelian groups to nilpotent groups, because a group is nilpotent if and only if it is the direct product of its CILA P subgroups for different primes, and these groups have coprime order, so your general formula that you have there in theorem 0.15 says as long as you can solve the problem for groups of prime power order, then you can solve it for all nilpotent groups.
Yes, I did not.
It's not a question, really. It's a comment.
I did not see that extent.
What it is, so that you can understand it.
Yes, I'm showing the slide. I did not see that extension. I did not go for the important group, so on.
Well, maybe that's a direction that would be worth going in.
Yeah, okay. Thank you, sir. I will check that out.
Okay. Right.
Any other questions? So, if there is no question, so we thank the speaker again for this lecture, and I especially thank all the speakers, 7 speakers in this session, for contributing such nice papers, and I am really very much surprised and very much happy to see that some elements of algebraic graph theory has attained a very rich position, and that when we have started with these power graphs and intersection ideals of rings, and then what was the scenario now, I am really very much happy to see that the scholars and various professors and teachers and mathematicians throughout the globe, that they are contributing greatly to the algebraic graph theory, and these are very rich contribution. It is very happy to see that, and so I again congratulate Professor Angsuman for organizing this conference on in algebraic graph theory in this pandemic situation. It is lovely. Thank you. And I make an end of this session. And so, please, Angsuman.
Thank you, Professor Ghosh. Shubnaran Singh, can you please stop presenting?
How to do that?
Yeah, just click that you are presenting and then click stop presenting. Yeah.
Thank you.
Thank you. So I would like to thank again the chair of this session for, organizing the entire session in a nice way and to end the session in time. So I'm really thankful to him. I think we have 10 minutes time before the next speaker's lecture. So we'll be back again within 10 minutes. Now it is 3:48 here. So by 3:57 we'll be here for the next talk. The next talk will be by Professor Peter Cameron. So we'll be back within 10 minutes. Okay, so we are back. So now may I request Dr. Kuntal Banerjee to formally introduce our next speaker.
Shall I share my screen first?
Yes, you can.
How's that? Can you see that?
Yes, you can see.
Yes, it's visible. Yeah.
Okay, fine. Right, so go ahead.
Kuntalda, please.
Okay. Welcome everyone to the second session of the invited lectures. And the speaker here is Professor Peter Cameron. Professor Cameron has received his bachelor's degree from University of Queensland and his PhD degree from University of Oxford under the supervision of Peter Neumann. He was awarded the Whitehead Prize in 1979 and the Euler Medal in 2003. In 2018, he was elected as a Fellow of Royal Society of Edinburgh. He is currently an Emeritus Professor at the University of Queen's Mary, London, and he is a half-time Professor at University of St Andrews in UK. His main research areas are algebra and combinatorics. He has authored many books on combinatorics, algebra, permutation groups, and logic. He posed the famous Cameron-Erdos-Lagrange conjecture with legendary mathematician Paul Erdos on some presets in 1988, which was proved later by Ben Green in 2004. So welcome, Professor Cameron, and I request you to start your lecture now.
Thank you very much. Can you hear me clearly?
Yes.
Yeah. Okay, fine. Good. So, graphs defined on groups. Well, first of all, let me say thank you very much to the organizers. In these rather strange times, it's so nice to have this opportunity to meet, if only virtually, and to share information. So, there will be quite a lot in my talk. I'm talking for an hour and a half. So, if you have any questions, please don't hesitate to get in touch and by email. So questions are welcome. What I propose to do is, an hour and a half is a long time to concentrate for, so I will try and stop about every half hour to give you the opportunity to catch your breath and to ask any questions that you might have at that point. There is a selected bibliography at the end of the slides, but there's a lot of information in the slides, so I prepared a handout version, and you're very welcome to ask for a copy of that. So just email me and I'll send you a copy of the handout version. Okay, so graphs and groups is a very big topic, and it's far more than I can cover even in an hour and a half. So let me first of all say two things that I will not be talking about. First of all, the famous theorem of Frucht from 1939, every group is the automorphism group of the graph. And indeed, you can put many restrictions on the graph, and this remains true. You can specify the valency, the connectivity, the chromatic number, and it's still true that every group is the automorphism group of such a graph. And in the other direction, graphs have been very useful to the study of groups. So, for example, when about the time that I was a student, sporadic simple groups began to pop up all over the place, including, for example, the Hickman-Sims group, which is the automorphism group of a graph on 100 vertices, and was discovered in 1968 by Hickman and Sims, though in fact the graph had been constructed earlier by Dale Mesner, but Hickman and Sims studied the automorphism group. So I will not be talking about that either. So I'm going to talk on a rather specific topic, but we've heard several things about this topic already in the contributed talks. So the vertex set of my graph will be a group, and the joining rule in the graph, the rule for edges, will give you some information about structural properties of the group. So The first example is Cayley graphs, which Brian told you about in the first plenary lecture this morning. They're invariant under translation by group elements, so they're certainly vertex transitive graphs. Then there are graphs defined more directly, such as some of those that we've heard about. We heard about the power graph and the commuting graph just now. Another one is the generating graph, which I will tell you about later. And there are some other graphs that are related, although they're not actually defined on the set of elements of the group. They're defined in a slightly different way, but they're relevant to the study of these graphs that I'm interested in. And these include the Grunberg-Kagel graph, sometimes called the prime graph of the group, and the intersection graph of the group. So, several of these graphs were defined first for semigroups. I'm not going to consider semigroups. If you're interested in semigroups, many of the questions I raise here can also be asked for semigroups, where there are also many other interesting questions. And as well as semigroups, I should say rings, because we heard this morning something about graphs associated with rings. I will stick to finite groups almost entirely in this lecture. Infinite groups are a different game altogether, and I may make some remarks, but basically I will, my groups will be finite for the most part. And the other thing to say, my first example of a graph defined on a group was a Cayley graph. If I tried to tell you about Cayley graphs, we would be here all week. So fortunately, Brian is telling you about Cayley graphs in his lectures, so I will omit that, and I'll just stick to the kind of graphs that I've described in the second two bullet points on the previous slide, the graphs defined on a group and then related graphs like the prime graph and intersection graph. So, let me start off with the example which is easiest to define, which we heard about earlier, the commuting graph of a group. So, the vertex set of the commuting graph is the group G. We join two vertices, little g and little h, if they commute. In other words, if GH is equal to HG. So this is obviously a symmetric relation on the group, so this defines a graph, an undirected graph. Now there's one small thing to notice here. An element commutes with itself. So if you interpret my definition strictly, this graph has a loop at every vertex. And that's sometimes useful, as you'll see in a moment. I will change the definition shortly. I'll change it a couple of times, but this is the basic definition for now. And I want to tell you something that perhaps you didn't already know about the commuting graph, even if you study it. So as I say, the graph has a loop at each vertex, and also elements of the center. The center of the group is by definition the set of elements that commute with everything in the group. So they are the elements that are joined to all vertices. Right, so if G is an abelian group, then any two elements commute. The commuting graph is the complete graph. So that's easy enough. Here is a non-abelian example. There are two non-abelian groups of order 8. There's the dihedral group and the quaternion group. And it turns out that their commuting graphs are actually isomorphic. So each group has a cyclic subgroup of order 4, whose subgroup of order 2 I've put in red here. The other elements can be labeled so that you don't have to know which group I'm talking about. Is it the dihedral or quaternion group? But the elements are labeled like that, and these are the edges in the commuting graph. So there's an example. A commutes with all its powers. B commutes with, well, B squared is equal to either the identity or A squared, depending which group we have, but it commutes with these four. And AB is in this complete graph up here. So there's an example of the commuting graph of a non-abelian group. Now here's a remarkable property of the commuting graph, due essentially to Mark Jerram. Suppose we take the commuting graph and we go for a random walk on it. In other words, I start off at some vertex, I choose a random neighbor of that vertex, and since there's a loop everywhere, I'm allowed to stay where I am. But I choose randomly a neighbor, and I move to that neighbor, and then I go on doing that for a long time. Where will I be in the end? Well, it turns out I could be anywhere, but the limiting distribution is uniform on the conjugacy classes of the group. In other words, if you end up after a large number of steps, you're equally likely to be in any of the conjugacy classes. So if we just go back to the example for a moment, you can see in this graph, it's got these two red vertices that are somehow right in the middle of things. And to get from here to here, for example, you have to pass through a red vertex. So you're more likely to be at the red vertices than at the black vertices around the outside. In fact, if you do the sum, you're twice as likely to be at the red vertex as you are to be at the black vertex. And indeed, these red vertices lie in conjugacy classes of size 1, whereas the black vertices lie in conjugacy classes of size 2. So the probability of being at one of these two is the same as the probability of being at this particular red vertex. So that's that's the theorem. So the probability of being at a vertex tends to a limit as the time goes to infinity, and the limit is inversely proportional to the size of the conjugacy class. And as an application of that, suppose that you are given a huge group that has not too many conjugacy classes, some large, some small, and you want to find representatives of all the conjugacy classes. Well, if you pick an element at random, chances are it will lie in a large conjugacy class. And if you go on picking at random, it'll take you a very long time to hit a small conjugacy class. So for example, in the symmetric group of degree n, the transpositions form a conjugacy class of size just n times n minus 1 over 2, about n squared, whereas the n cycles form a class of size n minus 1 factorial. So how do you find these small classes? Well, what you do is you take a random walk on the commuting graph, and that, so to speak, amplifies the small classes and makes them equally likely to the large classes. So this is a practical way. That commute with everything in that subgroup. So if you take a Silov P subgroup of the group, all its elements must lie in a single connected component of the commuting graph, because you can go via the center of that subgroup. So take a connected component, let's call it C. Because the Grunberg-Kagel graph is connected, we can move from one prime to another, and we find at least one Silov P subgroup for each prime contained in C. So C, we don't know it's the whole group yet, but we know at least it contains a Silov P subgroup for every prime. Now, we take an element of C, let it act by conjugation. Remember, C is a connected component of the commuting graph. So this element we pick commutes with itself, and therefore it commutes with all its neighbors, and you work your way out, and you find that it fixes the entire connected component. So the normalizer of C is the whole group. But all the Silov subgroups are conjugates, so if one Silov subgroup lies in C, then they all do. So C contains every Silov subgroup of G, and thus it contains all the elements of prime order, and that's all we need to prove that it's connected. So that's the proof of that proposition. And the moral of that is that this small graph, the Grunberg-Kagel graph, can tell you strong information about some of these other graphs. And we'll see other examples of that later as we go on. So just a couple of things about the Grunberg-Kegel graph. It's a study, it's an intensely studied graph at the moment. You have to go to Russia to find out the experts on this. People in mathematicians in Yekaterinburg and Novosibirsk have been working hard on this graph, and they've been looking at questions such as which groups are characterized by their Grunberg-Kegel graphs, or perhaps by their labeled Grunberg-Kegel graphs. So, for example, Grunberg-Kegel graph, the vertices are labeled by primes. You might have the same graph, but with the primes put on differently. And given a graph, how many different labelings of it correspond to actual groups? So here's a little example. So this is a graph, a triangle with a pendant vertex. I'll show you a diagram in a moment. Now, in Yekaterinburg, which is in the Ural Mountains, this is called the Por. In Novosibirsk, it's called the Balalaika. So I suppose they have more bears in Yekaterinburg and more musicians in Novosibirsk. But anyway, here are two graphs two groups whose Grunberg-Kegel graph is isomorphic to this graph. The alternating group of degree 10 and the automorphism group of the sporadic Yanko group J2. And here they are, and you can see why it's called the Balalaika from this picture. But also, if you look at these two, it's the same. So in the alternating group of degree 10, that's easy to think about. Take a 3 cycle and a 7 cycle, they commute. So 3 and 7 are joined. But an element of order 5, you can't fit a 5 cycle and a 7 cycle into 10 points. So there are no commuting elements of orders 5 and 7. And 2, because we're in the alternating group, the smallest element of order 2 will be a product of 2 transpositions. And again, that uses 4 points. You can't fit it in with these 7. So with arguments like that, you can verify this is the Grunberg-Kegel graph. And if you compare it to this one, which I don't expect you can easily work out, but this is the Grunberg-Kegel graph of this group, you see that 3 and 2 have swapped places. So these have isomorphic Grunberg-Kegel graphs, but the primes have been put on in a different way. So that's probably a good point to stop, take a short break. If anyone has any questions so far, you can ask them now if you want.
If you have any question, ask.
So are there no questions? Then I'll carry on. Okay, so now I'm going to start talking about some of the other graphs that I'll be referring to here. I'm reversing the historical order. We heard just a little while ago that the power graph was defined by Kolerev and Quinn in about 2000. The power graph wasn't defined for some time, the enhanced power graph wasn't defined for some time afterwards, but in a sense it's easier to define, so I will give you the definition first. So, also, I'm going to change my conventions again. When I was talking about the commuting graph, I said we leave out the elements of the center. But I want to compare these different graphs. I'll have several different graphs defined on the same group. I want to compare them, so I want to have the same vertex set in each case. So I'm going to change my convention, and for the rest of the lecture, this is the convention. The vertex set is all the non-identity elements of the group. So in the case of the commuting graph, if the center happens to be just the identity, which is a case, especially interesting case as you saw, if the center is just the identity, then this is the same as the usual definition of the commuting graph. So the vertex set of each of my graphs now is going to be the non-identity elements of the group. And in the enhanced power graph, we join x to y by an edge if there's some vertex z, some group element z, such that both x and y are powers of z, right? So if x is some power of z and y is some possibly different power of z, then we will join x and y by an edge. So you can say that in a simpler way. X and y are joined by an edge if and only if the subgroup that the two elements generate is a cyclic group. And why is that? Well, if x and y are both powers of z, then they both lie in the cyclic group generated by z. But every subgroup of a cyclic group is cyclic. So whatever the subgroup generated by x and y is, it's a cyclic group. So this is a definition purely in terms of the group structure. X and y are joined if and only if they generate a cyclic group. Now, if you think back to the commuting graph, in the commuting graph, x and y are joined if and only if the group they generate is an abelian group. And you might already think, well, I can generalize that in various ways. I'll say a little bit about that later, but for the moment, just remember that we have those definitions. And you see from that the enhanced power graph is a spanning subgraph of the commuting graph, because every cyclic group is abelian. So if the group generated by x and y is cyclic, then it's certainly abelian. So edges of the enhanced power graph are edges of the commuting graph, but not necessarily conversely. So this graph, the enhanced power graph, is a spanning subgraph of the commuting graph. And if you haven't met that term, it simply means you use all the vertices, but only some of the edges. Right, now the power graph, as I say, which we've seen a definition of, but here it is again. First, we define the directed power graph. So the directed power graph of a group G has an arc from x to y if y is a power of x. So it's a directed graph. It comes naturally as a directed graph with this rule. And if we want to get the ordinary power graph, we have to undirect that relation. But first of all, we note you might have arcs in both directions. It might be a bidirected arc. If x and y generate the same cyclic group, then y is a power of x and x is a power of y, and so you get arcs in both directions joining. So the power graph is obtained by just ignoring the directions on the edges. And if there are double edges, we forget that they're double edges, we just put single edges. In other words, x is joined to y in the power graph if and only if one of x and y is a power of the other. So if this relation holds one way round, at least, then we join them. And so again, we see that the power graph is a spanning subgraph of the enhanced power graph, because remember, in the enhanced power graph, we required simply that there's some elements such that both of these are powers of that element. And of course, if y is a power of x, then we can take both x and y to be powers of x, and that shows that they're joined in the enhanced power graph. So, different groups can have isomorphic power graphs. So suppose that you have a group whose order is 3 to the d, say, and whose exponent is 3. In other words, all its non-identity elements have order 3. Then, what are the edges in the power graph? Well, if you have an element of order 3, its only powers are itself, its inverse, and the identity, and that gives you a triangle. So you have a whole bunch of triangles just joined together at the identity, but we've thrown the identity away. So what we've actually got left is just this many disjoint edges. So any group of exponent 3 has power graph consisting of that many disjoint edges. And the reason I chose 3 rather than 2 is because there are non-abelian groups of exponent 3. There's an abelian group of exponent 3, namely the direct product of d copies of the cyclic group of order 3, but there are also non-abelian groups of exponent 3, and they all have isomorphic power graphs. In the infinite case, so I will touch here on the infinite, things are even worse here. There's a group called, well, there's one group of these for each prime. The proof of group is the group whose elements are the, you take the rationals mod the integers, and you take the rational numbers whose denominator is a power of p. And it has the property that every subgroup, every proper subgroup is a finite cyclic group. So the power graph, any two elements are joined, so the power graph is a countable complete graph. We can't even say which prime we started off with. If you take C2 to the infinity and C3 to the infinity, they have isomorphic power graphs. So that's not much use. So we'll stick to the finite case. So the power graph is complete if and only if G is cyclic prime power order. We heard this theorem earlier. And otherwise, if it's not complete, we'd like to know which vertices are joined to all others. And the identity would be, but we've thrown it out. And the ones that the cases that remain are, if G is a cyclic group and little g is a generator, then it's joined to everything. If G is a generalized quaternion group, this is a group that has a unique involution in the center, and every element of the group, some power of it, is this central involution. So this element is joined to everything. So those are the only cases where you can have a vertex joined to all others. As I said, the power graph comes naturally to us. It's given to us as a directed graph with directions on the edges. If you're just given the undirected power graph, can you recover those directions? Well, you can't recover them uniquely because, for example, if you take the cyclic group of order 6, we saw a picture of the power graph of this earlier. It has 5 vertices. The 2 generators are joined to everything else. But there are 2 elements of order 3 which are joined to the generators and also to one another. They have valency 3. There's one element of valency 2, namely the element of order 2, which is joined just to the generators. But to recover the directions, we'd have to know which element of order 6 is the square of which element of order 3 is the square of which element of order 6. And the graph doesn't tell you that. But it tells you it up to isomorphism. So the following theorem holds. I proved this based on the work that I did with Shamik Ghosh. If you take any finite group G, if you're given the power graph, you can put directions on it to get the directed power graph up to isomorphism. The directions are not uniquely defined, but any 2 ways that you put the arrows on to give the directed power graph will be isomorphic. So at least that much information that isn't obviously there can be pulled out now. So that gives you some information, and that tells you more. That tells you that if you know the power graph, then you know the enhanced power graph. Because how do we get edges in the enhanced power graph? Well, remember that x and y are joined in the enhanced power graph if they're both powers of some element z. So if we have the directed power graph, that's just saying there's some element z that sends arcs to both x and y. And so if you know the directed power graph, you can determine that, and so you can determine the enhanced power graph. So the power graph determines the enhanced power graph up to isomorphism. Right, well, I said we have this definition of the enhanced power graph and the commuting graph, which look very similar. You look at the subgroup generated by x and y. For the enhanced power graph, you require that to be cyclic, and for the commuting graph, you require that to be abelian. So, plenty of open questions there. What if you take some other group theoretic property and say, we'll join x and y if the subgroup x and y generate has the property P? What can you say about that graph? And now, as far as I'm aware, very little is known about this question. But you might like to start off with the property that this group is nilpotent, or perhaps that it's soluble. And what can you say about those graphs? So I think there are probably interesting open questions there that you might like to take a look at. So now coming back to our main characters, the commuting graph and the power graph and enhanced power graph, here's another variation. Here we were just talking about properties of the group generated by X and Y, but what about saying we'll put an edge if X and Y generate the whole group? And this gives you a graph called the generating graph. This has been the subject of very much study recently, and I'll tell you a little bit about it. So so you join X and Y if the group that they generate is the whole group. Now, if you can't generate the group with two elements, of course, this graph has no edges at all. That's not very interesting. And the other thing that isn't terribly interesting is in a cyclic group, if you take Y to be equal to X to be a generator of the cyclic group, then you would get a loop. I'm not very much interested in those cases. So usually I will assume that the group genuinely has two generators and it's not a cyclic group. It can't be generated by just one element. And one of the reasons why people are interested in this is because one thing that the classification of finite simple groups tells us is that every non-abelian finite simple group can be generated by two elements. So the generating graph of a non-abelian finite simple group will not be the null graph. It will have at least some edges. And once people started thinking about that, they realized that there's a great deal of freedom in how you choose those two generators. So, for example, it was a fairly early observation that if you pick any non-identity element of a finite simple group, it lies in a two-generating set. In other words, you pick an element X, then you can find another element Y such that X and Y generate the group, and that means Y is joined to X in the generating graph. So, but in fact, something much stronger is true. So this is a recent result of Tim Burness, Bob Guralnick, and Scott Harper. Lovely theorem. So, for a finite group G, the following three conditions are equivalent. The first condition says the generating graph has no isolated vertices. And now, think what that means. It means what I just told you. If you pick an element X, a non-identity element of the group, you can find a non-identity element Y such that X and Y generate the group. So any element is contained in a two-element generating set. So the second condition, this looks much, much stronger. It says if you take two vertices, any two vertices, they have a common neighbor. So in other words, if you pick any two elements X and Y, not the identity, you can find an element Z such that X and Z generate the group and also Y and Z generate the group. So that's very strong and tells you, it's much stronger, for example, than saying that the generating graph has diameter 2. So this is a very dense graph. And the group theoretic equivalent condition is that every proper quotient, every proper homomorphic image of the group is cyclic. So, for example, this property holds in a non-abelian finite simple group. So all non-abelian finite simple groups have this property here, that any two vertices have a common neighbor. So that's the generating graph. And now let's look at these graphs together. So part of the reason that I chose the vertex set in each of these graphs to be the non-identity elements of the group is so that I can compare them. So I'm going to give you a hierarchy of graphs. So we start off with group G, and we take our vertex set in every case to be G minus the identity. First graph we look at is just the null graph, no edges at all. Next one we take is the power graph. So X and Y are joined if one of them is a power of the other. The enhanced power graph, X and Y are joined if they're both powers of some other element. The commuting graph, X and Y are joined if they commute, and we saw that if they're joined in the enhanced power graph, then they're joined in the commuting graph. Then the non-generating graph, where we join two elements if they don't generate the group. Now, it's not obvious that the commuting graph is a subgraph of that, so I'll have to come back to that. But at the top of the hierarchy, we have the complete graph with all possible edges. So we saw on the way through that the null graph is certainly a spanning subgraph of the power graph, which is a spanning subgraph of the enhanced power graph, which is a spanning subgraph of the commuting graph, and everything is, of course, a spanning subgraph of the complete graph, but it might not hold for these two, and indeed, when does it hold? The commuting graph is a spanning subgraph of the non-generating graph if G is non-abelian, because here we join two elements if they commute, and if the group is non-abelian, then two commuting elements can't generate the whole group because they generate an abelian subgroup. So that would show you that if you just simply require that the group G is non-abelian, then the commuting graph will be a spanning subgroup of the non-generating graph. So I genuinely have a hierarchy of graphs here. And we're going to think about this hierarchy for a little bit. So the first thing you might want to know is, when are two consecutive graphs in the hierarchy equal? So the null graph, when is the null graph equal to the power graph equal to the enhanced power graph, or so on, or the non-generating graph equal to the complete graph? So I'm going to look at all those questions and tell you something about them. So I'm going to start at the top and work down. So the non-generating graph is complete. What does that mean? That means that you can't generate the group with two elements. So we said that if G is not two generated, then the commuting graph, the generating graph is null, therefore the non-generating graph is complete. So the top two things in the hierarchy, that's the condition. Right, if we take a non-abelian group, then the commuting graph is a spanning subgraph of the non-generating graph. When are they equal? Well, it turns out that they're equal if and only if G is a minimal non-abelian group. That is, G is non-abelian, but every proper subgroup is abelian. So that would say that if you take two elements that don't commute, then they can't lie in a proper subgroup, because proper subgroups are abelian. Therefore, they must generate the whole group. So that shows you why these two graphs would be equal for minimal non-abelian groups. And this is an old result. It goes back to 1903. Miller and Moreno determined completely the minimal non-abelian groups. There are two types. I won't go through them in detail here, but the paper is in the bibliography. So there's one type of group that has prime power order, and another where the order is a product of two prime powers, where the second prime divides p to the n minus 1. So there are two types of groups, but they're all completely determined. Now, the next two cases are in a paper I wrote with Godratella Alipur and colleagues in Iran. So, when is the commuting graph equal to the enhanced power graph? What does that mean? That means that if two elements commute, then they actually lie in a cyclic group, so they're both powers of a single element. So the thing that forbids is a subgroup which is a direct product of two cyclic groups of prime order, because this is the essential example of a group where the generators of the two factors commute, but there's no element that they're both powers of, because all the elements have order p. So by saying that the commuting graph equals the enhanced power graph, we're forbidding subgroups Cp cross Cp. Now, for groups of prime power order, this goes back to Burnside, who showed that a group of prime power order with no Cp cross Cp subgroup had to be cyclic or generalized quaternion. And we can actually determine all the groups that have this property. So here's a rough sketch of what happens. So there might be a normal subgroup of odd order, and modulo that, we have a group with a unique involution, which it could be. So the point is that if you take a generalized quaternion group and you factor out the central involution, you get a dihedral group. So we're looking at groups whose seal off 2 subgroup is cyclic or dihedral, and they were characterized by Gorenstein and Walter back in the late 1960s. So essentially we know groups where the commuting graph is equal to the enhanced power graph. So when is the enhanced power graph equal to the power graph? Well, that says that if 2 elements generate a cyclic group, then one is a power of the other. And what that forbids is cyclic groups of order PQ, where P and Q are distinct primes. Because if you take an element of order P and an element of order Q that commute, they lie in a cyclic group of order PQ, so they're joined in the enhanced power graph, but neither is a power of the other if these are distinct primes, so they're not joined in the power graph. So we're forbidding cyclic subgroups of order PQ. Well, you see, that's a condition that can be expressed in terms of the Grunberg-Kagel graph. There are no elements of order PQ. That means the Grunberg-Kagel graph of G is a null graph. It has no edges at all. Okay, so what could happen? Well, it could be that the order of G is only divisible by 1 prime. Then the Grunberg-Kagel graph is just a null graph on 1 vertex. But otherwise, it's disconnected. So we can apply the results about groups whose prime graph, whose Grunberg-Kagel graph is disconnected. And there's still quite a bit more work to do, but you can actually figure out a complete description of what all these groups look like. And Natalia Maslova and I hope to publish this complete list soon. We're working on that at the moment. So these 2 things, these 2 classes that we just saw, groups where the commuting graph equals the enhanced power graph, or where the enhanced power graph equals the power graph, they're both rather complicated. If you want a simpler characterization, you just jump over the enhanced power graph and say, what are the groups where the commuting graph is equal to the power graph? Well, it turns out they're easier to classify. Cyclic groups of prime power order, generalized quaternion groups, and some groups with order divisible by 2 primes, and with some condition like this holding. So you can describe these groups completely anyway. So those groups are relatively simple to describe. And the final triviality, when is the power graph null? Well, now, if you don't throw out the identity, then this would only happen for the trivial group. But we're throwing out the identity, and so that means that every element must have order 2, because its only power is allowed, if you take x, the only proper power of x must be the identity, so every element has order 2, so G is an elementary abelian 2 group. So the answer to this case is the elementary abelian 2 groups. And that gives us all the cases in the hierarchy where 2 consecutive groups are equal. So what might you do? Well, are there similar results for infinite groups? And we did get some results for infinite soluble groups with power graph equal to commuting graph, but there's a lot that hasn't been worked out there. So there are open problems there. And this, I think, is a more interesting question. Suppose successive graphs in the hierarchy are not equal, then you can look at the graph, you can look at their difference. You can look at the graph whose edge set is the edges in the larger graph, but which are not edges in the smaller graph. So, for example, things that are joined in the commuting graph, but not joined in the enhanced power graph, to just pick one example. So what can you say about those? Well, again, starting at the top of the hierarchy, at the top we had the complete graph, and the next one we had the non-generating graph. And the difference between those is, of course, exactly the generating graph. And this is a graph that's received a lot of study. The other cases, much less. The difference between the non-generating graph and the commuting graph for non-abelian groups. So Saul Friedman, who's a PhD student in St Andrews, has looked at this, and he has a lot of detailed results, which I can't describe to you in general, but in particular, there's a complete analysis of connectedness and diameter for nilpotent groups. So for the next two cases, the difference between the commuting graph and the enhanced power graph, the difference between the enhanced power graph and the power graph, I know nothing about that. I don't think anything has really been done on that. So if you want to take a look at that, you've got the field to yourself pretty much. The bottom case is the difference between the power graph and the null graph, which is just the power graph, which has had a lot of study. But here's another question. Remember we saw that the random walk on the commuting graph is extremely interesting because its limiting distribution is uniform on conjugacy classes. What about random walks on some of these other graphs? Do they have interesting properties? And you may, if you wish, put the identity back in, and you may, if you wish, put loops on all the vertices and that kind of thing. So can you say anything about the behavior of the random walk on any of these graphs? So one final remark on the hierarchy. The non-generating graph is somewhat exceptional in that list, because in all the others, if you take a subgroup H of your group G and look at the induced subgraph of the big graph on the set H, it's just the corresponding thing of the subgroup H. For example, if you take the commuting graph, if you take two elements of H that commute in the group G, then of course they commute in the group H, so they form an edge of the commuting graph of H. And that holds for all the other cases except for the non-commuting graph, because, the non-generating graph, because for the non-generating graph, if you take any proper subgroup, then two of its elements can't generate the whole group. So you get a complete graph there, which is not necessarily the same as the non-generating graph of H itself. So, but at least what we can say is that the edge set of the non-generating graph is a union of the complete graphs and all the proper subgroups of G. So if you take all the proper subgroups of G, two elements don't generate G, must lie in a proper subgroup. So that edge is contained in one of these proper subgroups. So it's a union of complete graphs on the proper subgroups. And of course, it's enough to take the maximal proper subgroups. And in the commuting graph, or the enhanced power graph, the induced subgraphs on the abelian or cyclic subgroups are complete and cover all edges. So there's a similar thing going on there. So that's the hierarchy, and I think there are interesting questions to ask there. But now I'm going to go back, I'm going to go on to another graph associated with a finite group. That's the intersection graph. So the vertices here are not the group elements, but the non-trivial proper subgroups. So you take all subgroups of G apart from the whole group G and the identity subgroup, and two of these vertices are adjacent if their intersection is non-trivial. So it's an intersection graph in the usual sense in graph theory. You have a family of sets. You join them if their intersection is non-trivial. Here our sets are the non-trivial proper subgroups of the group. And this is related to the generating graph because two elements are adjacent in the non-generating graph if and only if they're contained in a proper subgroup. So this is why some of the same techniques for the non-generating graph also apply to the intersection graph. So here are some remarks about it. First of all, if you take the cyclic group of prime order, it only has two subgroups, itself and the identity, so there are no vertices at all in the intersection graph. But for any other group, there will be at least one vertex. And in a finite group, every proper subgroup is contained in a maximal subgroup. So if you can find that any two maximal subgroups lie at distance at most d, then the diameter of the whole intersection graph is at most d plus 2, because you take your first subgroup, go up to a maximal subgroup, then in d steps you can move across to the other maximal subgroup containing your second subgroup, so you can get there in d plus 2 steps. And the final thing to remark is that if your group is not a dihedral group, then any two subgroups of even order have distance at most 2. Because if a group has even order, it contains an element of order 2, an involution. So pick an involution in the first subgroup, pick an involution in the second subgroup, and use the fact that 2 involutions generate a dihedral group. And if the whole group is not dihedral, that means the group generated by these 2 involutions is a proper subgroup. And so we have a path of length 2 between the 2 subgroups. So, the question of the diameter of the intersection graph was first, well, these graphs were introduced by Czerkani and Pollack in 1969. They proved that if the group is not simple, then they could determine when the intersection graph is connected, and if it is connected, then its diameter is at most 4. That's for non-simple groups. What about simple groups? Well, nothing happened for quite a long time. Then in 2010, Shen proved that the intersection graph is connected. He didn't find a bound on the diameter, but in the same year, these 3 authors, Herzog, Longobardi, and May, bounded the diameter by 64, and a little later, Ma reduced this bound to 28. Now we know the answer. Saul Friedman showed that if you have a non-abelian simple group, the intersection graph has diameter at most 5. So 5 is the correct bound because the baby monster group attains the bound 5. There are 2 subgroups of order 47, if I'm not mistaken, in the baby monster, which are not joined by any path of length shorter than 5. There might be other groups achieving the bound, but they must be unitary groups of prime dimension. And in fact, it's known that for unitary groups, there are some examples that have diameter 3, some have diameter 4, some have diameter 5. Oops, sorry. We don't know which groups realize which possible values. All possible values occur, but there's a good question there. Can you decide which unitary groups fall into which of the 3 cases? Okay, time for another little break, I think, if anyone has any questions.
Any questions?
Any questions?
Hello, sir. I have a question.
Yes.
Can we characterize the group G such that the enhanced power graph is always the complete graph or a tree, or it has isolated vertices?
Well, if you take a cyclic group, then any 2 elements of a cyclic group generate a cyclic subgroup, so they are joined in the enhanced power graph. So the answer is yes, in a cyclic group. But if the group is not cyclic, then there will be 2 elements that generate a subgroup that isn't cyclic, so that it won't be complete. So that is known. Your other question, which are the vertices joined to all others? That's a very good question. At the moment, I don't know the answer to that. I don't think it would be all that hard. You could probably sit down and work that out. It would be an important thing to know, because when you're analyzing these graphs, one of the first things you want to know is which of the vertices joined to all others. So I think that's a good question. I can't give you an answer precisely for the enhanced power graph. Does that answer the question?
Yes, sir. And one more thing, the enhanced power graph is always contains loop, right? As x is always adjoint to x.
Sorry, I didn't quite catch that. Could you repeat, please?
The enhanced power graph is always contains loop, right? As S
yes.
is
Well, yes, that's right. But I don't care about loops. You can throw them away if you like. I don't mind, because if you're just considering connectedness, then loops on a vertex don't make any difference. So for those questions I was talking about, loops don't matter, but they are there. And if you want to look at, for example, that random walk, then I think it's important to leave the loops in, because you must have the option of staying where you are at any point with some probability. So it's a good question again. It's a convention whether there are loops. Yes.
Huh?
Yeah.
Can we have any connection between the enhanced power graph and generating graph of a group?
Well, the enhanced power graph is a spanning subgraph of the non-generating graph. So, provided the group is non-abelian, yes, the edge sets are disjoint. Okay.
Okay. Thank you.
Okay. Right. Shall I continue?
I have one question.
Yes, go on.
I mean, we know that the Cayley graphs usually have large automorphism groups.
Yes.
So can we say something like that? I mean, for this, the power graphs or enhanced power graphs in particular cases?
We certainly can. I'm coming to that later on in the talk, if you just mind waiting. So in the last part of the talk, I want to get on to automorphism groups. But I want to say a little bit about some graph theoretic properties of these graphs. So a very important property of graphs is being perfect. A graph is perfect if every induced subgraph has clique number equal to chromatic number. Power graphs are always perfect, and there's a fairly simple reason for that. A power graph, there's always a directed power graph underlying it. And the directed power graph is a partial pre-order, not a partial order, because there may be elements that are comparable both ways around, but it's a partial pre-order. And the comparability graph of a partial pre-order is always perfect. So the power graph is the comparability graph of a partial pre-order and is therefore perfect. So just briefly why that's true. If you have a partial pre-order, so this is it's a reflexive and transitive relation. So we call two elements equivalent if they're joined in both directions, then that will be an equivalence relation, and the equivalence classes are partially ordered. And so we have a partial order on the set of equivalence classes. Now we just refine this to a partial order on the whole thing by simply arbitrarily ordering each equivalence class. This doesn't change the comparability graph because elements of the equivalence class are joined in both directions, so they're joined anyway. And so what we get is that the power graph is the comparability graph of a partial order. And so by Dilworth's theorem, by the easy direction of Dilworth's theorem, it's perfect. So the power graph of a group or semigroup or even a power associative magnum, you don't need the associative law for all elements, but only for powers of a single element to make this proof work. That graph is always perfect. But the enhanced power graph and the commuting graph can fail to be perfect. So if you take, for example, the commuting graph of the symmetric group S5, so we take the 5 transpositions, 1, 2, 3, 4, 5, 1, 2, 3, and 4, 5. I'm thinking of them in a cycle. Each one commutes with its neighbour because they have disjoint support, but it doesn't commute with the things 2 steps away in the cycle. 1, 2, and 1, 5 don't commute. So the induced subgraph is a 5 cycle, and that has clique number 2 and chromatic number 3. Those are not equal, therefore the graph is not perfect. So the enhanced power graph can fail to be perfect. And for the commuting graph, you replace these transpositions by cycles of pairwise coprime lengths, but with the same intersection pattern. And you can build an example where there's a group with commuting graph not perfect. So, which groups have an enhanced power graph perfect? Which groups have commuting graph perfect? I will say a little bit about the enhanced power graph later, but there are a few results. Britnell and Gill have a paper on the perfectness of the commuting graph, but the complete answer is definitely not known in either case, and it will be very interesting to know. So here's a program that might help you to figure out which are the groups whose enhanced power graph is perfect. So we look at products of graphs. So there are many different products of graphs. I will talk here about the strong product. So you take the Cartesian product of the vertex sets, you put an edge from x1, y1 to x2, y2 if x1 and x2 are equal or adjacent, and y1 and y2 are equal or adjacent, but the two pairs are not actually the same, right? So it's denoted by this symbol of a times in a square, and the mnemonic for this is a very nice mnemonic. That symbol represents the product of two copies of the complete graph on two vertices. If you take the product of an edge and an edge, you get this graph here. And various other graph products like the Cartesian product and the categorical product have symbols which can be defined in the same way. So the commuting graph of the direct product is the strong product of the commuting graphs of G and H. If the orders of G and H are co-prime, then the enhanced power graph is the strong product of the enhanced power graphs. So that'll tell us about products of groups of co-prime order. Now, the enhanced power graphs of finite nilpotent groups have clique number equal to chromatic number. That takes a little bit of proving, but when are they perfect? It's not known. But suppose we could answer that question. Well, a nilpotent group is the direct product of its Sylow subgroups, and their orders are powers of distinct primes. Therefore, it's a direct product of groups of co-prime orders. So by this result we just saw, its enhanced power graph is the strong product of the enhanced power graphs of these P groups. And then for a group of prime power order, the enhanced power graph is equal to the power graph, right? Because if two elements are both powers of the same thing, that thing must itself have order of prime power, and that means one element is the power of the other. That graph is perfect, we just saw. So these things are perfect. The complement of a perfect graph is perfect. This is the weak perfect graph theorem of Lovas. And the complement of the strong product of two graphs is the categorical product of their complements. Moreover, we know conditions for the categorical product of two graphs to be perfect. This is an old paper of Ravindra and Parthasarathi. So I think that by putting those things together, it should be possible to get a handhold on the question of which are the groups, which are at least the nilpotent groups, that have their enhanced power graph perfect. And if you can do that for nilpotent groups, you might be able to get somewhere with arbitrary groups, and you might see examples soon. So other graph theoretic properties. Well, there's a survey here of graph theoretic properties of power graphs, and so just very recently and completely by chance, I happen to have started a project with Pallavi Manna and Ranjit Mahatari on groups whose power graphs belong to various well-studied classes defined by forbidden-induced subgraphs. Now, I didn't say so at the time, but perfect graphs are defined by forbidden-induced subgraphs. This is the famous strong perfect graph theorem that says that a graph is perfect if and only if it doesn't contain either an odd cycle or the complement of an odd cycle of length greater than 3 as an induced subgraph. So all these classes I'll be talking about are subclasses of the perfect graphs, but defined rather differently. So a graph is a cograph if it contains no 4-vertex path, no path on 4 vertices as induced subgraphs. This is an interesting class in many ways. It's the smallest non-empty class of graphs closed under complement and disjoint union. And we were able to prove that if G is a finite nilpotent group, then the power graph of G is a cograph if and only if G is either of prime power order or a cyclic group whose order is the product of two distinct primes. So the choices there are rather limited. Any group of prime power order, but if it has more than one prime, then it must be the cyclic of order, the product of two primes. Next class are the chordal graphs, the graphs that contain no chordless cycles of length greater than 3. So any cycle of length greater than 3 will have a chord. And if you have a finite nilpotent group again, then the power graph is chordal if and only if either the group has prime power order or its order has 2 prime divisors, and one of the CLF subgroups is cyclic and the other has prime exponent. So a slightly strange condition. You can take the direct product of a cyclic group of 1 prime power order and a group of prime exponent of a different prime. But those are the only ones. Then we come to something where we can have a complete characterization, not just for nilpotent groups, but for all groups. Threshold graphs and split graphs. A threshold graph is a graph containing no induced path or cycle on 4 vertices and no 2 disjoint unconnected edges. So no copy of 2K2 as an induced subgraph. This is the smallest non-empty graph class that you can get by the operations of you're allowed to add an isolated vertex or add a vertex joined to all others. So it's built up in that way. And a split graph is a graph whose vertex set is a disjoint union of a set inducing a complete graph and a set inducing a null graph. So split it into 2 parts, one a complete graph, the other a null graph, with arbitrary edges between them. And this is also a nice class of graphs, good algorithmic properties. A graph is split if and only if it has no induced cycle of length 4 or 5 and no 2 disjoint unconnected edges, so no copy of 2K2. And it's the 2K2 that's the crucial thing here. So this is the theorem. The following conditions on a finite group G are equivalent. Power graph is a threshold graph, power graph is a split graph, or the power graph has no 2 disjoint unconnected edges. So just forbidding 2K2 is enough to do the business here. And these are the groups. Cyclic groups of prime power order, elementary abelian 2 groups, dihedral 2 groups, cyclic groups of order twice a prime, dihedral groups of order twice power of an odd prime, or 4 times an odd prime. So that's the complete list of groups whose power graph belongs to one of these classes. And they're exactly the groups that have no pair of subgroups such that both H minus K and K minus H contain elements of order greater than 2. So I think there are many other things that can be done here, but I just want a little detour to look at the question of when is the power graph of the group PSL2Q a cograph? So this is one of the smallest, easiest classes of simple groups to look at. And I'm going to make it even easier by taking Q to be a power of 2. Then you can show that the power graph of PSL2Q is made up of copies of the power graph of an elementary abelian group of order Q and cyclic groups of order Q minus 1 and Q plus 1. So we've removed the identity and just have the non-identity elements. So it breaks up into these many, many connected components. And so you remember that for a cyclic group, for the power graph of a cyclic group to be a cograph, the cyclic group must be a product of, must either have prime power order or a product of 2 primes. So we want to know, when is it the case, Q is a power of 2, when is it the case that both Q minus 1 and Q plus 1 are either prime powers or products of 2 primes? So if you make one of these a prime, then you have a Fermat or Mersenne prime. If one is a prime power, you get the Catalan equation whose solutions we know. But we don't know all about Fermat and Mersenne primes, but we have a slightly different problem here. We want to know for which positive integers d, is it the case that both 2 to the d minus 1 and 2 to the d plus 1 are the products of at most 2 primes? Are there infinitely many? There are quite a lot. So here are the values up to 200 for which this is true. You see, there are quite a number of them, but it's not clear whether this set is going to be finite or infinite. And number theorists I've talked to say it's probably finite, but they have no idea how to prove it. Okay, so now to automorphism groups. And the difficulty in studying automorphism groups of these graphs is that they have many pairs of vertices with the same neighborhood. So let me just give you a little example. Suppose we take the alternating group of degree 5 and we look at the generating graph, and almost the same comments would apply to power graphs and commuting graphs and all these things. So two elements that lie in the same cyclic subgroup will have the same neighborhood, because if A and B generate the group, I can replace A by something else that generates the same cyclic subgroup, and I'll still have generators. So two elements generating the same cyclic subgroup have the same neighborhood. So if you take, there are 6 subgroups of order 5, they give you 6 disjoint sets of 4 vertices, any 2 of which have the same neighborhood. And similarly, there are 10 subgroups of order 3, so you get 10 disjoint pairs of vertices which are indistinguishable. So you can permute those arbitrarily. So you get the symmetric group S4 to the 6th power and the symmetric group S2 to the 10th power. Now this is of no interest. This is just sort of rubbish, but it slows down the computation, because this means that the automorphism group of this graph is a huge group. And narrowing down on the interesting stuff is quite difficult and tricky. So we'd like to factor out that normal subgroup before we proceed. So I'll just say something about power graphs here, though you could do this sort of thing for any of these types of graphs that I've been talking about. So a paper by Ashrafi and 2 others in 2017 looked at automorphism groups of power graphs, and they made a conjecture. They worked them out in some specific cases, and then they made a conjecture. And this is their conjecture. You take the class of groups that can be obtained from the trivial group by 2 operations. You're allowed to take the direct product, or you're allowed to take the wreath product of what you've already got with a symmetric group, right? So 2 simple operations for building groups. And they conjectured, or at least let's put it a different way. They asked whether it's true that the automorphism group, the power graph of any finite group, belongs to F. And surprisingly often that turns out to be true, but it's not completely true. And the sporadic Mathieu group M11 provides a counterexample. So I want to say just a little bit about M11 here. The power graph of M11, or the reduced power graph, we take the identity out. So these are the connected components. There are elements of order 11 in here, and their powers only of themselves. So they give you a complete graph of size 10. And there are 144 such subgroups, so we get 144 complete graphs of size 10, corresponding to the elements of order 11. We get 396 complete graphs of size 4, corresponding to the 396 subgroups of order 5. So already you see, what have we got? We've got symmetric group of degree 10 raised to the power 144, and then a symmetric group of degree 144 permuting those things around. So we actually have the wreath product of S10 with S144. And down here we have the wreath product of S4 with S396. And that's of no interest, because these are just little complete graphs that are connected components. So throw them away. What's left is a single connected component on the remaining 4,895 vertices. That's still quite a lot of vertices, and this still has quite a large automorphism group, even when we've dumped all this junk here. But we can compress it in a sense. So look at the relation on vertices of having the same closed neighborhood. Factor out that relation, and then in the resulting graph, look at the relation of having the same open neighborhood, and factor out that relation. And if you do those 2, then you can't reduce it any further. You end up with a connected graph on 1,210 vertices, whose automorphism group is exactly the group M11 that we started off with. So once you've thrown away the junk and factored out the junk, you're just down to M11, which was the group that we started off with. But of course, you have to do something. You have to show that these reductions haven't messed things about. So you have to show that when you factor out this equivalence relation, you don't introduce more automorphisms than you had before, but it's possible to do that. So this is all computational. say in here. So we get down to M11. Now that means that this is a counterexample to that conjecture of Ashrafi et al. Because groups in their class F can't have anything other than a cyclic group or an alternating group as a composition factor. And here we've got M11. But on the other hand, the automorphism group of any cograph belongs to F, and that's a fairly simple inductive proof based on the way you build cographs up by taking complements and disjoint unions. But unfortunately, that doesn't characterize cographs. Automorphism groups of trees also all belong to the class F. This is for structural reasons. Any tree has either a center, a vertex that's fixed by the automorphisms, or a bicenter, an edge that's fixed by all automorphisms, and then you break it down into smaller trees, and so there's an inductive proof. Automorphism groups of almost all random graphs belong to F. This for a very stupid reason. Almost all random graphs have only the trivial automorphism group. So the trivial group certainly belongs to class F. So, but anyway, automorphism groups of cographs belong to F. So if you have a group whose power graph is a cograph, then its automorphism group satisfies the Ashrafi et al. Conjecture. So there are some, at least, for which it's true. Now, what we saw in the case of M11 was that the automorphism group of G, so basically in that case, M11 itself was a homomorphic image of the automorphism group of the power graph. You throw away all those Reith products of symmetric groups, and you factor out some more products of symmetric groups, and what's left was just M11. For which finite simple groups does something like that hold? It doesn't hold, well, I went to M11 because it doesn't hold for a lot of the smaller groups. You can take A5, A6, small PSLs. Their automorphism group does belong to the class F. So I had to go to M11, but for which other groups is that the case? And so I think there are probably things to find there. But certainly if you're looking at the automorphism group, so to answer the question from before, there is an awful lot of junk in the automorphism group of one of these graphs. And the best way is to compress them by getting rid of that junk. If there are direct factors that are Reith products of symmetric groups, throw them out. If there are normal subgroups that are direct products of symmetric groups, factor them out. Eventually, with a bit of luck, you'll come down to something interesting. So that's the end of my talk. Here are the references. I won't linger on these because they will be in the slides, and if you want the handout version, you can have it. So I'll just say thank you for your attention, and there's a nice little picture to cheer you up to finish with. So thank you.
Thank you, Professor Cameron. And now I will ask the participants, if you have any questions, you can ask.
Sir,
yes,
I have a question.
Yes?
Okay.
Yes, go ahead.
I have a question that you have mentioned that the commuting graph of G tensor product H is the strong product of the commuting graph of G and N, right? So
Yes.
what can we say about the commuting graph of G Cartesian product H?
Well, that's an exercise for you. I needed it for the strong product. I think you can probably figure out what happens for the Cartesian product.
Okay.
I won't answer the question. I don't know the answer off the top of my head. I'm sure I could sit down and work it out if I really had to. I needed it for the strong product. I proved it for the strong product. But you can figure it out. You'll find out, I think, fairly easily what happens.
Okay, thank you.
Sir, I have a question, sir.
Yes?
Can we, like directed power graph, can we define directed enhanced power graph? I have an idea, but I don't know it is valid or not.
The directed enhanced power graph. There's no
directed
obvious
enhanced power graph.
Yes. There's no obvious way to direct the enhanced power graph because remember we join two elements if the group they generate is a cyclic group.
Yes, sir.
That doesn't mean that one's a power of the other, you see. So that relationship is completely symmetric, and how you direct it is not clear to me. So I think the answer is, I don't know. If you can find a good way of doing it, I'd be very interested to hear about it.
Suppose A and B two are adjacent, and AB belongs to some generated C. Suppose A equal to C power I and B equal to C power J. If I less than J, then there is n from A, edge from A to B. Can we define like this?
Well, the trouble with that definition is that they're both powers of C. But what if I took a different element C? What if I said C inverse, for example? If I replace C by C inverse, A and B are still both powers of C inverse, but now you reverse the direction, right? So your direction depends on making a choice of that element C. And
choice of element of C, sir. Yeah, okay. I got it.
So there are many choices of C, and they may give you different answers to what the direction of the AJP is. Yeah?
Right, sir. Okay, thank you so much.
Any other questions?
Yes, I have a question.
Yes.
Hello, sir.
Please go ahead.
Hello, sir.
Yes, hello.
Yeah.
Can you hear me?
Yeah, yes, I can hear you, sir. For cyclic groups, we can see that the enhanced power graph and the generative graph is same.
Well, for a cyclic group, the enhanced power graph is complete, right? Because any two elements generate a cyclic subgroup. The generating graph, however, is not complete in general, because if you take, say, a cyclic group of order 12, now take an element of order 2 and an element of order 3. They don't generate.
Okay. But for generating graph, two elements will be adjacent if they generate the whole group.
Yes.
So, I mean, is there any connection between the automorphism group of these two graphs, the enhanced power graph and the generating graph for non-cyclic groups?
Oh, I'm sure there is. But again, this is an exercise for you. And I think to answer that exercise, you first of all have to look at this way of compressing the graph by saying, look at the equivalence relation of vertices having the same neighborhood or perhaps the same closed neighborhood. Factor those equivalence relations out. But the equivalence relations will be slightly different, very similar, but slightly different for the different kinds of graphs. So, for example, for the generating graph, as you see, two elements will be equivalent if the... Sorry, am I making sense? I think there is a lot to be said, and so here's a little test problem. Can you decide which groups have the property that the automorphism group of the power graph or enhanced power graph is the same as the automorphism group of the generating graph or of the commuting graph? Yeah, for which of these graphs do you get the same automorphism group? For which of these groups do the different graphs have the same automorphism group? I think that's an interesting question, and you will probably find some interesting stuff if you try it out. But I can't give you an answer.
One more question, sir, I want to ask you.
Yes, of course.
In a picture of QA, there is a picture where the central vertex is colored as red and non-central vertex is colored as black.
Yes.
Here in that picture,
there.
Yeah,
yes.
This is the picture. So I have observed one thing, that if we consider any walk between any two non-central vertices, so it should pass through the central vertex.
That's
any
right.
one of the central vertex. So I don't know, but is this observation leads to any interesting fact?
Well, what that's telling you is that if you remove the center, as people do when they're studying the commuting graph. If you remove the center, the graph becomes disconnected. So to say that removing the center disconnects the graph says that to get from one component to another, you must go via the center, right? So if you look at a graph a group whose commuting graph with the center removed is disconnected, then it will have exactly this property that there'll be vertices. To get from one component to another, you must go through the center. Yes?
Yes.
So yes, that's exactly what it corresponds to.
Okay. Thank you.
Okay?
Yeah, okay, thank you.
Hello, sir.
Yes.
Myself, Vinayak Joshi from Pune University. The intersection graphs of subgroups of a group is you can look at the complement of the zero divisor graph of the poset of subgroups of a group G.
Yes.
And using that, recently we settled that these graphs are weakly perfect. That means the chromatic number is same as the clique number of intersection graphs of subgroups.
Okay.
So that
nice
is what
result. Thank you.
Yeah, thank you, sir.
Yes. Yes, I think the questions of whether these graphs are perfect, there are some very interesting questions there. And I hope that some of you would be inspired to push them further.
Yes, sir. Zero divisor graphs, which zero divisor graphs are perfect graph that we have characterized. That may be helpful to give the highlight on the intersection graphs of subgroups of a group G.
Well, possibly, except that not every group G lives inside a nice ring. But yes, I mean, these problems are closely connected, certainly, yes.
Yeah, thanks.
I have a question.
Yes.
Hello.
Hello.
Thank you for your presentation. I remark that a lot of research. I have a question in general. I remark that a lot of researchers work on a graph without a loop, but I don't know why.
Well,
I would like to know why.
Well, I think the answer is, for some problems, loops make a huge difference, but for other problems, they make no difference at all. Like, if you're given a graph and you want to know, is it connected? Then the presence or absence of loops makes no difference to that because the loops don't help you to connect up the graph. But on the other hand, if you want to know, can the graph be colored so that there are no monochromatic edges? If there's a loop, it can't be colored because the two ends of the loop will always have the same color. So it really depends on what problem you're looking at. Sometimes it makes a huge difference. Sometimes it makes no difference at all. And to go back to this random walk business, if you have loops, that allows you to take a little rest in random walking and say, right, at the next step, I'm going to stay where I am. And that sometimes makes a big difference to the behavior. And also, it makes things a lot easier to prove in many cases. So the answer is sometimes yes, sometimes no.
Okay. Thank you very much for your answer.
I have two questions.
Yes, please.
The first one is for power graph, you said it is perfect. And for enhanced power graph, also for some cases, we know it is perfect. So is the edge...
It's not always perfect.
Yes. For some, basically, vertex coloring is well studied in this power graphs, enhanced power graphs, and all this stuff. But whether edge coloring is also studied, do we know anything about chromatic index?
Chromatic index? No, I don't. This is something that I don't know any work on that. Maybe you do, but take any graph property or any graph parameter. You can ask about any of these graphs that I'm talking about, and very likely there will be interesting questions there. There will be interesting stuff to find out. So I don't know about the chromatic index of any of these graphs that I've been talking about. This is something that I haven't actually looked at.
Okay. So second question is about this generating graph.
The generating graph, yes.
So if the group has at most 2 members in the generating set, then this defining this generating group is really good. But the group has more than 2 number of elements, then can we define some sort of hypergraph and study all these things?
Certainly we can. Certainly we can. People have only just begun thinking about that. I mean, people have been looking at groups with more than 2 generators for a long time, but the idea of actually looking at the generating sets and thinking of them as edges of a hypergraph or something like that. So let me just give you a little example. Suppose you take the elementary abelian group, so the direct product of copies of the cyclic group of order P. That's a vector space over the field of P elements, and the minimal generating sets are exactly the bases of the vector space. And that's a very interesting collection of sets. In fact, it's a matroid. It's a set of bases of a matroid. And so, that doesn't happen very often. If you have a group of prime power order, then its minimal generating sets will be the bases of a matroid. But if the group doesn't have prime power order, that will probably not be true. And I have a little bit of thought about that. I have a paper with Andrea Lucchini and Kolkata-Dougal where we look at questions like that, but I know very little literature about it. I think there are many interesting questions there.
Okay, thank you very much.
So any further questions or comments? Anything from the audience? You can write on the chat if you like. Okay, so if no further question, then it's our great pleasure to thanks.
Okay, I just want. Hello?
Yeah. Yes, Professor Ghosh, could you please continue? Yeah.
Oh, Professor Cameron, hi. Hello.
Yes, hello.
For your great illuminating lecture.
Sorry?
It's great to see you with the lecture again. Can you
it's
just repeat the group or the construction, not the group? You just told what is matroid structure is coming on. Can you please repeat that again?
Okay, this is the statement. Suppose you take a group and you look at the collection of minimal generating sets for the group, right? Minimal generating sets. Then if the group happens to have prime power order, then these minimal generating sets are the bases of a matroid. This is essentially Burnside's basis theorem. But if the group doesn't have prime power order, then that will almost certainly fail. I don't know a general result, but I think there aren't any other groups apart from groups of prime power order where you will get a matroid out of that. But you may get other interesting structures. And this has not been much looked at, but as I say, there are just a few results. I could probably, give you a handful of papers that talk about this question, but not much is known.
Okay, thank you, sir. Thank you.
Okay.
So it's now our great pleasure to give thanks to Professor Cameron for his nice and illuminating talks, and I'm sure that all the students as well as all the faculty members are enriched with your talk, from starting from the very basic to quite a deep result with lots of varieties of groups and graphs interplay. Thank you so much for your nice talk, and I'm sure that in future also we'll have some opportunity to collaborate with you and have some more talks for all the students as well as faculty members here. And thank you so much for your kind and generous support for all of us. Thank you.
Well, thank you. And your job now is to solve some of these questions. Okay, thank you.
Thank you very much.
There. Okay.
Am I audible to everyone? Am I audible to everyone? Yes. Good evening to all of you, and welcome again for the next contributory session of the International Conference on Algebraic Graph Theory and Applications, ICAGTA 2020. And thanks again Professor Peter Cameron for his illuminating and informative talk on graphs defined on groups. Hope participants enjoyed a lot from his wonderful presentation. Now it is my immense pleasure to invite and welcome our colleague and dynamic faculty of our department, Professor Abhishek Odhikari, to chair the contributory session. Now I request to Professor Odhikari to chair the session, please. Please continue, Professor Odhikari.
Thank you, Subhash. Now it's the last session for today's whole day. So it's a long day, but still we have 4 very nice presentations waiting for all of us. So without wasting any further delay or any time, so directly may I request Hiranmoy Kishode to please share your slides with all of us. And the title of his talk is on the connectivity of enhanced power graph of finite group. So it's for Hiranmoy, please.
Yeah.
So as you all know, it's a 15 minutes time. So please just take care about all the timing and all. Thank you.
So is the slides visible and am I audible?
Yeah, it's loud and clear. Thank you.
So I really thank the organizers for organizing the conference, and I'm happy that I have been given an opportunity to present my work. So this is a joint work with Shudip Bera and Shajal Mukherjee, and the topic is on the connectivity of enhanced power graph of finite group. So Professor Peter Cameron has already introduced the notion of power graphs and enhanced power graphs. And also my fellow speaker, Shubhnarayan Singh, he has also introduced the notion of power graphs. So let me just recall. So for a group G, the power graph PG is the graph such that if for any two vertices U and V, they are connected if and only if either V is a power of U or U is a power of V. And the enhanced power graph, there the adjacency relation is for any two vertices U and V, they should be, for there exists an element W such that U and V both should be power of W. So this definition may seem a little different than the definition so Professor Cameron gave. So this will be very clear within 2 or 3 slides. So here I have not omitted the identity yet. So this is introduced. So the notion of power graph that has been introduced by Chakraborty and Ghosh in 2009, and the notion of enhanced power graph that has been introduced by this Alipur Akbari, Cameron, Nick and Dishan-Shevishi in 2017. So let gamma be a graph where V is the set of vertices and E is the set of edges, and vertex connectivity, that is a minimum number of vertices which needs to be removed so that the induced subgraph gets disconnected. And a vertex, it is called a dominating vertex if it is adjacent to every other vertex. And for a graph gamma, let this dominating dom of gamma that denote the set of all dominating vertices in gamma. And the enhanced power graph, we call that dominatable if it has a dominating vertex other than identity. Because so if one just checks the definition, then every element is, so identity is so we will mostly deal with finite group. So identity is power of every element. So then identity is adjacent to all the elements. So if it has any other, that is not interesting. So if it has any other vertex which is adjacent to all the vertex, that is the interesting case. So in the 2017 paper, so they asked about the connectivity of power graphs when all the dominating vertices are removed. And Cameron and Jaffer in 2020, so they answered this question for power graphs. And the goal of this paper is to investigate the same question for enhanced power graphs, especially of finite abelian groups and some family of non-abelian groups also we do. So for this we first define the thing. So the proper enhanced power graph, so which is denoted by G double star G. So that is the graph obtained by deleting all the dominating vertices from the enhanced power graph GG. And the G single star graph. So that is the graph where we delete only the identity element. And if G is such a group such that there is, so if in a graph there is no other dominating vertices other than identity, then it is clear that G star equal to G star star G. So now when is this kappa, that is the vertex connectivity of GG, is 1. So Bera and Vuya, so they proved that this enhanced power graph of the enhanced power graph of a group G that is complete if and only G is cyclic. So Professor Peter Cameron has also in his lecture mentioned a proof of this. So if it is cyclic, then it is complete, so it's not interesting. So let's move to the non-cyclic case, and there so we are first able to show that this is our first result, that let G be a finite non-cyclic abelian group. So from now on we assume non-cyclic. Then this kappa, this vertex connectivity is 1 if and only G is a P group. So that means just if we delete the identity vertex, then that G star G that becomes disconnected. So now we move. The thing is, we want to get the connectivity of G star star G. That is, we want to omit all the dominatable vertices. So for this, we actually need to know which groups are dominatable and what are their dominating vertices. So that was characterized by Bera and Vuya. So this is the theorem. So let G be a finite abelian group, and then this enhanced power graph is dominatable if and only G has a cyclic silo subgroup. So from this theorem, this dominating size of the dominating set that is strictly greater than 1 means it has a dominating vertex other than identity if and only if G can be written as G1 direct product Zn, where the GCD of the order of G1 and N is 1, and G1 has no cyclic silo subgroup. So in that case, we want to omit all the dominating vertices. So further, we first need to know which are exactly the dominating vertices of the enhanced power graph. So theorem 7 tells about that. So if G1 is a non-cyclic abelian group such that G1 has no cyclic subgroup, then this dominating set of G is G1 cross Zn, that is exactly the vertices Ex, where E is the identity of G1 and X is any element of Zn. So these are exactly the dominating vertices. And now, now if one gets all the dominating vertices, so now one can consider the graph G star star G. So we are able to prove that if we take G a non-cyclic abelian, so if cyclic, then we are already done. So we assume non-cyclic, and in non-cyclic abelian, if it is a P group, then we know that it is the vertex connectivity is 1. We already proved, so there is a result before. So we have assumed that it is also non-P group. So let G be a non-cyclic abelian non-P group such that G is isomorphic to G1 cross Zn, where the GCD of G1 and is 1, and G1 has no cyclic silo subgroup. Then this G star star G that is disconnected if and only if G1 is a P group. Now, from this we get that, so if G1 is a P group, then G star star is disconnected. So the vertex connectivity of GEG in that case, so that is clear. That is the number of dominating vertices. But if not that, then what it will be? So here we give an upper bound for a general non-cyclic abelian group. So let G be a non-cyclic abelian group. And by structure theorem, we can write G equal to as this, P1 to the product of Pi's, P2's going up to PR's. So where Ki greater than equal to 1 and this, then this is an upper bound, that this should be less than equal to P1 of T1 to the power T11, P2 to the power T21, PR to the power TR1 minus phi of that. So In the cases where this G is where in the cases where the G is star G is disconnected, then we ask what is the number of components. So for when G is a finite abelian P, so when it is a P group, so then the number of, we prove that the number of components is P to the power R minus 1 by P minus 1. So one can notice that this does not denote on the depend on the exponents T1, T2 going up to Tr. This only depends on the number of, so R, the number of, so this, and if G is an abelian group such that G is, so if it is a P group, then this is the number of components. Now there is another case which, so we also showed that if G is isomorphic to G1 plus Zn, where G1 is a P group, then this is disconnected. So in that case, what is the number of components? So we were able to give a bijection between the number of components of this GG and GG1, and by that we were able to prove that the number of components here, that also agrees with the number of component of this, and that is also P to the power R minus 1 by P minus 1. So, so this is all about the finite abelian groups, and so now we deal with some non-abelian groups, and symmetric is one of the important class of non-abelian groups. So Dustabadi and Faruqi, they prove that when n greater than equal to 1 and n or n minus 1 is prime, then this power graph of G, P star G, so P star G is defined, just omit the identity from G and look at that induced graph. So that is connected, and if n is such that n and either n or n minus 1, one of them is, if it is prime, then it is disconnected. So here we looked at, so this is for the power graph part. So we looked at the enhanced power graph thing. So for first thing, what the thing is, first we need to look at if there are any other dominating vertices. So we showed that for n greater than equal to 3, the enhanced power graph GSN has no dominating vertex other than identity. And therefore for n greater than equal to 1, these two graphs coincide. Then, so this is the last slide. So for any group G, you are able to prove that the P star G, so you obtain the, you omit the identity and look at the power graph, that is connected if and only if you omit the identity and look at the enhanced power graph. So using theorem, so this theorem 12, lemma 13 and theorem 14, so we are able to deduce the following, that for positive integers n greater than equal to 3, this vertex connectivity of this GESN, this enhanced power graph of symmetric groups, that is 1 if and only if either n or n minus 1 is a prime. So we are also able to do for dihedral groups, alternating groups, but yeah, I am not going there right now. So thank you.
Thank you, Hiranno, for your nice talk. So now it's the time for the audience to have any question or comments. So you are welcome. So any question or comment? So if not, then thanks once again, Hiranno, for your nice talk. So it's now the time for the next speaker, Pankaj Kalita. So may I now request to share your screen, Mr. Pankaj Kalita.
Yes, sir. I'm starting my screen.
Yeah.
I'm sharing my screen.
Yeah. The title of his talk will be Relation among the various types of energies of different types of graphs. So now it's yours.
So am I audible?
Yeah, you are audible and your screen is also visible.
Yes, sure, sir. Thank you. So before starting, I would like to thank the organizer for letting me participate and present my work along with Saint Cooper sir. So good evening to one and all present here. Myself, Pankaj Kalita, and I will try to discuss on relation among the various types of energies of different type of graphs. So before starting, I would like to thank Saint Cooper sir for guiding me in the right path to doing some proofs along with one conjecture. So in this paper, it consists of 4 sections. The first section is the introduction, whereas in the second section, it contains 2 proofs that are related to that relates the energy for the regular graphs and complete bipartite graphs. In the third section, it contains the relation. Here the third section is some kind of interesting because in this third section, I have concluded one conjecture, but we have got one counterexample today itself by one of our presenter, Rajat Kantinath sir. And then in the fourth section, I would like to conclude as a whole. So for the first section, introduction, I would first like to say about regular graphs and complete bipartite graphs. We all know that regular graphs are those graphs in which all the vertices have the same degree. And for complete bipartite graphs, we have to first know about what is bipartite graph. Bipartite graph is those type of graphs in which the vertex set can be partitioned into two sets, such that no two vertices of each partite set are adjacent. Now this is gonna be a complete bipartite graph, when each of the vertex set of one partite set is adjacent to all the vertices of the other partite set. Now for the next, like energy, Laplacian energy and signless Laplacian energy, let us move to the next slide. So here is the definition of the energy. Energy of a graph is nothing but the sum of the absolute value of all the eigenvalues of the adjacency matrix. Now, Laplacian energy of a graph is defined as the sum of the absolute value of all the Laplacian eigenvalues after getting deducted by the term twice m by n. And what twice m by n is? Twice m by n is the average degree of a vertex. That is, m is the number of edges and n is the number of vertices of that graph G. Now for signless Laplacian energy, it is defined as the sum of the absolute values of the signless Laplacian eigenvalues after getting deducted by the term twice m by n. So here comes to an end of the section 1. Now for the section 2, as I have said, we will see two proofs related to regular graphs and complete graphs. But the first theorem states that if G is a regular graph with n vertices, then the energy, Laplacian energy and signless Laplacian energy will be same. Now let us see the sketch of the proof. So for GB a graph with GB and R regular graph with n number of vertices. Now DG and AG be the degree matrix and adjacency matrix. Now degree matrix is none other than the diagonal matrix that contains the degree of and its elements are the degree of the vertices. Now we all know that Laplacian matrix is degree matrix minus adjacent matrix, and signless Laplacian matrix is degree matrix plus adjacency matrix. Now for an R regular graph, if we look at the degree matrix, since all the vertices have the degree R, therefore the degree matrix is going to be R of IN, that is, it is the scalar matrix RIN. So the Laplacian matrix is going to be RIN minus adjacency matrix, and the signless Laplacian matrix is going to be RIN plus adjacency matrix. Now we all know that all symmetric matrices are diagonalizable. So here RIN and AG are being symmetric matrix, therefore both of them are diagonalizable. And if we look at both the matrices, then both of them commute each other. That means by a well-known theorem that if A and B are two matrices that commute and both are diagonalizable, then we can say that both are simultaneously diagonalizable. So by using that theorem, we can say that RIN and adjacency matrix are simultaneously diagonalizable. And then again, we know that if two matrices are simultaneously diagonalizable and we know the eigenvalues of those two matrices along with the eigenvectors, then the eigenvalues can be added or subtracted. For let AIs be the eigenvalues of the adjacency matrix. And then for R of IN, we all know that all the eigenvalues are going to be R. So for Laplacian matrix, the eigenvalues are going to be R minus AIs. And for signless Laplacian matrix, the eigenvalues are going to be R plus AIs. So these are going to be the eigenvalues. Now let us look at the energy, Laplacian energy and signless Laplacian energy for our regular graph. Now by the definition of energy of graph, for regular graph, it is going to be AI, as we have assumed that AIs are the eigenvalues of the adjacency matrix. So it is going to be a summation of approximate sum of the absolute values of AIs. Now for Laplacian energy, we can say that since eigenvalues are R minus AIs, and here if we look at this term, twice m by n, it is going to be R. Why? Because twice the number, we all know that in graph theory, there is a theorem that twice the number of edges is equal to the sum of the degree of the vertices. So here if we find twice m, it is going to be R times of n. So n gets cancelled. So twice m by n is equal to R. So by calculating, we get that Laplacian energy is again equal to energy of the graph. And then similarly, signless Laplacian energy is also going to be equal to energy of the graph. So by this we can say that Laplacian energy and signless Laplacian energy of our regular graphs coincides. So here comes to an end of the first theorem. So here is the second theorem. So for second theorem, we will have to look at complete bipartite graph. Let Kmn be a complete bipartite graph. Kmn means the first partite set will contain m number of elements and the second partite set will contain n number of elements. This is like this we used to represent complete bipartite graph. Then for complete bipartite graph, Laplacian energy and signless Laplacian energy coincides. Now we will prove this. Now here is the sketch of the proof. So let us consider DZ, AZ, LZ, and L plus of Z be the degree matrix, adjacency matrix, and Laplacian and signless Laplacian matrix of this complete bipartite graph. Now if we look at the adjacency matrix, the first block matrix is going to be 0 of m. It is the 0 of m means here it will contain the first m vertices. That means since in a complete bipartite graph, no two vertices of the same partite set are adjacent. Therefore, this is going to be a 0mn. And Jmn is the matrix of order m by n, which entries are all 1. That means since each of the vertices of the first partite set is going to be adjacent with the second partite set. That means each of the vertex from the m number of vertices is going to be adjacent with the n number of vertices. Therefore, the second block matrix is going to be m by n, Jm by n. Similarly, this. So also we can easily check that degree matrix is going to be this matrix, and after that Laplacian matrix is dz minus az, which is going to be n times of in, and by using dz and az we can easily find that Laplacian matrix and signless Laplacian matrix. Now now we have to find the Laplacian energy and signless Laplacian energy. To find Laplacian energy and signless Laplacian energy, we have to find the eigenvalues of Laplacian matrix and signless Laplacian matrix. That means we have to find the characteristic polynomial of Laplacian and signless Laplacian matrix. Here is the characteristic polynomial of the Laplacian matrix. So it is the determinant of this matrix, and by using determinant of block matrix, we get this second line, and then by using a matrix calculation, we used to get this result. Then after that, if we find the determinant of signless Laplacian matrix, and then by using the determinant of block matrices, we get the second line, and then just by calculation, and we get this line. But if we look at the previous slide, the characteristic polynomial of Laplacian matrix and the characteristic polynomial of signless Laplacian matrix are same. That means both the eigenvalues of both Laplacian matrix and signless Laplacian matrix are same. Therefore, we can conclude that Laplacian energy and signless Laplacian energy coincide for the complete bipartite graph. Now here comes to the end of the section 2. Now here is the starting of section 3. Now section 3 gives the relation of types of energy for non-commuting graphs. I have taken the group U of 6n. For U of 6, for non-commuting graphs, actually defined for non-abelian groups. It is defined for non-abelian groups because it is defined as the vertex set is G minus, if G is a group, then the vertex set is defined as G minus ZG. ZG is the center of the group. Now, if we take the group B abelian, then ZG is going to be the group itself. That means there is no valid point to consider non-commuting graphs for abelian groups. That's why we always used to consider non-commuting graphs for non-abelian groups. Now U6n is a non-abelian group, and if we calculate the center of the group, it is the cyclic group that generates by a square. Now, if we look at the non-commuting graph of U6n, which is denoted by gamma of U6n, it is easy to say that it is a 4-partite graph. That means its vertex set can be partitioned into 4 partite sets. Now, after that, we can look at adjacency matrix of this graph is going to be this matrix, and then the degree matrix is going to be this matrix. And we have read one of the paper by Khorbani and Al-Khansari. He have found that the spectrum of this for spectrum of the gamma U6n is going to be this. Now, after that, we have found degree matrix and adjacency matrix. Then Laplacian matrix is going to be this matrix, and the signless Laplacian matrix is going to be this matrix. Then by using a software called MATLAB, I have found the energy and Laplacian. Then by using this generalized spectrum, I have found the energies for gamma of U6n for n equal to 1, 2, 3, 4, 5. And then by using a software called MATLAB, I have found the Laplacian energy and signless Laplacian energy for n equal to 1 to 5. And then I have got these values, and then I have observed that the relation is signless Laplacian energy is always greater than energy which is less than Laplacian energy. So I thought but just by looking at 5 graphs, we cannot say for whole non-commuting graphs that the relation of energies will be this for non-commuting graphs. So I have found for groups D twice and T4 and V8 and have found the same relation, but with an equality sign. But the interesting thing is that today in the first session, Rajat-Kantina sir proved this relation and proved that a conjecture energy is always less than Laplacian energy as wrong. So this conjecture is not going to be valid as we have got a counter example. So as a conclusion, I would like to say that for regular graphs, energy, Laplacian energy and signless Laplacian energy are going to be same. And for complete bipartite graphs, Laplacian energy and signless Laplacian energy are going to be same. But for non-commuting graphs, as a conjecture, we have stated that for non-commuting graphs, Laplacian energy and signless Laplacian energy is going to be related as signless Laplacian energy is greater than equal to energy which is less than Laplacian energy. But this conjecture needs to be improvised as Rajat-Kantina sir have always proved that Laplacian energy of non-commuting graphs can be less than energy. So I have to work on this. So here is the end to my presentation. Thank you. These are the references I have gone through. Thank you.
Thank you, Pankaj, for your nice and informative talk. Now it's time for any comments or questions from the audience. Any question or comments from the audience? So if not, then thanks once again.
Yeah, thank you, sir.
Okay. Now it's a time for the third speaker of this particular session, Mr. Gopinath Shahu. May I now request Mr. Gopinath to please share your slides.
Good evening, all. Let me share the screen.
The title of his talk will be Complex Adjacency Spectra of Cayley Diagrams.
Yes. Good evening, all. Is it visible now?
Yeah, it's visible. Just make it full screen. Presentation. Yeah. Okay, fine. Thank you.
So basically, my work is on it's a part of the spectral graph theory, where actually we are given with a graph or a digraph or a multi-digraph, and we associate with it matrices like adjacency matrix, Laplacian matrix. So we can associate a matrix with a graph. Now what we do, the matrices may have eigenvalues. If it's a square matrix, so always it has eigenvalues. So by studying the properties of eigenvalues, we want to find relationship of these eigenvalues with that of the structural properties of the graph. Okay, by structural properties I mean like for example, I'm saying for undirected graphs, if it is bipartite, we know that the spectrum, the adjacency spectrum, that means all the eigenvalues. If we list them or we'll collect them, we'll call it as the adjacency spectrum of the graph. Okay, so adjacency eigenvalues, the collection of all the adjacency eigenvalues. And if the adjacency eigenvalues are symmetric about origin, that means if lambda is one eigenvalue, then minus lambda is also one eigenvalue with the same multiplicity. That means they are distributed around origin in a regular way. That means if lambda is there, then minus lambda is there. Then we can say the graph is bipartite. Okay, so this kind of relation, there is a if and only if condition. That means if it is bipartite, then this spectrum, adjacency spectrum, is symmetric about origin, and if it is symmetric about origin, then we can say the graph is bipartite. So this kind of interrelationship we try to find out here. So here is this goal. The goal of spectral graph theory is to see how the eigenvalues and eigenvectors of a matrix representation of a graph are related to the graph structure. So here is one digraph. And so by digraph we mean this simple directed graph, and we are not allowing any kind of self-proof here. So this is the adjacency matrix of the digraph, and here the rows and columns are indexed by the vertex set of the digraph. So it is on 6 vertices, so the adjacency matrix is of order cross 6 cross 6. And how it is, the entries are there. So if it is, we are considering this 1, 2 entry, because it is corresponding to the vertex 1, and along the column also it is corresponding to the vertex 2. So it is a 1, 2 entry is 1 if there is an edge from vertex 1 to vertex 2. And there is no directed edge from 2 to 1, that's why it is 0. So this is how it is defined, and you can see the way it is defined. Generally, the adjacency matrix of a digraph is not symmetric. So it's not a symmetric matrix. So some problem arise while dealing with the adjacency spectrum of the digraph. Okay, so as it is not symmetric, it may happen. Its spectrum may contain complex eigenvalues. Just like this case, we have some complex eigenvalues. Okay, so if we have complex eigenvalues, we cannot compare two directed graph on the basis of spectrum, because again we can't compare complex values.
So those will be, again, we are having this problem. And what else? It may not have n linearly independent eigenvectors also, or orthogonal eigenvectors. That means here you will get, actually here you can see 0, its algebraic multiplicity is 3, but geometric multiplicity is 2. So it's lagging. So this, to overcome this kind of error, we define a new matrix, we call it complex adjacency matrix. And how we will consider it? Instead of putting 1, we'll put 1 plus I by 2, and in the other part, if it is from 1 to 2, we are putting 1 plus I by 2, and from 2 to 1, we are putting 1 minus I by 2. So this complex, or the imaginary part, basically indicates the direction. Okay, so this is how we define, and the way we define it becomes a Hermitian matrix. So all our eigenvalues become real, and we'll get also n orthogonal eigenvectors. Okay, and using this, we have also studied properties of many multi-digraphs, as well as different types of digraphs and structural properties. So let's see how it works in case of cycle digraphs. So here are some cycle digraphs. Proper cycle digraph, it could be clockwise or anti-clockwise. That means all its edges are in clockwise direction or in the anti-clockwise direction. Then we call them the proper cycle diagram. There could be, these are some special kind. There could be many more. So like colliding cycle digraph, where you can see this one. It is a colliding cycle. Why I'm saying? Because one is in the clockwise sense, then some of them are in the same clockwise sense, and rest are in the opposite sense. Okay, so they are colliding. And similarly, there is alternating cycle digraph. Alternating, you'll find actually this one, which is basically, you can see one is in the forward direction or the clockwise direction, and the another one is in the just opposite direction. So alternate, the direction alternates. So this kind of diagrams we want to study, and their spectral properties. Let's see. So the first immediate result we get actually that complex adjacency spectrum of a proper cycle diagram. So it's a immediate matrix, means all these super diagonal entries will be 1 plus I, and the bottom diagonal entry will be 1 minus I by 2, and that way. So immediately its spectrum we can compute, and it comes out to be this. And the eigenvector follows this formula. And here you will find actually the eigenvector contains complex entries. Okay, so let's move to the next one, like how it will affect. Suppose that means if we'll change the orientation of some of the arcs of a cycle diagram, then how the complex adjacency spectrum is affected, that we want to study. So what we got, we find that if suppose there are v number of backward directed edges, we define forward directed edges as maybe this clockwise orientation, all those which are in the clockwise orientation, that as the forward directed edges, and all those which are in the anti-clockwise sense as the backward directed edges. So if there is, suppose D is a cycle diagram on n vertices and having b number of backward directed edges, then the adjacency spectrum of D consists of these values. Okay, and from the formula you can see it doesn't depend upon where these backward directed edges are exactly present. It depends upon how many are there. So it creates a problem again. We can't distinguish between two cycle diagrams based on actually they may be having the same number of backward directed edges, but the position may be different. But from the spectrum, complex adjacency spectrum, we may not be able to detect that. So what we did, for example, here we have a cycle diagram on 6 vertices, 2 cycle diagrams. One is alternating type, so they are alternating, and this is a colliding cycle diagram. And for both of them, we have the same spectrum. Okay, so they share the same complex adjacency spectrum. So it is difficult to judge two cycle diagrams based on their spectrum, complex adjacency spectrum. So here are some terminology: co-spectral, co-base diagram. So basically by co-base diagram we mean if we'll remove all the orientation, that means we will consider the undirected edges, corresponding undirected edges. So they have the same structure. That means they are on the same number of vertices and all this. So they have the same base structure and they are non-isomorphic and they have the same complex adjacency co-spectrum, or maybe, or I can say they have the same complex adjacency spectrum. Then we call them co-spectral co-base digraph. And there is something called counter-spectral co-base digraph. So what are those? They have the same structure, that means they are on the same number of vertices. And what else? They are non-isomorphic digraphs, and one's complex adjacency spectrum differs from the other by just a negative sign. That means if lambda is one eigenvalue in the first digraph, then minus lambda should be the eigenvalue in the second digraph. So they differ by the minus sign. So the result 3 we got actually, suppose we have two digraphs, cycle digraphs on odd number of vertices. They are D1 and D2. Then there must be either co-base digraph or there must be counter-spectral co-base digraph. So this creates the problem, and we want to find this. We have this question immediately, that how to find the structural difference between the two cycle digraphs on the same number of vertices, which complex adjacency spectra are the same. So we have many cycle digraphs on the same number of vertices which have same complex adjacency spectra. We want to sort them, or we want to find them, or we want to detect them. So in terms of some other parameters, so that they have different same spectrum, but we want to find how they are differing from the spectrum or from some extra more property. So what more property we need here? We are considering a cycle digraph on n vertices. Fi and Fj and Bj be the number of forward and backward directed edges in the path 1 to j. Okay. Then the components of the eigenvector xk corresponding to the complex adjacency eigenvalue lambda k, that we will be considering. So we will be considering one eigenvector corresponding to the eigenvalue whose algebraic multiplicity is 1. And its component will tell where the edge is oriented. Exactly. So I'm giving the proof here in the pictorial form. So this is a cycle digraph on 9 vertices. And suppose this component, we consider it as 1. So next one, the component will only increase in its argument. Okay. So it becomes e to the power I theta 1. And the next one, it will become, because they are in the same direction, so they increase by theta 1 amount. The component, the argument is increasing here. So it becomes e to the power I theta 1, then e to the power I 2 theta 1. So it becomes, because they are in the same direction, but as it changes the orientation, so there comes another argument. So that comes theta 2. So this way, we'll come down to this value. So e to the power I times 6 theta 1 plus 2 theta 2. And that has to be same as 1, because this is how it has to be same. So by equating that and making some calculation, we'll come to this result. Okay. And this is the example. We have considered the same this is the alternating cycle on 6 vertices, and this is the colliding cycle on 6 vertices. And we have considered the largest eigenvalue here, that's root 2. Its corresponding eigenvector is represented. The component of the corresponding eigenvector corresponding to this value root 2, these components are represented here. Okay. So corresponding to vertex 1, the value is 1. Corresponding to vertex 2, it becomes e to the power minus I pi by 4 is the component of the eigenvector corresponding to the eigenvalue root 2. So you can see the argument is here is minus pi by 4, then it changes because in the opposite direction, so it becomes again pi by 4 gets added, so it becomes 1, minus pi by 4, again pi by 4 gets added, so it becomes 0, then again minus pi by 4 and so on. So here it's a colliding type, and you'll see it becomes minus 5 again increases by minus 5 again increases by minus 5 but it collides here. So the direction and the component actually, it gets changed. And the argument is now increased by 5 amount. So it becomes e to the power minus I pi by 2. Now again becomes e to the power minus I pi by 4. And like this. So by knowing eigenvector corresponding to an eigenvalue whose multiplicity is 1, we can tell how the orientation is there for each edge in the cycle diagram. So this is our result. And this is the references. Thank you. And if there is any question, please.
Thank you, Gopinath, for your nice talk with nice examples, and the style that you have mentioned is like a teacher. Nice. Thank you very much for your nice presentation. Any question or comments that you have from audience? Any general comments or questions? So if not, then once again, thanks to Gopinath for his nice talk. And now it's for the last speaker of this session, Sanchita Pal. May I now request Sanchita to please share your screen. And the title of her talk is on characterizing proper circular arc catch diagrams. So please, Sanchita, it's yours.
Sir, is the presentation is visible?
Yeah, it's loud and clear. Yeah.
Okay. So first of all, I would like to thank the organizer and all other committee members of this conference for giving me the opportunity to present the talk. The title is on characterizing proper circular catch diagrams. This is a joint work with Sayan Gupta and Professor Shomik Ghosh of Department of Mathematics, Jadavpur University. So let's start with the introduction. Intersection graphs have many significant uses in real-world situational problems, and it was invented to model different types of geometric objects. And most popular among them is the class of interval graphs. So in this diagram, you can see that this I1 and I2 are intersecting. So that is why V1 and V2 have an edge in between, whereas I1 and I4 are disjoint. That is why V1 and V4 don't have any edge in between. So this is the definition of interval graphs. Another variation of intersection graph is the class of circular arc graphs, where the adjacency criteria is same as the interval graphs, and only the intervals are replaced by circular arcs here. So these I6 and I1 are intersecting, so that is why V6 and V1 are adjacent, whereas V6 and V2, that is I6 and I2 are non-intersecting, and that's why they don't have an edge in between. So in 1970, Tucker first characterized circular graphs in terms of the augmented adjacency matrix structure of it, and one of the important subclass of circular graphs is the class of proper circular graphs, where there exists no circular arcs which contains other property. And there are several characterizations of proper circular arc graphs till now, and this is one among important among them that G is a proper circular arc graph if and only if G is round. But I will tell you what the round means while describing one of our results. But for the time being, I'm just moving to the next slide. That another important variation of intersection graph for digraphs is the catch digraphs. A catch digraph is what? That for each vertex we associate a set SU and a point PU which lies within SU, so that U to V there is an edge if and only PV belongs to the set SU, and V to U there is no edge. Here you can see that PU is outside the set SV, and this is the definition of catch digraphs. And continuation to the study of catch digraph, interval catch digraphs was introduced by Prisner in 1989, and he first characterized interval catch digraphs. And in our paper, we introduced the circular catch digraphs analogous to the concept of interval catch digraphs, where we only replace the intervals by the circular arcs. Otherwise, the adjacency criteria is same. So this is an example of a circular catch digraph. In fact, this is an example of a proper circular catch digraph. So here you can see that no circular arc is contained in other property. So here you can see that V2 to V3 there is an edge, and P3 is within the interval, circular arc I2. Whereas V3 to V2, there is no edge, so P2 is outside of the arc, circular arc I3. So this is the definition. And what we do, we first characterize circular arc catch diagrams by giving a certain vertex ordering with respect to which the augmented adjacency matrix satisfies circular one's property along its rows. We all know the definition of adjacency matrices. Augmented means that we consider all the diagonal entries as one. That is, vi entry is 1. And circular one's property along rows means that we get some permutation of the columns of the augmented adjacency matrix with respect to which in each row the ones appear as a circular stretch. So in V6 you can see that the circular ones starting from the V6 column, and it just moves around the matrix, and it just ends at the column V3. So it's the ones are consecutive here. So this is what the circular ones property means. And we have ordered the vertices according to the increasing order of their p-values to get this theorem. And here you can also see that this 1.87 is within the interval 1.87,6. That's why the entry is 1. Whereas 1.87 doesn't belong to the interval 3.58, 9. That is why this P2 does not belong to the arc I3. Next, we define proper circular arc catch diagrams where no circular arc is properly contained in other, and we obtain the first characterization theorem for this graph class. And we have introduced the concept of monotone circular ordering of a binary matrix containing all types of rows. All types of rows except 0 rows. And this is basically a generalized version of monotone circular arrangement property, which was introduced by Basu, Das, Ghosh, and Sen to characterize proper circular bigraphs. They don't have considered the full rows and full columns, but we have considered all types of rows here. So what monotone circular ordering means, suppose let's take the binary matrix B, and with respect to some independent permutation of the columns and rows of it, it satisfies circular ones along rows and columns of it. So you can see that the ordering along the rows is not same as the ordering along the columns. So the ordering may be different, but along each row and along each column, the ones are circular. And next criteria is that so this is the next we define what is called the first type row. First type row means the rows which contain only exactly one stretch of ones. That is, V2 is the first type row. And what is second type row? Second type rows are those rows which contains exactly one stretch of zeros. So V7 is the second type row. And full rows are the rows where it contains only all entries as ones. Like V1 and V5 are the full rows here. So we treat the full rows as the rows of first type and as the rows of second type as per our need. And we have defined certain rules that when to treat it as a first type and when to treat it as a second type. So if a first type, if a full row occurs after a row of first type, or it occurs at the beginning of the matrix, then we treat it as a row of first type. Otherwise, we treat it as a row of second type. So here we have treated these as a row of second type. And you can see from the diagram that these ones and zeros can be partitioned by drawing this stair diagram. And for each rows, we have associated two variables lambda I and mu I in such a way so that the lambda I, the values, and mu I, the values of mu I are non-decreasing. And what is the lambda values of lambda I? Lambda I is the denotes the values where the circular stretch of 1 starts. So for the first row it is 1, for the second row it is 3, for the sixth row it is 6, and what is the values of mu I? They denote the ending value of the circular stretch. And for the row of V7, the mu I is basically 2, but we have just added the value of 7 to make it the all values of mu I increase, non-decreasing. That is, here you can see the 2 plus 7 is 9. So this is the monotone circular ordering. We have obtained the first characterization theorem of proper circular catch diagrams, and in terms of the augmented adjacency matrix structure, where the statement is that the augmented adjacency matrix must satisfy circular ones property along rows and columns of it, and the transform matrix is B. So let's move to the example. So this was the augmented adjacency matrix, and you can clearly see that in the column V6, you can see that 1 0 1 0 1 is happening. So this is not a circular ones along columns, but if we permute its rows and columns in such by certain rules, then they satisfy circular ones along both rows and columns of every row and column of it. So this is a transform matrix. This is B. So here the first condition is satisfied, and for next 2 and 3 condition, what it says that if R and S are 2 rows of B, so suppose R is V2 and S is V4, then R minus S means the set difference between the circular stretch of ones of rows in B. So R minus S means only these 2 entries. This V2 minus V4 means only these 2 entries. So this is a circular interval, and this is what the condition 2 says. And condition 3 says that if S and T are 2 non-trivial rows and R is a full row, then R minus S minus T is a circular interval. So just consider R as V5 and S as V3 and T as V4. So R minus S minus T is just the entry, this first 2 entry and the last 1 entry. So it is clear that last 1 entry and starting from here, if I just move like this and up to V1, then that must form a circular interval. So this was the last condition, and so we obtained the characterization theorem by just making some by getting this matrix M from B by certain rules. So what are the rules? That we have first put the rows of first type according to their occurrence of their I1 values. So what are the I1 values? Where the circular stretch starts. Here it was 1, and for this row it was 3, and if 2 I1 values matches, then we just ordered them according to their I2 values. That is where their wand ends. That is, here it is 4 and it is 6. So we have put V4 before V3, and then we put the rows of second type, and here according to the increasing values of their I3 values. So this in this case I3 is V6, and also for the row V6 the I3 value is same 6, but in that case where I3 is equal to J3 for any 2 rows, we just arrange them according to the non-decreasing value of the I4. Here for the case of V7 the I4 is 2, and here for the V6 this is 3. So we have put V7 before V6. And for the case of full rows, where to insert it or where not, we have defined certain kind of rules, and they are already written in the paper. And so, we want this matrix M to satisfy all these conditions which are satisfied by the augmented adjacency matrix, and it must also satisfy the monotone circular ordering. So you can see from this diagram that these matrices satisfy monotone circular ordering. And we have put the natural numbers over these upper stairs starting from 1, 2, 3, 4, 5 like this, and this helps us to determine the value of PIs and the IIs. PIs are the points and the IIs are the circular arcs, and these we obtain from the values associated with these stairs. And we have able to prove that this circular arc catch diagram representation is indeed satisfied by the matrix M as well as by the matrix B as well as by the matrix A star G, because row and while permuting rows and columns, it doesn't change any entry. I mean, if V2 V4 is 1 here, then it is also V2 V4 is 1 here, and also V2 V4 is 1 here. So at the end of the day, this representation is satisfied by the matrix A star G. So this was our characterization theorem of proper circular catch diagram. Next, we define a circular catch diagram which is called oriented circular catch diagram, where for each edge we have exactly one single direction, and it is called proper also if no circular arc is contained in other properly. And this is an example of a oriented proper circular catch diagram, where you can see that from this diagram that for each edge we have only associated a single direction. So here V2 to V1 is an edge. That means this V2 V1 entry is 1 and V1 V2 entry is 0, because there is no edge from V1 to V2. And this is the undirected underlying graph of this graph, and where all the directions have been removed, and this is an undirected graph clearly. And this is the corresponding augmented adjacency matrix associated to the underlying graph. This is basically a symmetric matrix, and we have been able to prove that if G is an oriented proper circular catch diagram, then its underlying graph is a proper circular graph. And here we need the theorem of calculation of proper circular graph, which tells us that G is round. And to prove UG is round, that is underlying graph is round, we have to orient each edge of UG by giving a single direction to it. Not necessarily this direction matches with the given direction of G. And so that in that circular ordering, the inset and outset of every vertex appears consecutively right to it and left to it. And for each edge, Vi, Vj, Vi plus 1 up to Vj form a transitive tournament. So looking at this example, you can this is a round enumeration of the vertices, and you can see that we orient the edges from V1 to V2 and V1 to V3, and V2 to V3, like V3 to V4, like this. And this orientation actually gives us the transitive tournament criteria. Next, this was our for the time constraint. I'm not going details to the proof. And neither next theorem tells us that G is the oriented proper circular catch diagram if and only if there exists a circular vertex ordering sigma for which the 4-point condition is satisfied. That is, if UVWX are there and UW there is an edge, then UV is an edge and VW is an edge, or UX is an edge and XW is an edge. So you can see from this diagram that this V3 to V1 there is an edge. So V2 to V1 is an edge and V3 to V2 is an edge. So this is the condition. And another thing that V3 to V5 is an edge. So V3 to V4 is an edge and V4 to V5 is an edge. So this is the characterization theorem of oriented proper circular catch diagrams. And these are the relations between these subclasses which we have discussed so far. And these are the separating examples G1, G2, G3, G4. And these are the references. And thank you.
Thank you, Sanchita, for your nice talk. So it's now for the audience to ask or give any comments or questions to Sanchita. So if there is no such questions, that's again thanks to the speakers. It's not only the last speaker, but I would like to thank all the 4 speakers of these sections. In this section, we have witnessed many things, like from the connectivity of enhanced power graphs, starting from power graphs to some spectral graph theory with Laplacian, signless Laplacian and all. And at the end, we have a glimpse of intersection graphs with circular arc diagrams, catchy diagrams. So it's a nice session that we all witnessed. And thank you very much to all the participants as well as all the audience for your kind cooperation towards making it a success. So thank you very much. Now I am switching it to Angsuman, please.
Thank you, Professor Odhikari, for chairing this session. And with that, we have come to the end of day 1. And before just ending the day, I just want to mention that tomorrow we will be getting a new meeting joining link, which you will be getting within an hour. So you need to join with that link. And for tomorrow, we are going to have 3 more invited lectures and 1 contributed lecture session. So with that, I end this session for day 1. Let's meet again in day 2. Thank you all.
So tomorrow at 2 p.m. of Indian Standard Time.
Please note that the tomorrow, I mean, day 2 will start at 2 p.m. in Indian Standard Time.
Thank you very much. So, bye all.